In this video, I'll describe the main features of the Java programming language. Java is an object-oriented programming language that encapsulates data and methods in objects and makes use of inheritance. Inheritance refers to the traits that an object gets from a parent object, the properties and behaviors it inherits. Think of the analogy in the real world where a child inherits the genes and traits of a parent, whether we're talking about a human or other animal or even a plant species or any living thing. Some characteristics are defined by genes and some by the individual. In Java, classes are the logical entities that describe the blueprint that objects can be created or instantiated from and inherited from. Think of a blueprint for a house. Many houses can be built or created from a given blueprint. Objects in Java are entities that have both state and behaviors created from the class blueprint. Whether you're conceptualizing a cat, a house, or a tabular list of values, objects are what represents the instance of it in a program. So Java is based on objects, classes, and interfaces, with objects being the stateful entities existing in a Java program's memory, and its behaviors and how a program interacts with it is based on the class blueprint and the interfaces it implements. Classes are the logical structure of properties and methods that objects can be instantiated from. Java also has the concept of regular classes and of abstract classes, and for abstract classes, objects can't be created directly from them, but they're used to help define other classes. And interfaces are a type of abstract class, but they don't contain any code. Interfaces regulate a class, describing how parts of the blueprint must be implemented. Interfaces are a way of making interaction with a class consistent. And taking the analogy of the house, you can think of the interface describing how a house should be built in terms of sizes and functions of elements in the house, such as the size of a door and the fact that it can open and close. What are the conceptual elements that make up an object? Well, objects can have variables to maintain the state of the object, to describe certain characteristics about it. For example, if we have an individual cat, it may be described by its color, its size, and a name. Objects have behavior and can perform actions. For example, a cat has the ability to walk, run, jump, and meow. Objects have a unique identity. Even if two objects are the same, they are differentiated. Twin cats, even a clone of a cat, would be different. No two objects can occupy the same space at the same time. In Java objects, we have a unique object identity which is used to internally identify it by the Java virtual machine. Even if multiple objects have exactly the same properties, they are uniquely identified. Apart from Java's object-oriented foundations, some of the features of the Java programming language include the following. Java is considered to be a secure programming language because it does not permit explicit memory pointers, and it runs inside a virtual machine sandbox. Components such as the class loader, bytecode verifier, and the security manager provide further security features and mechanisms to ensure the code is safe. Java is considered to be a robust programming language, since it provides strong memory management, the absence of memory pointers, and automatic garbage collection and exception handling and type checking mechanisms. Java is considered architecturally neutral because it doesn't have implementation-dependent features such as the size of primitive data types, such as int, which is different on different operating systems and hardware architectures. So Java makes these consistent across the various platforms it can run on. Some more features of Java include its simplicity to learn due to the absence of explicit memory pointers and operator overloading, and it's a garbage-collected language, so explicit calls to free memory when it's no longer in use is not required. Java is compiled into bytecode, which runs on a Java virtual machine, which then compiles the bytecode to run on local platforms, which allow for code portability, without having to create a separate binary file for each platform implementation. Java virtual machines can run on multiple operating systems and processor architectures, which allow Java to be platform independent. Some additional features that benefit the Java programmer are Java supports multi-threaded processes and uses a common memory area that's easy to synchronize with. Java supports the creation of distributed applications and allows for the use of remote method invocation. And Java is a dynamic programming language and supports loading classes on demand, dynamic compilation, and automatic garbage collection. And that concludes this presentation on Java features. In this video, I'll describe the Java virtual machine and how it relates to Java. So Java and other languages that compile to Java bytecode, such as Scala and Clojure, are available to run on the Java virtual machine, or JVM for short. The JVM is available for multiple operating systems, allowing Java to run on that OS. The JVM contains several key components. The class loader needs to recognize and load code that compiles with the Java class file format. The Java virtual machine architecture operates on basic values such as integers and floating point numbers and contains a garbage collector to manage heap memory. Java bytecode is an abstract machine language that runs on the JVM. Java code is compiled to Java bytecode, and JVM languages include any language that can compile down to Java bytecode. The bytecode verifier checks and confirms all bytecode before it's executed on the JVM, and bytecode interpreters will run Java bytecode on any machine that runs the interpreter. The just-in-time compilation will convert and translate Java bytecode into native machine language in real time. The class loader is used to recognize and load code that compiles with the Java class file format. Some of the key components of the class loader include the following. The first action of the loader is to find and import the binary data for the type. During the linking process, the following occurs. Verification is performed to ensure the correctness of the imported type. Then preparation is done to set aside memory for class variables, and during the initialization phase, the Java code is invoked and the class variables are initialized. The Java virtual machine has several key components that are essential to its operation. The JVM operates on basic values such as integers and floating point numbers. Each JVM thread has its own call stack, which is used to store frames, and frames are created when a method is called and is deleted when the method exits. The JVM garbage collector is used to manage data that is stored on the heap. Memory is automatically garbage collected and freed when there are no more references to that memory. Java bytecode is an abstract machine language that runs on the JVM. Bytecode instructions are grouped into the following types of tasks. Load and store instructions are used to provide memory access, and arithmetic logic unit (ALU) operations. Arithmetic operations perform mathematical functions on data. Type conversion operations are used to convert from one data type to another. Object creation processes are used to create new objects and arrays. Operand stack management processes are used to push and pop data from the stack. Control transfer operations are used to move to locations in the bytecode. Method invocation processes involve jumping to subroutines and carrying out returns. The exception processes involve catching and throwing exceptions. Monitor-based concurrency processes are used for working with threads and multiple processes. The JVM languages include any language that can compile down to Java bytecode. Besides Java, here are a few other high-profile languages which run on the JVM. Jython is an implementation of the Python programming language that can be compiled to Java bytecode. JRuby is an implementation of the Ruby programming language. And Clojure is a dynamic and functional dialect of Lisp which compiles the bytecode and runs in the JVM. The bytecode verifier checks and confirms all bytecode before it's executed on the JVM and performs the following checks. The bytecode is verified to ensure all branches are always jumping to valid memory locations. It ensures data is initialized and that references are always type-safe. It ensures access to package or package private methods and data are strictly controlled. And Java is platform independent and secure due to the JVM. The Java bytecode can be either interpreted or compiled to run natively in just-in-time fashion. Bytecode interpreters can run Java bytecode on any machine that runs an interpreter. The just-in-time or JIT compiler will convert and translate Java bytecode into native machine language as needed when it's run. And that concludes this presentation on the Java virtual machine. In this video, I'll describe the key components of object-oriented programming and how it relates to Java. Java makes use of several object-oriented programming concepts such as encapsulation, abstraction, and polymorphism. Encapsulation refers to classes which set access controls to properties to private, making access only possible through methods. Other classes cannot access the private properties directly, which is why it's also called data hiding. Abstraction refers to class blueprints that cannot be instantiated into objects on their own, but they provide a partial blueprint that allows for consistent implementation of concepts. Java uses the abstract class and interface concepts to achieve this type of partial blueprint. Polymorphism is when a class changes its inherited behavior. This is done through what is called method overriding and method overloading. The outward structure of the inherited behavior, the common blueprints are similar, but the underlying implementation differs. Some of the features of the Java programming language include the following. Java is considered a secure programming language because it does not permit explicit memory pointers and runs inside a virtual machine sandbox. Components such as the class loader, bytecode verifier, and the security manager provide further security features and mechanisms to ensure safe code. Java is considered robust since it provides strong memory management, the absence of memory pointers, and automatic garbage collection and exception handling and type checking mechanisms. Java is considered architecturally neutral since there are no implementation-dependent features such as the size of primitive data types like int, which could be different on different operating system architectures and system hardware. Java inheritance refers to the ability of a class to obtain the properties and behaviors of a parent class. Class inheritance is done through extending an existing class. This allows for new features to be implemented while reusing code that can be more universally described. An interface is a type of class that describes methods that must be interacted with, but the actual implementation is defined by a class that implements the interface. And classes are able to implement more than one interface. However, for direct class inheritance, a class may only extend one other class, known as its base, parent, or superclass, using the extends keyword. Let's talk a little bit more about the terminology of Java classes. A class is a blueprint for an object that describes the common properties and methods. A class can generally be instantiated into an object unless it's an abstract class, in which case it's expected that a non-abstract class that inherits from it will be instantiated into an object. The superclass is what we call the class that is inherited from. It's also called the base or parent class. A subclass is a class that inherits from another class and is also called a child, derived, or extended class. And in Java, when we talk about reusability, it refers to classes being able to make use of the fields and methods they inherit from their superclass. Java abstract classes are similar to a regular type of class, but they can't be instantiated directly. Abstract classes are restricted and can only be inherited from other classes. They cannot be used to create objects. Abstract methods contain a signature of a method such as the name, the return type, and any parameters being passed to the method. Then the code of the abstract method must be written in any class that inherits from the abstract class, unless it's an abstract class itself. Abstract classes can have regular methods that have code, and these methods can be overwritten by the classes that extend it, but it's not required. Java interfaces are similar to abstract classes in that they cannot be used to instantiate or create objects, but they can't contain any code. So interfaces can be thought of as a partial blueprint, a type of blueprint for a class that contain the signature of the method, including the return type, method name, and the name and type of its parameters, but has no code body. Interfaces are completely abstract. Abstract classes can have regular methods, but interfaces cannot. And an interface is meant to be inherited by a class through the implements keyword. And unlike an abstract class, multiple interfaces can be implemented by a class. And that concludes this presentation on Java Object-Oriented Programming. In this video, I'll describe the platform independence of Java and the advantages and drawbacks of this approach. Java is a platform-independent language which allows for programs to be written once and run on multiple operating systems. The platforms are software and hardware systems comprising mainly of the operating system and processor architecture, as well as other onboard devices and systems. Independence means that compiled Java bytecode can run on different combinations of platforms without having to be recompiled. You deploy the same Java code on every platform it runs on without having to change it for each platform. A Java runtime environment, JRE, for each platform runs the Java bytecode through the JVM. Regular programming languages, in terms of platform native executables, are compiled to run directly on operating systems such as Windows, Linux, or BSD. Different versions of the same program have separate platform configurations and are compiled for each platform it runs on. The Java programming language only needs to be compiled once, and the same version of code can be run on multiple platforms. The Java Development Kit, JDK, provides the necessary prerequisites for running Java programs. Some components of the JDK are as follows. The Java Runtime Environment, JRE, contains a standalone the Java Standard Library and a configuration tool. The JavaC compiler is used to compile Java code to platform-neutral bytecode. And the Java Virtual Machine, JVM, contains the class loaders, the bytecode verifiers, the bytecode interpreter, and the just-in-time compiler. So the Java Virtual Machine runs compiled bytecode. The process of running Java code on the JVM is as follows. The Java code is created in a development environment such as IntelliJ or Eclipse, or even just a basic text editor. The Java Development Kit, the JDK, includes the JavaC compiler, which compiles Java code to bytecode. JVMs are developed specifically for the OS they run on, and only run on that OS. So the JVM reads the bytecode files, the class files, and interprets it and runs it on top of an OS, whether it's a JVM running on Windows or Linux or some other operating system. The Java programming language has many features besides portability. Some of the features include the following. Well, in terms of portability, it means that the compiled Java program can run on any operating system with a JVM installed. The compiled program does not depend on any specific operating system or CPU architecture. Java is an object-oriented programming language which supports objects, classes, encapsulation, inheritance, and polymorphism. And Java supports multi-threaded applications, and multiple tasks can be performed in parallel. Some more features are as follows. Java is considered a secure programming language because it does not permit explicit memory pointers and runs inside of the JVM sandbox. Components such as the class loader, bytecode verifier, and the security manager provide further security features and mechanisms to ensure safe code. The Java programming language is easy to learn due to the absence of explicit memory pointers and operator overloading, and also because of automatic garbage collection. The just-in-time compiler, or JIT compiler, ensures that compiled Java programs run quickly and efficiently. Java programming is platform independent due to the bytecode that is generated when Java is compiled. There are, however, limitations to this platform independence. Bytecode is portable and can be run on any operating system that has a JVM installed. If there isn't a JVM installed on the operating system, then the bytecode will not run. Java virtual machines themselves are platform dependent, and every operating system requires a version of the JVM compiled specifically for that operating system and its underlying processor architecture. And that concludes this presentation on Java platform independence. In this video, I'll describe the features of Java that ensure that it's safe, secure, and robust. Java is considered a secure programming language because it doesn't permit explicit memory pointers and runs inside a virtual machine sandbox, providing an extra layer of protection. Components such as the class loader, bytecode verifier, and security manager provide further security features and mechanisms to ensure safe code. The bytecode verifier, provided by the JVM, checks and confirms all bytecode before it's executed on the JVM. And the security manager checks to ensure that code is safe and doesn't try to run outside of the secure JVM sandbox. Java is considered a robust programming language since it provides strong memory management. In managing the stack, which is used to store values and references to objects on the heap. The stack manages the scope of objects which can be accessible from the method level or globally. Every thread in Java creates its own stack, making the stack more secure and free from stack smashing attacks. The heap is used to store actual objects with references to the object being stored in the stack. There is a single heap allocated by the JVM for each Java process. The maximum size of the heap and stack depend on the platform it runs on, so the address space of a 32-bit platform is smaller and different from a 64-bit platform, and the JVM takes this into account. Garbage collection is performed automatically and is managed by the JVM. Garbage collection can also be performed or triggered manually by column system.gc directly. The class loader is used to recognize and load code that compiles with the Java class file format. Some of the key components of the class loader process work as follows. The first action of the loader is to load the appropriate bytecode. Then comes the linking process, where verification is performed to ensure the correctness of the imported types. Preparation is done to set aside memory for class variables and initialize the variables to default values, and resolution is used to convert symbolic references to direct references. And during the initialization phase, the Java code is invoked and class variables are initialized. The Java bytecode verifier checks and confirms all bytecode before it's executed on the JVM and performs the following checks. It ensures all branches are always jumping to valid memory locations in the JVM. It ensures data is initialized and that references are always type safe. And it ensures access to package or package private methods and data are strictly controlled. Applications can be secured using the Java Security Manager in a process called sandboxing. Permission represents the access to a system resource and must be explicitly granted. Java provides predefined permissions such as file permissions and custom permissions can be created as well. Policies are used to grant permissions and is responsible to determine if the code can perform a secure operation. Code is not granted any permissions by default. Signed code ensures the authenticity of the application and helps to reassure the users that the application is legitimate. Signatures can be tested within the policies. And privileged code operates at a higher trust level and has permission to access resources that the code that called it may not have. And that concludes this presentation on Java security and robustness. In this video, I'll describe the neutral architecture of Java and the benefits that this provides. Architecture neutrality means that software can be written once and deployed on any target platform. Java is an architecture-neutral language because of the following features. The Java Development Kit. It provides the necessary prerequisites for running Java programs. Java is compiled into bytecode, which runs on a Java virtual machine, which then compiles the bytecode to run on the local machine, which allows for code portability. JVMs can run on multiple operating systems and their computing environments, which allows Java to be platform independent. The Java Development Kit, or JDK, provides the necessary prerequisites for running Java programs. Some components of the JDK are as follows. The JRE, or Java Runtime Environment, contains a standalone JVM, the Java Standard Library, and a configuration tool. The Java-C compiler is used to compile Java code to platform-neutral bytecode. And the JVM, or Java Virtual Machine, contains the class loaders, the bytecode verifiers, and the bytecode interpreter, and a just-in-time compiler. Java bytecode is an abstract machine language that runs on the JVM. The code is compiled to Java bytecode using Java files, which are the plain text source code. The compiled files are class files, so this is compiled bytecode, and the JVM is the abstract computing machine that translates Java bytecode into the host platform's language. You can think of bytecode as a machine instruction not tied to any one processor architecture, but can be easily translated to run on different operating systems and processors, such as using Windows or Linux, and processor instructions for architectures from Intel, ARM, MIPS, Spark, Power, and other CPUs. The Java virtual machine runs compiled bytecode. The process of running Java code on the JVM is as follows. Java code is created in a development environment such as IntelliJ or Eclipse or some text editor. The JDK includes the Javac compiler, which compiles Java code to bytecode, and JVMs are deployed specifically for the OS they run on and run only on that OS. And the JVM reads the bytecode files, interprets it, and runs it on top of the OS and CPU that the JVM was designed for. Java and other languages that compile to Java bytecode are able to run on the Java virtual machine. The JVM is available for multiple operating systems, allowing Java to run on an OS. The JVM contains several key components. There's the class loader that needs to recognize and load code that compiles with the Java class file format. The virtual machine architecture operates on basic values such as integers, floating point numbers, and contains a garbage collector to manage heap memory. Java bytecode is an abstract machine language that runs on the JVM. Java bytecode gets translated by the JVM into machine instructions for the platform it runs on. Java and other languages that compile to Java bytecode are able to run on the JVM. The JVM languages include any language that can compile to Java bytecode. A bytecode verifier checks and confirms all bytecode before it's executed on the JVM, and bytecode interpreters can run Java bytecode on any machine that the interpreter runs on, that the JRE and JVM runs on. The just-in-time compiler will convert and translate Java bytecode into native machine language. And that concludes this presentation on Java architecture neutrality. In this video, I'll describe the features of Java that allow it to be portable. Java can be created on and executed on any device or operating system or platform that contains a Java virtual machine. Java is a portable programming language that you can write once and run anywhere. And that's how Java's been promoted since it was created in the 1990s. The Java compiler, Javac, is used to compile Java code to platform-neutral bytecode. Bytecode are platform-independent machine instructions that aren't tied to any one processor architecture, but they're executable by the Java runtime environment, JRE, which contains a standalone JVM, the standard Java library, and a configuration tool, which are the key components for allowing portability of the Java bytecode. Java provides 3 different types of portability, including the following. Source code portability, which ensures the Java program generates bytecode that executes and provides identical results on any operating system that the bytecode is run on. The Java virtual machines allow CPU architecture portability by running Java bytecode on any CPU that has a JRE interpreter. And user interface portability is achieved with Java providing a set of UI libraries to create virtual user interfaces that run on a variety of desktop environments. Java code should generate the same results on any operating system that it runs on. This is known as source code portability. During the compilation phase, the Java source code is compiled into Java bytecode. This is an intermediary language that is similar to assembly language, but as a generic, easily translatable assembly language that targets the JVM. The bytecode is not compiled to run on any specific operating system or processor architecture. Instead, it runs inside a Java virtual machine. During the interpretation phase, the class loader will read bytecode files, which can be run on an interpreter or just-in-time compiler. Java is a portable language which allows for programs to be written once and run on multiple operating systems. The platform is the environment where the software is executed. Java provides a JRE, where compiled Java programs can be run. Portability means that the compiled Java program can run on multiple architectures using the JVM. And Java programs allow for the creation of user interfaces to interact with users of the system. So it's not limited to command line or server programs, but each operating system has their own unique libraries and code for displaying user interfaces, some with multiple different desktop environment possibilities, such as in Linux. So Java code is written using a Java library such as AWT or AUT, util, and lang to generate user interfaces that will run on any operating system via the JVM. The Java libraries operate by writing to the JVM, which maps the generic library calls to the underlying desktop and GUI functionality particular to the operating system it's running on. The Java libraries are written to allow functionality that is common across all operating systems. This allows the user interface and other code to be portable. The only drawback is that functionality unique to an operating system or desktop environment cannot be taken advantage of, and Java relies only on the common functionality across operating systems. But this allows it to be truly platform independent. And that concludes this presentation on Java portability. In this video, I'll describe the features of Java that allow it to run quicker than traditional interpreted programming languages, such as common scripting or shell languages. The Java Virtual Machine, JVM, has several features that contribute to the performance of the compiled Java program. Some of the optimization features are as follows. The just-in-time compilation. The original JVMs would interpret Java bytecode, which added to the execution time. JIT compiling was introduced to increase the speed and optimize code that is frequently run. Adaptive optimization performs dynamic recompilation for parts of the program after analyzing the current execution profile. The adaptive optimizer can make trade-offs between interpreting and performing JIT compilation of the Java bytecode. The JVM performs garbage collection using a generational collector that divides objects into generations based on when they were created, which allows for a better defragmentation model. The JVM also has other features that allow it to execute quickly. Compressed ordinary object pointers allow Java to use 32-bit references to address up to 32 gigabytes of heap space, which allows for more efficient memory management. Split bytecode verification performs part of the verification when the class is compiled to bytecode by annotating the compiled bytecode. During runtime, bytecode verification can be performed quicker by using the annotations. Escape analysis and lock coarsening means that when a section of code or an object is requested to be locked, it is only locked when necessary. And some more features that allow Java to execute quickly is the improved allocation of registers, which did not live across blocks in the client virtual machines initially. Register allocation improvements allow registers to exist for multiple blocks, which reduces access to the memory. Class data sharing reduces startup times for Java applications and reduces memory consumption by using a shared archive of preloaded class libraries. When optimizing and tuning Java applications, there are some main techniques that can be applied to the code itself. Some of the techniques are as follows. Storing and working with data in memory is much faster and more efficient than using disk storage. Cache files and data in memory is used where possible. Reading and writing data sequentially is faster than working with memory and disk storage. Try to perform sequential data access whenever possible instead of random access. Creating and destroying object is resource intensive. Create objects only when necessary and reuse objects whenever possible. Using the precise data formats and data structures helps increase the speed of the application. Don't grossly overallocate space for arrays and strings as a premature optimization. Only allocate the space you need and increase it as necessary. When optimizing and tuning Java applications, there are a few more techniques that can be applied, such as asynchronous I/O, which allow other processes to continue running while the I/O process itself continues to run. This also scales better than synchronous I/O processes, which require blocking. Single-thread performance should be optimized before multi-threaded processes can be expected to also perform efficiently. And be careful using shared memory or shared disk storage across threads. This can be bad because multiple processes are fighting for the same resources, which leads to poor performance for all. When you're trying to synchronize shared memory across multiple threads, you'll have many threads waiting for whoever has access to the data to finish before you can get access to it yourself from a different thread. You want to minimize the amount of time that threads are waiting for each other. And that concludes this presentation on Java performance. In this video, I'll describe the features of Java that allow applications to be distributed. Distributed applications consist of multiple clients that connect to multiple backend services over a network or the internet. Java can be written using many architectural models for creating distributed applications. The client-server architecture involves a front-end client system that makes requests to backend services over a network. The broker pattern architecture is a system that uses decoupled components that interact using remote service calls. The broker facilitates all communication between the decoupled components and redirects tasks to the correct component. The Common Object Request Broker Architecture, or CORBA, is a standard method on implementing the broker pattern. Service-oriented architecture is a design method which allows applications to use available services on a network. The application can be divided into a client tier, web tier, business tier, and enterprise information system tier. One method for creating distributed applications is to use the client-server architecture. This architecture consists of a client application and a server backend. The client-server architecture involves a front-end client system that makes requests to backend services. The client initiates all requests with the backend and is independent of other client applications. The backend system exists independently of the client application. It receives the request to perform tasks and returns the results back to the application that made the request. The backend system can scale by adding additional services and routing client requests to these additional services so that the load can be balanced. The broker pattern architecture is a system that uses decoupled components that interact using remote service calls. CORBA contains the following components. The Object Request Broker is the middleware that manages requests between applications and services. Application interfaces are developed for a specific application and can be developed as required for the application. Domain interfaces define interfaces for specific domains such as manufacturing, telecommunication, medical, and financial. They provide a similar function as common facilities interfaces are horizontally oriented towards end-user applications. For example, the Distributed Document Component Facility, DDCF, is based on the OpenDoc standard and can be used to link together documents. And Object Services interfaces are not for any specific domain and can be used by many distributed object programs. A discovery service can help applications find the service that they require. Examples of this are the naming service, which finds objects based on their name, and the trading service that finds objects based on their properties. Java applications can be divided into the following application tiers based on a service-oriented architecture, an SOA architecture. The client tier components run locally on the client machine. The web tier components run in the backend of the Java server. The business tier components also run in the backend of the Java server. And the enterprise information systems EIS tier services run on the dedicated EIS server. Some of the benefits of using a distributed application architecture are as follows. Some resources can be very costly to run, so you may only have one such resource running. This could be some complex algorithm or service. Using a distributed architecture permits applications to share this resource. Openness involves making a service available to any users that want to be able to consume it. Concurrency is the ability of sections of the program to run in any order without affecting the outcome of the application. Using a distributed architecture permits concurrency. Distributed services can be scaled by creating and running additional virtual machines that provide a service on demand when need of that service increases. Distributed services are fault tolerant because if a service fails, the request can be redirected to the same service running on a different server or virtual machine. There are several tools that are available to help create distributed applications. Some of the available tools are as follows. Docker, which is used for containerization and is used for creating and scaling backend services and microservices. Kubernetes is used for container orchestration and is useful for automating deployments, scaling, and managing containerized applications. JRebel is used to skip redeployments when developing services in Java. This is a useful time-saving tool. And Xrebel is used to monitor and track requests in real time as they move through a distributed system. And this tool is very useful for debugging. And that concludes this presentation on Java distributed applications. In this video, I'll describe the multi-threading features of Java. Multi-threading in Java allows multiple processes to run concurrently within the application. There are two mechanisms in Java for creating threads. A custom class can be created by extending the java.lang.thread class, which overrides the run method. The custom class is instantiated, and the start method will invoke the run method for the class. A custom class can also implement the java.lang.runnable interface and override its run method. This custom class is once again instantiated, its start method invoked, and the run method called. When a thread is created, it follows a number of stages in its lifecycle. The thread can be in one of the following states. Threads start in the new state until the thread is started by the program. Then the start method is called once the thread becomes runnable. The run method is called from the start method, and the state of the thread is running. Threads may transition to the waiting state while the thread waits for another thread to perform a task. The thread will move back to the running state once the other thread tells it to. And the thread can also be in a time to wait state. The thread will move back to the running state when the time expires. A thread enters the terminated or dead state when a task it is performing is complete or it terminates. The thread class contains several important methods which need to be understood. The important methods are as follows. The start method is used to start the execution of the thread class. The run method is used if the thread object was instantiated using a runnable target. The setName method changes the name of the thread object, and the getName method retrieves the name of it. The setPriority can change the priority level of the thread from a range from 1 to 10. The thread class contains several important methods which need to be understood. The setDaemon method can be used to designate the thread as a daemon thread. The join method is called to synchronize threads so that two threads can terminate at the same time or until a specified time passes. The interrupt method is used to continue executing if a thread was blocked. And the isAlive method returns the value true if the thread is active or alive. The thread class contains several important static methods which need to be understood and are as follows. The yield method causes a thread to yield to another thread with the same priority level. The sleep method causes a thread to lock for a number of milliseconds specified in the parameter value. The holds lock method returns a value of true if the current thread has a lock on a given object. The current thread method returns a reference to the currently running thread. And dump stack returns the stack trace of the thread that is currently running. And that concludes this presentation on Java multithreading. In this video, I'll describe the dynamic features of Java, such as static class loading and dynamic class loading. So class loaders are used to recognize and load code that compiles with the Java class file format. Static class loading is performed when a class is instantiated with a new operator and the object is instantiated at compile time. Dynamic loading involves invoking the functionality of a class loader at runtime. This is done when the class name is unknown at compile time. Some of the key components of the class loader include the following. The first action of the loader is to find and import the binary data for a type. Then during the linking process, verification, preparation, and resolution occur. The initialization phase comes next, and this is where the code is invoked and class variables are initialized. The class loaders get arranged in a hierarchy, and creating a new class loader requires using the parent class loader. So the class loader will request that its parent attempt to load a class first. There are several steps that are followed when loading a class. The first step is to check that the class is already loaded. If the class is not loaded, then the parent class loader is asked to load the class. If the parent class loader is unable to load the class, then the current class attempts to load the requested class dynamically. One of the key steps of the class loader is linking of the class. The steps performed during the linking are as follows. Verification, which is performed to ensure the correctness of the imported type. Preparation is done to set aside memory for class variables and initialize the variables to their initial values. And resolution is used to convert symbolic references to direct references. Loading a class dynamically is done by using the class loader class. In this example code, there is a sample class, myClass, which will be loaded dynamically. The sample class will be used to dynamically load the myClass. The class loader is loading using the getClassLoader method, and then on line 11, the myClass is dynamically loaded using the name of the class. So class myClass equals myClassLoader.loadClass, and in quotations, myClass. And then on line 12, system.out.println has the string myClass.getName equals plus myClass.getName. And it will return the name of the dynamically loaded class, if the class is loaded correctly. And when loading classes dynamically like this, it's important to catch any class not found exceptions and handle it appropriately. And that concludes this presentation on Java dynamic loading. In this video, I'll describe some examples of real-world Java applications. Java can be used to create many types of applications. Some of the application types are as follows. Desktop applications can be created using Auth, the Swing API, the Java Foundation classes or JavaFX, and real-world desktop applications include Adobe's Acrobat Reader. Web applications can be written in Java using servlets, struts, Spring, Hibernate, or JSPs. Real-world examples of Java web applications include Amazon and Wayfair. Mobile applications can be developed using a cross-platform framework called J2ME. Real-world mobile applications written in Java include Netflix, Google Earth, and Uber. Java can be used to create many types of applications. Some of the application types are as follows. Enterprise applications can be created using the Java Enterprise Edition, Java EE, that has an API and runtime environment for running scripts, enterprise software, network tools, and web services. Real-world applications include enterprise resource planning, ERP systems, and customer resource management, CRM systems. Java provides powerful math libraries for creating scientific applications that generate the same results on multiple platforms. Real-world examples of scientific tools include MATLAB. There are numerous web and application servers available, including Apache Tomcat, WebSphere, JBoss, and WebLogic. Some more application types that can be created with Java are as follows. Embedded systems, which are applications that are part of low-level systems and can be created using Java. Real-world examples include SIM cars and Blu-ray disc players. Financial institutions, such as banks and investment firms, used server applications to transfer financial information and transactional data. Many software tools are created with Java, such as Eclipse and IntelliJ IDEA. Java has several popular frameworks that can be used to develop applications. Some of the more popular ones are as follows. Java Server Faces JSF is used for web application development and uses a Model View Controller or MVC model for its architecture. Scaffolding is available to limit the amount of code that needs to be written. Blade is a tiny MVC framework created with the goals to be self-contained, productive, elegant, and fast. Struts is an open-source, Apache-based enterprise-level framework based on the MVC model that requires reduced development time to create applications. And the Google Web Toolkit GWT is an open-source and cross-compatible framework that allows developers to maintain JavaScript front-end applications in Java. Some more popular frameworks are as follows. Grails is an open-source framework that uses the Apache Groovy programming language and is built on top of the Java platform and can be integrated with Java libraries. Spring is an application framework and an inversion of control container for the Java platform and usually uses the Enterprise Java Bean model. Hibernate is an object relational mapping or an ORM or ORM tool, providing a framework for mapping an object-oriented domain model to a relational database. And the Play framework is an application framework that uses the MVC pattern and is written in Scala and compiles to Java bytecode. And that concludes this presentation on Java real-world applications. So in this Java introduction course, we've examined the main features of the Java programming language. We did this by exploring the Java Virtual Machine, JVM, key components of object-oriented programming, Java platform independence, security robustness, and architecture neutrality, and Java portability and performance. In our next course, we'll move on to examine the features of the Java Development Kit, JDK, and the Java Runtime Environment, JRE. In this video, I'll present the features and components of the Java Development Kit. The Java Development Kit, JDK, provides the tools to create Java programs. The JDK comprises the Java Runtime Environment, JRE, a standalone JVM containing the Java Standard Library and a configuration tool, the Java C compiler, used to compile Java code to platform-neutral JVM bytecode, and the Java Virtual Machine, JVM, containing the class loaders, the bytecode verifier, interpreter, and the just-in-time compiler. Java is platform independent and secure due to the JVM. The Java bytecode can be either interpreted or compiled to run natively. Bytecode interpreters will run Java bytecode on any machine that contains the interpreter. JVM's just-in-time compiler converts Java bytecode into native machine language. The JVM contains several key components. The class loader, which recognizes and loads code compiled into the Java class file format. The virtual machine architecture operates on basic values such as integers and floating point numbers and contains a garbage collector to manage heap memory. Java bytecode is an abstract machine language that runs on the JVM, and Java code is compiled into Java bytecode. JVM languages include any language that can compile to Java bytecode, such as Clojure and Scala. The bytecode verifier checks and confirms all bytecode before it's executed on the JVM. Bytecode interpreters can run Java bytecode on any machine that contains an interpreter, and the just-in-time compiler will convert and translate Java bytecode into native machine language. Java is platform independent due to the bytecode that's generated when Java is compiled. There are, however, limitations to this platform independence. Bytecode is portable and can run on any operating system that has a Java virtual machine installed. If there isn't a JVM installed on the OS, or the OS doesn't support one, or the processor architecture isn't supported, then the bytecode can't run. The Java virtual machine itself is platform dependent. To run Java bytecode, a version of the JVM must be built for the target system. The Java Development Kit, JDK, contains several tools and components for developing Java applications. The Java Disassembler tool, used to convert compiled class files back into human-readable code. The Java Head File Generator tool is used to generate C headers and source files which are used to call native methods from Java. And the Java Debugger tool helps the developer determine the cause of a bug in an application. The built-in debugger, JDB, can be used to debug classes at the command line. The JDK contains documentation and tools for working with Java applets. Java documentation is used to document and maintain code. The JDK provides a tool called Javadoc that can be used to generate documentation for the public classes, private classes, nested classes, interfaces, constructors, methods, and fields. And the Java Applet Viewer is a tool that can be used to view and test Java applets. Applets are small Java programs that are run inside a web browser through a Java plugin. And that concludes this presentation on the Java Development Kit. In this video, I'll present the features and components of the Java runtime environment, as well as its development components. Java runtime environment consists of components that can be used to execute Java programs. The JVM contains several key components. The Java class libraries, consisting of standard libraries such as java.lang and the java.util that are essential. The class loader is used to recognize and load code that compiles with the Java class file format. So the Java Virtual Machine, JVM, is built from several key components. Class loader, which recognizes and loads Java class files. The virtual machine architecture operates on basic values, such as integers and floating point numbers, and contains a garbage collector to manage heap memory. Java bytecode is a machine code targeted not to specific processor architectures, but to Java's virtual machine, the JVM. Java source files are compiled to Java bytecode using the class file container format. And Java bytecode interpreters can run Java bytecode on any machine that runs the interpreter. The just-in-time compiler, meaning it's compiled on the fly when it's loaded and not pre-compiled, will convert and translate Java bytecode into native machine language to run on its target platform. The class loader verifies and loads code in the Java class file format. The key steps that the class loader carries out are loading, which is what you'd expect. The loader finds and imports the binary data for a type. During the linking process, verification, preparation, and resolution are performed. This is done to ensure correctness, allocate memory, initialize default values, and convert symbolic references to direct references. Then the initialization phase invokes the Java code and class variables are initialized. The Java Standard Library and a configuration tool. Development toolkits provide libraries to create user interfaces and include the Java 2D library, the Abstract Window Toolkit, AWT or AUT, and the Swing library. Integration libraries are used to connect to different data sources, including Java IDL, Corba, the Java Database Connectivity API, JDBC, and the Java Naming and Directory Interface, JNDI. Java class libraries consists of libraries such as java.lang and java.util that provide a base-level functionality for Java applications. Development toolkits provide libraries to create user interfaces such as Java's 2D library, Swing, and AUT, where the Java 2D library is used for drawing two-dimensional graphics and can be used for creating games and rich UI interfaces. The Abstract Window Toolkit, AUT, is used to create user interfaces using controls such as windows, buttons, and form controls. And the Swing framework is used to create user interfaces and has a diverse set of custom widgets. Integration libraries are used to connect to different data sources and include the Java IDL, Corba, JDBC, and JNDI. The Java Interface Definition Language is an implementation of the Common Object Request Broker Architecture Corba specification. Corba is a standard method for connecting and interacting with decoupled components that use remote service calls. The Java Database Connectivity API, JDBC, provides an interface for connecting to and working with databases. And the Java Naming and Directory Interface is an API for directory services and makes use of the Lightweight Directory Access Protocol, or LDAP. What are some built-in packages or common features that we use or import into our applications? The Java Applet package contains classes for creating applets. Java Auth contains classes for creating graphical user interfaces with menus and buttons. Java I/O contains classes for supporting input-output operations, such as printing to the screen, a printer, or a file storage system. And Java.lang contains classes that support the Java language, such as primitive data type wrappers, string and string builder classes, and the math and system classes. Java.math package contains methods for arbitrary position, floating point, and integer arithmetic. And Java.net contains classes for network operations and communications. And Java.util contains classes for containers and collections like linked lists, dictionaries, date and time operations, and other helper classes. And that concludes this presentation on the Java runtime environment. In this video, I'll describe the features and components of the Java compiler and interpreter. Java's tagline, write once, run anywhere, concisely captures the goal of Java. Java source code is compiled into bytecode that can be executed on any device or operating system that contains a Java virtual machine. There's no need to change the source code, nor put in special preprocessor statements to handle different architectures. Java doesn't need to be written differently for different operating systems. You write it the same for everywhere. The Java-C compiler compiles the Java code into platform-neutral bytecode, and the Java runtime environment JRE contains a standalone JVM, Java standard library, and a configuration tool to run the portable code. Java bytecode is an abstract machine language that runs on the JVM. Java code is compiled into Java bytecode. Java files contain the Java source code for the Java application. The class files contain the compiled bytecode, which is then just-in-time compiled by the JVM to run on the target platform's architecture. The class files are what gets deployed. It's not a scripting language. You don't deploy the code itself. You don't deploy the Java files, just the class files. Java code should generate the same results on any operating system that it's run on. This is known as source code portability. During the compilation phase, the Java source code is compiled into bytecode. This is an intermediary language that's similar to assembly language, and during the interpretation phase, the crossloader will read the bytecode files, which then can be run through an interpreter or just-in-time compiler to translate it into actual machine language. The bytecode verifier checks and confirms all bytecode before it's executed on the JVM and performs the following checks. The bytecode is verified to ensure all branches are always jumping to valid memory locations. It ensures data is initialized and that references are always type safe. And it ensures access to package or package private methods and data are strictly controlled. Java is considered a secure programming language because it does not permit explicit memory pointers and runs inside of the virtual machine sandbox. Components such as the class loader recognizes and loads code that compiles with the Java class file format. The bytecode verifier checks and confirms all bytecode before it's executed on the JVM, and its security manager provides further security features and mechanisms to ensure safe code. And that concludes this presentation on the Java compiler and interpreter. In this video, I'll describe the features and components of the Java interpreter. Some tools can be used to understand the inner workings of a compiled Java application and debug a Java application. First is the Java disassembler. These tools are used to convert compiled class files into human-readable code. A decompiler can be used to convert the compiled class file back into Java source code. The Java debugger helps the developer determine the cause of a bug in an application. The built-in debugger, JDB, can be used to debug classes at the command line, as well as other debuggers that are implemented for Java. There are several options for decompiling Java class files back into Java source code. Some of the options are as follows. Command line tools were the original method for decompiling class files. Java bytecode can also be decompiled on remote servers. The IntelliJ IDEA development platform uses the Fernflower decompiler as the default tool, and Eclipse uses a plugin called the Enhanced Class Decompiler, or ECD, which provides 5 separate compilers to the developer. Java debugger tools help the developer determine the cause of a bug in an application. IDEs, or integrated development environments such as IntelliJ, Eclipse, and NetBeans, have built-in debugging tools that can be used to isolate issues with Java applications. Standalone debuggers such as JIKES, Java Platform Debugger, and JProbe are tools used specifically for debugging Java applications, and the built-in debugger JDB can be used to debug classes at the command line. The Java debugger JDB is a part of the JDK and can be used for debugging Java applications. The 3 components of the JDB are as follows. The Java Virtual Machine Tool Interface, or JVM-TI, is implemented by the JVM and provides a method to inspect and debug the state of a running Java application. The Java Debug Wiring Protocol, or JDWP, provides a format for sending debug requests to the JVM tool interface. And the Debugger Interface, or JDI, is a high-level interface for connecting to the virtual machine for debugging purposes. The JDB, or Java Debugger tool, can be used to debug Java code from the command line or be used as an interactive tool. From the command line, the JDB can be used to attach to a running virtual machine or run the application on a Java hotspot client or server. The Java debugger can be run interactively using sessions. Commands can be issued inside the session to debug a running Java application, and breakpoints can be set within a Java program and can specify a class name, a line number, or a specific method or variable name. During the debugging of a Java program, the code can be stepped over line by line using the step command to step to the next line of code, but step over function calls without going into them, the list command to display the current line of code, and the cont command to continue running the application, as well as printing the contents of any variable in the current scope. And that concludes this presentation on the Java interpreter. In this video, I'll present the features and components of the Java documentation tools. Java documentation helps new and existing developers understand the available classes and methods that exist in a Java application. This documentation can also be used by non-technical staff as well to understand the Java application. The JDK provides a tool called Javadoc that can be used to generate documentation for the public classes, private classes, nested classes, interfaces, constructors, methods, and fields. Special tags can be added to comment statements that are read by the Javadoc tool and included in the generated documentation. Javadoc can be run on single source files or on entire Java packages. Javadoc comments add special symbols to the comments blocks that can be processed by the Javadoc tool and used to generate HTML documentation. There are several Javadoc tags that can be added to the comment blocks. The main ones demonstrated here are the author, used to add the name of the author of the code, the version, used to add the version of the code, @since, specifies which version of the code you added to this method or class, @deprecated can be added to indicate this class or method should no longer be used, @return adds a return section with a description describing the return value of the method, and docroot adds the relative path to the generated document's root directory. Some more of the special tags that are added are the @author, used to specify the name of the author or authors of the code, @docroot, surrounded in braces, represents the relative path to the document's root directory, @version specifies the version of the software, and there can only be one version declaration per class or interface, and the @since tag indicates the initial availability of this functionality. The @c tag references other elements, so it's a reference tag. @param is used to describe a parameter of a method. @return is used to document the return value. @deprecated is used to describe a method that is no longer used or should no longer be used or will go out of use or be removed in the future. @exception describes the exception type that the method may throw. @throws is also used to describe an exception that a method may throw. @inheritDoc tag uses or inherits the description of a method being overridden, so you can inherit documents from a parent class. And @value is used to indicate the value of a static field. The @link tag or reference is used to add an inline link that provides a link to the documentation for a package class or member name. @link plain provides the same functionality as the @link tag, except the label uses plain text. @code is used for formatting a block of text using the code font, so it's a code literal. And the @literal tag is used to indicate text that's not HTML markup or nested tags, and the text should be interpreted literally. And some more Javadoc tags are the @serial tag used to indicate the default serializable field, @serial data used to indicate the data written to the right external or right object methods, and @serial field literal is used to document the object stream field component. Now, not all of the tags here are required. It's a lot to take in all at once, but these are some of the Javadoc essential capabilities to comprehensively document your source code. And that concludes this presentation on Java Documentation Tool. In this video, I'll present the features and components of the Java archive. The Java archive file is a collection of files that may or may not be compressed and ends with the .jar file extension. It contains a manifest file, a manifest.mf, and is located in the meta-inf directory. This file contains a list of key value pairs that are grouped into sections. The key value pairs consist of headers and attributes. jar can also use the zip format to compress the Java archive file and decrease the size of the file to make it easier to transmit and deploy. Using Java archive files provides the following benefits. Jar files can be digitally signed, which will allow the people that use the package to verify the authenticity of the package before granting the package security privileges. Jar files can be compressed to take up less space and faster download times. Jar files can contain versioning and vendor information regarding the files contained in the package, and jar files are portable and can be used by any Java runtime environment. The manifest file contains metadata for the package. It's always called manifest.mf and is located in the meta-inf directory. It contains a list of key value pairs grouped into sections consisting of headers and attributes, and it's created automatically when a jar file is created. And it's also possible to create a custom manifest file that is used instead when creating the jar file. The manifest file has some common headers to provide general information. The manifest-version tag is used to indicate the version of the manifest file specification. The multi-release tag indicates that the package can be run on multiple releases of Java if the value is set to true. The created-by tag can be used to describe the version of the tool and information on the vendor that created the manifest file. The build-by tag is a custom header providing the name of the user that created the manifest file. Packages can be sealed, which increases the security of the package. Classes can only be loaded into the same package if they're signed by the same entities. Sealing a package prevents malicious code from being added to the package that would then have access to package-protected classes and methods. Packages need to be named in order to be made sealable. Unnamed packages are not sealable. So this provides a layer of verification and authenticity when dealing with code. And that concludes this presentation on the Java archive. In this video, I'll demonstrate how to download and install the Java Development Toolkit. This series has been built for JDK 1.8 compatibility. Ever since being released in 2014, Java version 1.8, or sometimes called Java SE 8, is still the baseline version today. It's actively supported with updates and security fixes and backwards compatible with newer versions. So if you've come to this course with a later version, that's okay too. It will still work because of this backwards compatibility. So I have my web browser open to openjdk.java.net. So this is the open source implementation of the Java Platform Standard Edition. I'm going to browse to the download and install section and look for the version I want to install, in this case JDK 8. I'm running on an Ubuntu system, and the instructions for the Debian or Ubuntu or any of the variants is to use apt-get. So I'll have to type sudo apt-get install openjdk-8- and in this case I want -jdk for the Java Development Kit. So I'll switch over to my terminal window, run sudo apt-get install openjdk-8-jdk. After the install completes, I like to verify that the correct version is installed when I run javac. So javac, short for Java compile, -version. And it shows me I have 1.8.0_275 installed. And I'll type ls in my current folder under documents Java -02-11. I have a file called hello-world.java. So this is a simple hello world Java example source. I'm not going to get into the source code. You can probably guess what it's going to do. But what I'd like to do is type javac hello-world.java to make sure it compiles correctly. And there's no messages, so it does. And if I type ls, I see the compiled hello-world.class contained in the folder. And now we're ready to start compiling Java code into class files. And I'll get into the code details throughout this course. And that concludes this demonstration of Java Development Toolkit installation. In this video, I'll demonstrate how to download and install the Java Runtime Environment, the JRE. On systems we deploy our Java class files to, or the Java archive files to, we don't need the Java Development Kit, the JDK. It's not needed to run the program. Only the runtime environment is needed, the JRE. After Java code has been compiled using the JDK, it can be distributed anywhere the runtime environment exists. We get the runtime environment from the same place we get the development kit from the openjdk.java.net website. So the instructions are here in the install page, select install, and it shows how to download and install pre-built OpenJDK packages, which can either be the JRE or the JDK. And in this case, I'm looking at the JRE for JDK version 8. Since I'm running Ubuntu, I want to use the command line that's specified here. So it's sudo apt-get install openjdk-8-JRE. So I'll copy it. I'll switch over to my terminal window and paste in the command. So in this case, it tells me openjdk-8-JRE is already the newest version. When you install the JDK, it automatically installs the JRE. But if you install the JRE, it doesn't install the JDK. I can check the version I'm running by typing Java. So running the Java program itself is running the JRE. So Java-version gives me the runtime environment version, and it's showing that it's 1.8.0_275. So it's running the latest 1.8 version. To run a program using the JRE, I can type Java and then the name of the class. In my current folder, I have a class file called hello-world.class. So to run it, I just run Java hello world, and it prints the result hello world. So if I look in my current folder with ls, there's a hello-world.java and a hello-world.class. So running Java hello world will look for the corresponding class file, in this case the hello-world.class. I don't need to run Java hello-world.class, so I don't specify the extension to the file itself, and I can't run Java hello-world.java. It doesn't make sense, because the Java extension specifies a source file that needs to be compiled. So your development machines need both the JDK and the JRE, but the systems that run the compiled Java code, compiled into the class files or archive files, only need the JRE. And that concludes this demonstration of Java Runtime Environment installation. In this video, I'll demonstrate how to download, install, and configure the IntelliJ IDEA development tools for Java. This is the IDE that I'll be using to carry out Java demonstrations throughout this course. It is by no means required. Other IDEs, even text editors, and running the Java tools from the command line also work. There are no shortage of development approaches, but in the end, Java code is still Java code, and the code you write in one environment will work fine in another. I have my web browser open to the jetbrains.com website. I'm going to select the Developer Tools option and select IntelliJ IDEA from the menu. Select Download, and although you can install the community version and use for free, it's an open source edition, I do recommend at least trying the free 30-day trial of the Ultimate Edition, which I've done here. So it's going to ask me to save the download, but I've already downloaded and saved this file. So I'll switch over to my terminal window, and I'm already in my downloads folder. I'm going to run tar-x for extract, z for zipped, and f for force of idea iu-2020.3.tar.gz. And then I can look in the folder idea-iu203.5981.155, and I see all the files are here. Now, I don't want to install it here. I want to put it into its final location, which I'm going to put in my home folder. So I'll type mv for move, idea-iu, and I just hit tab to complete the path. And I'm going to move this to /idea-iu. And now I'll cd /idea-iu. I'll type ls, and I have all the files here. Where I'd like to start is in the bin folder. So I'll cd into bin, ls, and I see all of the programs and scripts that are available in my IntelliJ install. The important one is idea.sh, and this will launch IntelliJ. But I don't want to just come to the command line and type it every time, so I'm going to create a shortcut for it in my panel. Now, depending on the operating system or flavor of Linux or desktop environment, adding this shortcut may be a little bit different. In general, the same process applies everywhere. So I'm going to create an application launcher, press add. The name of the application is going to be IntelliJ. The command, I'm going to select browse, go into my home folder, idea-iu, bin, and I'm going to select idea.sh. And there's also an icon here I can select. I'm going to select that. I'll go back into my home folder, idea-iu, bin, and I'm going to select the idea.svg to represent it as an icon. And now I can hit OK. I'll close the tool to add to the panel. Now I'll go up. It auto hides the top panel, but here I have the IJ icon for IntelliJ, and I can just click it, and it will launch IntelliJ for me. So I've run it for the first time. It asks me to accept the user agreement, which I will. And I can put in my IntelliJ license if I've purchased one, or I can select evaluate for free. Evaluation is free for 30 days, and I'll just click evaluate. And now I'm at a welcome screen where I can select a project. I can create a new project. I can perform some customizations. I can change the IDE font and the editor sizes. I like to boost it up a little bit for visibility. So I've set the IDE font to 16 and the editor font to 14. There's also plugins I can select and the Learn IntelliJ IDEA. So I'll go back to projects and select a new project. And it gives me some options on what I'd like to use for this project. I can select a Java project, and I can add libraries and frameworks for Groovy, Kotlin, and SQL support. There's also projects for Maven, Gradle, JavaFX, Android, and the IntelliJ platform plugin. So there's a number of options I can select. I'm going to leave it at Java. The important part here is selecting the Java versions. So it's selected 1.8 Java, which I have installed, but I can also select to download a JDK or add a different JDK instead of using the one that's detected locally. I could select download JDK and download a different JRE and JDK if I need a different option. So there's Java versions all the way from 1.8 to 15. The different vendors of JDKs. So there's the Open JDK from Oracle and some other ones that are hosted or distributed by third parties. Now I'm going to hit cancel. I'm going to leave it at 1.8, select next, and I can select to create a project from a template if I want to create a command line app, and select next. And I can call this project name. I'll just call it first project. I can have a base package, and com.example is perfectly valid. And now I'm ready to get started with IntelliJ and building my first application. And that concludes this demonstration of installing IntelliJ IDEA development tools for Java. In this video, I'll demonstrate how to compile and execute a simple Java application from the command line. So I'm in this folder, IDEA project/Javadoc demo. I'm going to cover the details of the source files in this demo in the video titled Javadoc later in this course. I'll type ls to see what's in this folder. So there's two folders, a source folder, src, and an output folder called out. If I look in source, I'm going to use ls src/com/example. This is where my source files are, greet.java and main.java. The main.java can't be compiled by itself. I can type javac src/com/example main.java. It tells me it can't find the symbol. So greet has to be compiled first, or together with main, and main.java needs to know where it can find the greet class file. So I can type javac src/com/example/greet.java. Now I can compile it on its own. I'll arrow up a couple of times and rerun javac on source example com main.java. And it still can't find the symbol. Why not? Well, it's looking in my current folder and in a class path, and it can't find the class for greet.java. So inside of src/com/example, there's a greet.class. And what I'm going to do is remove it because I don't want it there. I want to put it somewhere separate. So I delete using rm the greet.class from that folder. So where I want to put it is in the out folder. So I'll put it to the output. So I can type javac-d out. So that's the directory or destination folder, src/com/example/greet.java, and src/com/example main.java. So it's going to compile those two files and put the results in out. Now inside of out, where it puts it is in the com folder. So ls out/com/example, we have greet.class and main.class that were just compiled. The production folder is something put there by the IDE when these files were created and has nothing to do with the javac we just compiled now. So what do we do when we want to run it? Well, if I type java com.example.main, it won't be able to find where that main is. I need to specify a class path. So java-class path out. So I only need the top level root directory of where the package begins. So out and then space com.example.main. And it prints hello world. And that's exactly the output of this application. I can also debug it using JDB and the same thing, -class path out com.example.main. So instead of running Java, I can run JDB and it will do the same thing, but it will put me into a JDB, a debugging session, and I can type run and run the code from the debugging session. And it gives me the result, hello world. So whatever IDE you're working in, under the hood, the IDE is building a javac command out of your source files, but you're not completely tied to an IDE, and you can even use a text editor to edit your Java files and compile them from scratch using javac. Although I recommend not typing out the full names every time you want to compile something, but create a shell script or a makefile to do so. And that concludes this demonstration of the Java compiler and interpreter. In this video, I'll demonstrate how to create, compile, and run a simple Java application using IntelliJ. So once I've launched IntelliJ, and if I have no projects open, I'm presented with a dialog that gives me the option to select New Project, or open a recent one or some other one that I can browse for. So I'll select New Project, and there's some options. I can use Groovy or Kotlin with JVM. IntelliJ provides that, but what I'd like to do is select Java. The SDK I want is version 1.8, the one I have installed. And I'm not going to select a library to use. I'm just going to select Next. We can create a project from a template or an empty one. I'm going to create a project from a template and choose command line app, which is the only one I have here at the moment. And I can give the project a name. So I'll call this create, compile, run, demo. I can select a base package for this, and I'll leave this as com.example and select finish. IntelliJ gives me a file, main.java, with the blueprint for an entry point into an application with a class called main and the standard public static void main, string double brackets args, entry point function to our application, where we can start writing code. Also, in the side panel, there's a project explorer inside of IntelliJ. So if I expand it and expand to the source, the SRC folder, I can see com.example and main. So any source files get added to the project, and I can open them up and edit them right here in IntelliJ as part of my project. To build the program, I can go to the build menu and say build project, and it will give me any errors or problems. Compiling, in this case, it says no problems. If I put something, let's say a partial statement, I'll just type in int I without any semicolon. IntelliJ actually compiles it live, or at least checks the code for errors, and it's telling me that there's a semicolon expected, and variable I is never used. So the red circle with the exclamation mark are errors, and the triangle with the exclamation mark are warnings. So I'll remove that, and what I'm going to do is just type system.out.println. And of course, this example application has to be a hello, comma, world, exclamation mark. So it's a hello world application. And I'll save it. I can select build and build project, but if I just go to the run menu, I can select run main, or from the toolbar, I can click the run icon, and each one of these has a tooltip that says run main, shift F10. So I can select it from the menu, the toolbar, or type the shortcut shift F10. And I typed shift F10, and that will compile and run the program and bring me to the output. And the output shows hello, comma, world, and then process finish with exit code 0. Exit code 0 meaning success. And that concludes this demonstration of the Java development tools using IntelliJ. In this video, I'll demonstrate the Javadoc syntax and tool from the IntelliJ IDE to generate HTML documentation, following the syntax covered in the video titled Java Documentation. So let's start with this example file greet.java, and it's part of the package com.example. I start with the first Javadoc comment block. So I have /**, and then on each line I have some description or some tag associated with Javadoc. So I describe this as generic greeting example, @author is Steve, @version 1.0, @since 2021-01-20. Then inside of public class greet, I have another comment block describing a static variable, public static final string greeting equals hello. So it comments it as the default greeting if, double quotes, the empty string is supplied. And then I have a method called sayGreeting. And above this sayGreeting method, above its declaration, I have a Javadoc comment. So it just says Javadoc comment for main, and I can put in sayGreeting. So this describes the method. And then @param greeting. So @param is the parameter for the method. So the first one is greeting. This is the salutation, for example, hi or hello. @param recipient for the second parameter, the receiver of the message. So for example, world, Steve, or Jane. So we can greet saying hello world. And then @return describes the return value. This is the full greeting to the recipient, for example, hello world, with the comma, space, and exclamation mark added. So sayGreeting takes the greeting and recipient arguments, and it declares a string message. If the greeting.is empty, that's true, then no greeting was supplied, and I use the default one. So message is equal to greet.greeting plus or concatenate comma space and then plus to concatenate the recipient, and then I concatenate the exclamation mark. So just the exclamation mark in double quotes. Else, message equals greeting, so that's the argument greeting, comma, space, recipient, exclamation mark. And then system.out.println of message. So message doesn't actually get returned, it just gets printed. So I can change the comment and remove the return because there is no return value, and take this full greeting to the recipient and put that above in the comment and say it prints full greeting to the recipient, for example, hello world, and I clean up the bottom a little. So I'll save this. And now in main.java, I have greet g equals new greet, and then g.sayGreeting with the empty string, comma, world. So if I run from the toolbar, it will build the program, execute, and print hello world, process finished with exit code 0. So I know the program is fine. And what I'd like to do is go to Tools and select Generate Javadoc. And I'm going to generate it for the whole project. And the only thing we really need to change or specify is the output directory. So without it, we can't even generate the Javadoc. So it's going to go in Home, Steve, Documents, select OK. I'll select author and version from the options and OK. And it generates the documentation and puts me into my web browser with the Javadoc. So com.example is the package, the class summary is greet and main, and greet, which I described as generic greeting example. I can select it, and then it has all the documentation, since, version, author. So it has all the same information that was in the Javadoc comments, has the constructor, which I didn't supply, but it puts one in by default, and it's uncommented. But if I go down to methods and find my sayGreeting, it shows the declaration, and then Javadoc comment for sayGreeting prints full greeting to the recipient. And I can select it and go down to the full description, the method detail, and it shows the parameters, greeting, the salutation, for example, hi and hello, and recipient, the receiver, for example, world, Steve, and Jane, as examples. And that concludes this demonstration of Javadoc. In this course, we've examined the features of the Java Development Kit, JDK, and the Java Runtime Environment, JRE. We did this by exploring the Java Development Toolkit and Java Runtime Environment, features and components of the Java compiler, interpreter, assembler, and debugger, features and components of the Java head file generator, documentation tool, and archive format and archive tool, downloading and installing the Java Development Toolkit and the Java Runtime Environment, and downloading, installing, and configuring the IntelliJ IDE. In our next course, we'll move on to examine the importance and benefits of writing clean code and methods and tools for commenting and writing clean code.
When it comes to programming, it's very important that the code that's written is clean. While writing clean code might seem to take time and effort in the short term, it will certainly cost you less time and effort on maintenance and enhancements in the long term. So what are some ways that clean code can be beneficial? Well, clean code is far more extensible. The reliability of code is much greater if the code is clean and simple. Obviously, clean code makes debugging simpler too. Also, in those cases where refactoring is necessary, clean code makes that refactoring effort much simpler and quicker. And of course, clean code is far easier to maintain. Having clean code is not just about preference. There are several objectives we're trying to meet with clean code. For example, clean code should allow us to test business logic much easier. With clean code, minor changes shouldn't result in any significant impact on functionality. And of course, it's way easier to refactor small, simple, and clean code than it is with complex and monolithic code, isn't it? So one goal is to make sure that the code is easier to refactor if that's ever something we need to do. And naturally, one of the other goals is that upgrading a system should be relatively seamless. So what does clean code even mean? It sounds like a pretty subjective term, doesn't it? Well, in some ways it is subjective, but we try to make it more formulaic than that. So when we say clean code, we're really talking about a few particular elements. One of the most obvious elements of clean code is that it's readable. That means that the code is formatted a certain way, flows a certain way, and is even laid out a certain way. We'll get to that later in the course. But if code being readable is obvious, then code being understandable is important. It's one thing to be able to read code, it's a whole other thing to be able to understand what it's doing. And that means organizing your code a certain way, naming things a certain way, and keeping things simple enough that it doesn't overload the reader with complexity. And the final element of clean code is that it can be modified. Code will change, that's inevitable. So if code needs to change, it should be simple and clean enough that those changes can be made without significant impact. Now, as I said, clean code is a bit of a subjective term, but the developer community has been communicating standards and methodologies for decades. So when it comes to clean code, there are a certain set of principles involved. For example, clean code is not language specific. Having clean code is not something that pertains to just Java, let's say. Principles of clean code really are language independent. Developers often find themselves working with multiple languages anyways. So having the same guiding principles and standards across languages is very beneficial. And like I said, there's a large developer community, and that community has large online support. Most standards for code are now well documented and codified. In some cases, they're even built right into your IDE. Some clean code principles are so common they have names, and you may have even heard of some of them. Probably the most common principle is the KISS principle. Keep it simple, stupid. That's it. While you're writing code, always remember to keep it simple. If you have a method that's 1,000 lines long and full of loops and conditions, you're not keeping it very simple. My personal favorite code principle is the DRY principle. Don't repeat yourself. As a developer, you'll often find yourself writing a block of code and then repeating it for some other part of your solution. And suddenly you have two blocks of identical code. You've repeated yourself. So if there's a change you need to make, you now need to make it in two places. So you should work towards converting that block into a method so that it only exists in one place. Another clean code principle is YAGNI. You aren't gonna need it. Basically, this revolves around the idea that you should not build functionality into your software until it's actually needed. So saying things like, oh, users might like this, or this would be a good feature is bad because you're building things and adding complexity for something no one has even asked for yet. The SOLID principle is actually an aggregation of multiple principles. It stands for single responsibility, open closed, list-off substitution, interface segregation, and dependency inversion. I won't go into all of these, but we'll certainly talk about single responsibility later in the course. Now, with all that being said, the best clean code principle you can have is just having coding standards. In fact, most of the time, there are industry accepted and published coding standards that you can just use. I personally took the Microsoft standard and added my own tweaks before making it company policy. So you don't have to invent your own, but you should definitely have coding standards. And finally, we have the composite reuse principles. Basically, the idea here is to design your classes around the idea of what they do, rather than what they are. And once you wrap your head around that, you'll find that your classes get much smaller and simpler because they focus on doing one thing and one thing well. Having clean code will go a long way to making your life and the lives of other developers much, much easier. So what are some qualities of clean code? Well, first, clean code is simple, or put another way, it's not overly complex. Small code blocks, small classes, and doing one thing at a time are just a few ways that you can gauge the simplicity of code. Clean code is also readable. Any other developer should be able to come in and easily read what your code is doing, and you get bonus points if the code is understandable. Of course, you can't say code is clean without it also being well structured. Layout of code, classes, and even files can make things much easier on you. And a bit of a challenging aspect of clean code is that it's expressive. And that means that it tells a story. This is a sort of extension of readability. Now, clean code is also maintainable. You're not going to make perfect code out of the gate, so being able to go into the code and make adjustments is key. If the code isn't clean or is overly complex, that maintainability is not so good and it will take much longer to do. And even if you do make perfect code out of the gate, you're still likely going to want to add some more features. So having clean code allows you to be more extensible. And one of the most obvious qualities of clean code is that it follows standards. Not just your own personal standards, but industry standards. And finally, one more quality of clean code is that it has as few dependencies as possible. Now, you will have dependencies, and that's fine, but you want to keep those dependencies to the bare minimum. So let's dig into these qualities a bit more. The first and probably most important quality of clean code is simplicity, and there are several ways to achieve simplicity. The first, and in my opinion the most important, is the single responsibility principle. With SRP, you strive to make each individual line of code, each method, each class, and even each service do one thing, and do that one thing well. Ultimately, the idea behind SRP is that if there's a reason to change a class, there should only ever be one reason. And another aspect of simplicity is the dry principle. Don't repeat yourself. Ultimately, what you're trying to do is avoid cases where you have multiple identical code blocks. In cases where you have duplicate code, you should look to create additional methods or even classes to handle that code. That way, if you ever have to change the code, you can change it in just one place rather than in multiple places. Clean code is readable, period. Your goal should always be that another developer can look at your code and read what's going on. That means that your code needs to be well written. That can include formatting, layout, and even things like method and variable names. Having an obvious flow of logic is also useful. Now, the aim is to make sure that other developers can look at your code and not only read it, but understand it too. Now, having well structured code is a good sign of clean code. When we talk about code being well structured, we're talking about how classes and objects work together and with each other. If code is well structured, the time to create the code and certainly to maintain the code is drastically reduced. And the benefits are obvious over time. And of course, the less time you spend on maintaining your code or dealing with bugs, the lower your overall cost is over time. And who doesn't want that? Now, earlier I talked about code being expressive, as in it can tell a story about what's going on. To achieve that, you generally have to make sure your methods and classes follow an expressive naming convention. For example, imagine you have a class that opens and closes a connection to something. Well, you would want to create methods called open and close in the command sense. Then, if you happen to raise events from those methods, you'd call those events opened and closed in the past tense. To anyone reading the code, what you're doing is very obvious. But you should also strive to use proper naming too. For example, if you created a method called runaway, it might be sort of obvious to another developer and it might even get a chuckle, but it's not proper. Instead, calling the method abort would be way more obvious. Now, it's very rare that we create code, run it for a day, and then throw it away never to use it or see it again. Generally, we write software to last literally years. So it's very important that your code is maintainable. So how does clean code result in maintainability? Well, clean code means that the code is short, to the point, and simple. And that makes it much easier for someone to come in and adjust the code over time. Logically laid out code is much easier to understand. So in the event that there's an issue and maintenance is required to resolve it, it should be pretty obvious where to find the problem. And of course, clean code is consistent. And that means that your code does the same things in the same ways across the board. So when a developer comes into the code, the layout and methodologies are always the same. Not just in this code, but in all the code you write. Now, clean code is also extensible code. And extensible code means that you can make changes to it to make certain aspects better or faster. If you have to rewrite the code every time you want to make a change, it's not very extensible. So clean code should enable you to make changes easily. Extensible code doesn't just mean changes either. It can mean adding whole new functionality. Adding more to existing code is pretty common. So your code should be written in such a way that you can add features without having to rewrite everything. Now, I can't say this enough, but the best bet for clean code is simply to follow standards. Whether you use existing, published industry standards or you write your own, Whatever you do, follow those standards. It will save your life. There are all kinds of standards, really. Some are just guidelines. So, for example, you can specify when to wrap method parameters onto a new line, and that would technically be a guideline. Your standards could also include rules about how to write code, and that includes organization of code, naming conventions, commenting, and so on. But rules can be broken, right? Well, you should try not to, but sometimes there are compelling reasons to violate a rule. So that's why you should also have regulations. A regulation is an unbreakable rule. For example, you can say something like, "Thou shalt place all classes in their own file," and then any code that violates that regulation is rejected. And finally, you want to make sure that your code has as few dependencies as possible. Dependencies are references to code outside of your project. Dependencies can create real difficulties because dependencies can change, they can get outdated, or they can even go end of life. And that means that your code is actually held somewhat hostage to its dependencies. And that's not the worst thing in the world, but it's something that you want to manage for sure. And that means that on occasion, you should assess your code and work to reduce the dependencies to just what you absolutely need or are comfortable to be dependent on. When it comes to writing clean code, there are certain best practices that you should follow. For example, you should aim to have naming conventions, a good file structure, proper commenting strategies, good layout, naming, and implementation of methods, proper formatting like indentation, and logging for ongoing troubleshooting situations. So let's dig into these a bit. Clean Code 101 says that you should have a strong naming convention. A naming convention is exactly what it sounds like. You should make sure that everything in your code has a standard way of being named. For example, your code will inevitably have variables in it. Well, where those variables are being used and defined may warrant a naming convention. For example, lots of developers give class level private variables an underscore as a prefix. And there's also naming conventions for methods. Even project domains or namespaces should have a naming convention. And that means using things like upper camel case and avoiding the use of abbreviations. The one overarching rule for naming conventions is that the names are consistent and meaningful. Another common strategy for clean code is implementing a file structure. Having a solid file structure can result in clean code simply through organization. For example, I have a strategy that files must be stored in directories and subdirectories that match the domain or namespace of the file. So if I was looking at a stack trace from an exception, I would actually be able to tell exactly where the associated code file is physically located. A file structure helps to make your code understandable, and that's because you're laying out files into logical buckets. These are my service interface classes, these are my contract classes, and so on. Now, that being said, your file structure will almost certainly vary by project type. Not all projects are exactly the same. However, the strategy of laying out your files should always be the same. Next comes commenting. Now, we'll talk about this in a bit more detail later in the course. Comments are bits of text in the code that explain what's going on in the code to a developer that might follow behind you. Comments should always be efficient. It's often forgotten that comments are actually like code. If you change the actual code, you probably have to change the associated comment. So you're not just changing the one thing, you're changing two things. So the comment should be short, concise, and to the point. Ultimately, your comments need to be ergonomic to the code. In other words, they should be specifically designed to complement the code and enhance its clarity. Now, when we talk about clean code, it generally brings us to talking about the implementation of individual methods. Methods often use a verb-noun structure like getName or setName. Now, that being said, sometimes your class name is so obvious that you only need a verb. For example, if you have a class called SQL Connection, you would be perfectly fine to call your methods open and close, because adding the noun would be redundant to the class name. Remember, don't repeat yourself. Now, method names are always camel case. Now, that means that the first letter of each word is capitalized. Now, some languages, like Java, prefer the first letter of the first word to be lowercase. Now, importantly, it's a general rule that if your method has an abbreviation in it, the first letter is still the only one that's capitalized. Now, good methods are simple, and that means that methods really should only have a maximum of 2 arguments. If you find yourself needing more parameters, it might be worth creating a class that defines those parameters as properties, and then you pass in an instance of a whole class into the method rather than all the individual parameters. And finally, bracket placement is important. It's not a strict rule as to where the brackets should go. Developers have fought over this for years. But whatever you decide, stick to it. My general rule of thumb is to do whatever the IDE does out of the box. And generally, you should have a pretty good reason to fight the default. And speaking of formatting, clean code means having a consistent strategy for indentation. Generally, indenting is most important when it comes to nesting. Code that sits inside something like a method, a loop, a conditional statement, or even a whole class should be indented to show that it's inside that object. Now, braces are generally a good indicator of where additional indenting is required. Now, I would also recommend using spaces to indent your code and not tabs. Imagine opening your code in another editor just to explore it. If you use tabs, your code could be pushed way off to the side and harder to read. Whereas if it's spaces, it will always look the same no matter what editor you use. And the final aspect of clean code that's worth talking about is implementation of logging. Logging is very useful for debugging and troubleshooting your code as it runs. You can see what's happening or what happened in the past, and determine whether the code is functioning correctly. Now, that generally means that you should implement logging functions. Now, just like code, logging should have a set of standards, so having a function that performs the logging means that you can expect the same output no matter where you call the logging method from. There are many benefits of having clean code. For example, clean code means reduced maintenance during development and over time. It also makes it much easier to communicate with other developers about the code. Clean code also means much more efficient testing, too. And the cleaner and less complex the code is, the more likely it is that bugs will just present themselves rather than be squirreled away in hard to find nether regions. And clean code also provides the benefit that it mitigates cascading effects. So let's dig into each of these a little bit more. One of the most compelling reasons to have clean code is that it reduces maintenance. In other words, there's less involvement from developers over time. You'll still have to go in there and fix the odd bug or evergreen the software, but the time it takes to do that is drastically reduced. And that means that the whole business should be able to get behind clean code because it means a reduction in cost. But it's not just a reduction in the cost either, it's a reduction in lost opportunity costs. By having clean code, developers are less distracted from developing new features and value add work. So that's good, right? Now, at the end of the day, a reduction in maintenance means that developers can focus on the delivery of their software and the new features around it. Now, clean code also means that it's way easier to communicate with other developers. When different developers look at the same code, the intent of that code should be so obvious that both developers come to the same conclusion about what it does. Now, if I see a class called SQL Connection Manager, I have a pretty good idea about what it does. If your code is clean enough, then even the methods will be obvious. In other words, any developer should be able to pick up another developer's code, and if the code is clean enough, the developer should be able to quickly and easily understand what's going on. One of the biggest benefits of clean code has to do with testing efficiency. Mature organizations include various kinds of ongoing tests with their code, and this can be automated tests or even manual tests. Clean code is simply easier to test because it's simple and does one thing well. Given a certain input, you can expect a certain output. No jumping through hoops or sacrificing goats, it's just nice, simple code and tests. And what that means is that it's way easier to identify problems. If a test fails, it can only mean one thing, not 28 different possibilities. Now, the goal of any developer is to write perfect code. If you succeed in doing this, please tell me how. The fact of the matter is that you will encounter bugs. However, with clean code, the bugs tend to present themselves. If your code is simple and to the point, a bug is much easier to spot. So if a bug is encountered in the wild, It can be reported, and the exception information can ideally make it super obvious as to where the problem is and how to fix it. Clean code will mean that code reviews are also simplified, and that means that feedback can be much more efficient. And that's important because it means there's even less of a chance of bugs escaping into the wild. And the final benefit of clean code that I'll talk about is that it mitigates the cascading effect. But what does that mean? Well, imagine that you needed to change some code. If your code wasn't clean, then there would be a good chance that the changes that you need to make would snowball. In other words, making your simple change could potentially mean having to change many different classes. Clean code reduces the overall complexity of your software. Changes are simple and usually very contained and isolated. At the end of the day, that simplicity and avoidance of any cascading means that your applications will perform well and perform predictably. Our goal is to create simple and clean code. Our enemy in achieving that goal is bad coding habits. Bad code habits can be broken down into four areas of concern: teams and teamwork, code organization, code writing, and testing. So now let's dig into each of these a little bit more. Now, teamwork is a fundamental part of development. It's quite rare that development all flows through a single person. And even if that's the case for you now, one day you'll have to work with a team. But sometimes teams form bad habits that can really impact the quality of code being generated. For example, poor planning is a real kicker. If a team doesn't plan their activities well, they'll find themselves making up designs on the spot. And that generally means that the code is not well thought out, and the result is predictably bad code. Teams that don't communicate well often run into poor quality code too. And this can include not understanding requirements, or even just not realizing that different developers are working on the same things and wasting time. One of the best things that teams can do is commit to the work that they're embarking on. And that commitment shows that there's a plan and a timeline. Without that commitment, everything is being done sort of ad hoc, if it's even being done at all. How can that translate to good code? On a similar note to communication, teams that don't collaborate with each other can result in bad code organizationally. For example, if Team A is working on a component that Team B needs, but Team A doesn't tell anyone and doesn't gather requirements, then Team B is left in the dark, and it's also unlikely that Team A will deliver anything of value to Team B. Now, good teams will perform code reviews to validate the code that they've written and make sure that it adheres to standards, best practices, guidelines, and so on. They're also working hard to make sure that they're meeting the actual requirements. One of the coding bad habits that teams can get into is how they handle those code reviews. It's worth remembering that development is a business. Teams or individuals that take feedback from code reviews personally won't grow. They may end up becoming toxic and may even purposefully ignore coding standards. Teams and individuals can sometimes fall into the trap of shifting blame. Oh, the code is like that because Larry said. It doesn't really matter why the code is the way that it is. No one's blaming anyone. Let's just fix it and move on. And one of the worst traps that teams and individuals can get into is being inflexible. Oh, well, this is just the way we've always done it, so. Feelings and preferences cannot override standards and regulations. They exist for a reason. And finally, it's super important, particularly in code reviews, that feedback is timely. A really bad habit that some teams get into is giving feedback super late or not at all. Meanwhile, the developer has moved on to other things and has to context switch to get back to the feedback. And that takes time and costs money. Writing good code means organizing it appropriately, but there are some bad habits that people tend to fall into when it comes to their code organization. For example, having a poor methodology or just a way of doing things results in a non adherence to standards, and code can just get lost. Worse, it means that new developers may not be able to understand what's going on. And procrastination is another bad habit along those lines. Oh, yeah, I'll put that class in its own file later. I just want to finish this thought. A lot of times, when we put off the needed activities, we never get back to it. Another bad habit we can fall into when it comes to code organization is overworking the solution. Yes, there is too much of a good thing. Over engineering or over optimization rarely gives the benefit that we expect. I have a standard rule of thumb that I tell all of my teams. Never pre-optimize. Make the code work the proper way, then if there's a need to change it or optimize it, then we'll do the work then. Another bad habit I've seen teams run into over and over again is ignoring accessibility. It's so much harder to retrofit code with accessibility options than it is to handle it from the outset. It should also come as no surprise that cutting corners is a very common bad habit. Yes, I know our standard is XYZ, but it's just so much easier to do it this way. Standards and methodologies have a reason to exist, so if you find yourself cutting corners, it's likely that you're going to run into problems. Another fairly common code organization bad habit is rejection of styling. Developers have preferences, but standards should outweigh those preferences. Saying something like, well, this is my preference, so I'm going to ignore the standard, is no good. Remember, the goal is that all developers should be able to read and understand everybody else's code. If everyone implements their own styles, that goal is very difficult to achieve. I've literally had to let people go over this. Using poor naming is also another bad habit. Naming variables things like A, B, and C doesn't help the next developer to understand what those variables are for. Now, when it comes to just plain old writing code, there's lots of bad habits that we can fall into there as well. For example, taking shortcuts can be a real problem. Generally, that means not taking the time to understand the requirements, the tools, or even the code itself. Some developers get stuck in their ways, and so they avoid using the right tool for their job. And one trap that developers fall into more than any other trap is jumping right in. Developers get excited about development. So they have an idea in their heads and they excitedly start coding. But that means that there's no real plan or a strategy. It's also a really bad habit to ignore errors. Sometimes errors are intermittent or infrequent. Errors are a nuisance, so if they don't happen all the time, developers sometimes are willing to just live with them. Well, that's not good, and it's an indicator of bad code. Another bad habit is simply not asking for help. Sometimes developers are embarrassed or they're scared of senior staff, but all that results in is a waste of time. I once had a developer on my team that spent 3 days writing a JavaScript method to add 1 second to any date that you gave it. 3 days! That's already built into JavaScript. He didn't need to write that code at all. But he was too embarrassed to ask for help, so we wasted 3 days of development time. Now, good code can be reused, but a bad habit is haphazard reuse of code, meaning you need some code over here that you used over there, so you copy and paste the code and move on. Well, that's not good. If nothing else, you're repeating yourself, and you shouldn't repeat yourself. Then there's cases where you really should be using some existing code, but instead of using that code, you reinvent the wheel altogether. In that case, you're spending time writing code that already exists. And while development is happening, developers tend to hard code some things, and that's fine. But a bad habit to fall into is keeping those things hard coded versus allowing them to be configurable. And one last coding bad habit is simply ignoring consequences. Sometimes we write code, use a library, or even copy something from the internet that seems to solve our problem, but then ignore the consequences. I once had a developer that didn't know how to make an application wait for customer input. So he created a loop that constantly checked to see if the user had said anything. That loop was an infinite loop if the user never said anything at all. And the result was that all the memory and CPU was taken on the server, to the point where the application crashed and affected any other running process on the system too. All because the developer didn't think of the consequences of his code. Now finally, let's talk about testing bad habits. You're gonna have to test your code, but certain bad habits can get in the way. For example, some developers don't stand by their code. They write it, throw it over the wall, and then forget about it. It's not their problem anymore. And that doesn't help anyone. One of the most common bad habits I've seen is developers making changes to the code until the very last minute before deployment. If there's one thing that's guaranteed, it's that rushed jobs always result in problems. If you're coding that late in the game, the code simply isn't ready yet. The end. Developers also tend to get very excited about code and solving problems with the technology, but they have a habit of ignoring non-functional requirements. Developers should always try to remember the value proposition behind the feature that's being created. Why was it required? If the developer knows that and understands that, they can write code that most efficiently solves the problem. And the worst habit developers can fall into is manipulating tests so that they pass. If you have to manipulate a test to say that your code works, you're probably doing something wrong. When we talk about clean code and coding best practices, it's important to keep in mind the very nature of software projects. After all, at the end of the day, software development is, by nature, a research project. In other words, there are unknowns. If the answer was known, it would already be software that you can just buy. Software projects are notoriously difficult to maintain. Technology changes, people change, the software itself changes. It's something that has to be carefully managed. Having clean code can only help with that endeavor. Old software projects are tough to deal with, especially when you bring on new developers. If code isn't clean and hasn't been maintained, I will guarantee you right now that developers will immediately suggest rewriting the code versus trying to understand it. And finally, when it comes to software projects, there are hard costs and soft costs. Hard costs have a direct impact on the outcome, while soft costs have an indirect impact. And it's worth acknowledging that clean code is a soft cost. I once had a boss ask me to quantify to the dollar how much he would save if I instituted the code quality policies that I wanted. While I understand his question, it's impossible to quantify without running two identical projects, one with policies and one without, and see which was more expensive over a span of literally years. It's something where we all just need to agree that higher quality code will naturally be less expensive to create and maintain in the long run. Now, with all that being said, messy code does have some direct impacts worth noting. For example, it can't be understated how much impact messy code has on team morale. When teams are given clean code, it can be a pleasure to work with. But if they're given messy code and forbidden from rewriting it, it will be a terrible experience. I've been there, trust me. Messy code is simply harder to work with. It takes time to find out what's happening and how it works. Pulling a thread cascades into other areas. Simple tasks take forever, and the result is missed deadlines, and the business won't like that. Messy code also means that estimation is very difficult. It means that when enhancements or bug fixes are required, it's honestly a situation where everyone is put on hold until whenever it is that the work is completed. Imagine being a salesperson and you wanted a new feature for your customer, and then being told that that feature will be completed anywhere from 2 weeks to 6 months. And of course, messy code is bad code. Bad code is unreliable and often slow. Add that to the time it takes to add new features or fix bugs, and what do you get? Customer frustration. And no one wants that. Ultimately, bad code costs the business. Sometimes it's not immediate. Sometimes you incur those costs way later. But it will cost you. Those costs can certainly manifest themselves in terms of time and money, but it may also manifest itself in overworked staff. And it will certainly manifest itself in systemic inefficiency. In fact, let me dig into these a little bit. When we say that a business will incur costs, an obvious way to manifest itself is in terms of time and money. Bad code can result in time and money impacts in a few different ways. For example, there's a huge amount of time that businesses waste on working with bad code. Some jobs should be simple, but with bad code, it takes 10 times longer to deal with, 10 times longer to test, and sometimes even 10 times longer to deploy. That wasted time is no good for anyone. Often I've found companies that have dug themselves into such a deep hole that they seek outside support to understand what their true issues are and how to get out of that hole. And I've never been in one of those meetings where the business liked the answer. In fact, I was recently in a meeting where the blunt answer was, "I'm terribly sorry, but you're going to have to throw it out and start again." There's a sunk cost to all that work done to that point. And imagine hearing that as a developer on the team and what it does to morale. When team morale goes down, it can severely impact throughput even more. And at the end of the day, what needs to happen is that teams need to track and manage their technical debt. It cannot be allowed to get out of hand. My general rule of thumb is that technical debt should be something that you're allowing to happen for the sake of timeline, but is something you immediately deal with in the next release. And the business needs to be on board with that. It means that you're trading quality for time, followed immediately by time for quality. And of course, time should be set aside for performing maintenance of code. This includes evergreening, tweaks based on new understandings, bug fixes, and performance improvements. Businesses need to set aside time and money to do that. Let's put it this way. You can certainly skip putting oil in your car and it will certainly be cheaper. But sooner or later, the engine will seize and it will be a heck of a lot more expensive to deal with. Software is the same. Plain and simple, bad code will usually result in overworked staff. Most businesses don't account for fixing bugs and dealing with technical debt when they're estimating a project, let alone setting aside time to deal with bugs in previous versions. Bad code will certainly almost always result in there not being enough time to get the work done. So what happens? People get overworked trying to keep up, and then they cut corners. And there's an exponential cost to cutting corners too. You're incurring even more technical debt to try to get out of the technical debt that you already have. Sooner or later it blows up. And remember, it's always way more expensive to resolve a problem once it's in production than right at the point that you're developing. And lastly, one more way that time and money can be impacted is through plain old systemic inefficiency. When you're in a situation where you have teams that don't have the necessary specializations, you're going to have a hard time dealing with specific problems. For example, if your software appears to have a security issue, but you don't have a security expert, it means that your team is floundering and at best guessing at the result. And at the end of the day, you want to measure the amount of time that you're spending on writing code versus the amount of time that you're spending maintaining it. There's no right answer on that because it's project and scale dependent, but you'll need to measure it to decide for yourself if you've got the right balance. So we can all agree that messy code is bad. Even if you've never fully understood what the ramifications of messy code were, you'd still decide that messy code is bad. So that leads to the inescapable question: how do we go about fixing messy code? Well, there are three options available. One way is to actually make the fewest changes possible. Another is to clean and polish the existing code. Then, in the worst cases, do a complete rewrite. Let's talk about each of these options a little bit more. The first option available to you when you want to fix messy code is to make the fewest changes possible. Imagine a scenario where you have some messy code that could use some love, but that code isn't super important, or put another way, it's low risk. In those cases, it's really great fodder for a junior developer to cut their teeth on. In fact, my very first task as a developer was to take some existing code, fix some problems, and then add a new feature. It was a hard problem and I was not very confident, but the business gave me all the time and guidance I needed until I did it. Now, if you gave me that task today, it would take me all of 5 minutes. Now, this option is really good if you don't necessarily mind adding a little bit more messy code. Obviously, the goal is to reduce the messy code, but you can do that through oversight and feedback. What you really want to do is make sure that the developer adheres to a strict methodology and learns from the situation. In fact, your goal is less about the code itself and more about grooming the developer so that when they move on to other projects, they're not generating messy code there. Now, at the end of the day, the actual task may in fact be achieved, but what the developer did may not even be the best solution. A bonus activity would be to have the developer periodically return to that code and improve upon their solution. Now, the second option available to you when you want to fix messy code is to clean and polish the existing code. A simple polishing activity is to just go into the code and fix the formatting issues to adhere to standards. So that would include line breaks, code grouping, method ordering, and of course, indentation. Another activity that you want to do while cleaning and polishing code is to deal with variable names. Method and class names are also a good idea to deal with, but that can have a cascading effect, so at least variable names will do. Now, if the code is messy, of course that means that it's not clean. So simply reformatting and changing variable names doesn't make the code clean. So another thing that you can do to bridge the gap is add comments that explain what the code is doing at key parts of the solution. And the nuclear option that you have when you want to fix messy code is to not fix it at all. Instead, it's to completely rewrite it. The most important thing you'll need to do when you rewrite code is to come prepared with a plan. As excited as you or other developers might be to have a blank slate to work with, coming to the party without a plan will almost certainly result in you being in the same boat that you're trying to get out of. I once had a boss who gave us the plan of replace in kind. In that case, we all knew what the original application did and therefore what the new application should do. But that wasn't a plan. So the result was that the project went grossly over time and budget. Another important thing that you'll need to keep in mind is that if you're going to rewrite the code, it really is best to write it from scratch. Sometimes you have modules or packages that you want to try to keep around, and maybe that's fine. But remember that if you try to keep portions of the very code that you're trying to rewrite, it means that you're giving yourself a constraint that could cause you problems down the road. Now, technically, there's a fourth option for dealing with messy code, and it comes between polishing and rewriting, and that's called refactoring. Refactoring means to change the code and morph it into what it needs to be. Sometimes refactoring is the only option if you don't have the capacity to rewrite code altogether. Sometimes refactoring is good if you only want to change a small aspect of your code rather than the whole thing. So if you're going to refactor the code, there are some best practices that you should follow. For example, definitely start with the obvious. Don't go searching for the hard problems. Ease in and take care of obvious items first. And it's dangerous to go alone. So before you start refactoring, it's a good idea to elicit support if you can. Another set of eyes on your code or ears about your plan can help prevent you from making the same mistakes as the very code you're trying to clean up. Sometimes the problem with the code is the language itself. You wouldn't want to refactor an application that's still running on punch cards, right? Well, sometimes there's a newer technology that's just better suited to what you're trying to do. So definitely consider other languages and technologies. Of course, at that point, we really are talking about a rewrite, but still. But if you're going to stay within the existing programming language, definitely honor its conventions. Just because you have a particular style or even a corporate policy, if the language mandates a certain convention, it's best to follow that convention. And remember to use meaningful names while you're at it. One of the most common problems with messy code is that it can't be understood. And that's usually at least partially as a result of bad naming. So when you're fixing existing code or adding new code, make sure to correct that problem by setting good names. And don't forget about testing. Definitely test frequently. Each line of code you write should have at least a unit test that covers it. Make sure your code isn't falling into the same old traps. Let's talk about comments. I like talking about comments because I find that lots of people abuse them and don't even really realize it. When it comes to comments, there are two primary categories: clarification and documentation. So let's dig into each of these a little bit more. The first category of comments is clarification. The most important thing you can ever tell yourself about clarification comments is that they're an apology for bad code. That's right. If you write a clarification comment, you're admitting that your code is not readable, can't be understood, and needs further explanation. Generally, a clarification comment should be limited to situations where there's an intent for future modifications. You'll see lots of developers online tend to use the to-do keyword and sometimes even provide a ticket number. Clarification comments can be seen by anyone viewing the code, so it's really important to keep the comment clean, especially if the code is public. But remember, if you're making a clarification comment, you're really indicating to everyone that there's some code smell here. Code smell means that there's something wrong with the code. You can't quite put your finger on it, but there's definitely something wrong. It's not quite right. Ultimately, if you find yourself needing to write a clarification comment, your better bet is to find a way to simplify the code instead, so that it can be read and understood on its own merits. The second category of comments is documentation comments. Documentation comments are generally class or even method level comments that explain what the class or method is for and how it's used. The intent of documentation comments is for anyone viewing the code to understand it more holistically. You can understand what each parameter is for and why. But it's worth remembering that even though comments are code per se, they can still become obsolete, and so they need to be updated right along with the code. If you change a parameter name, you'll have to update the comment too. In today's world, document comments can be interacted with and understood by certain tools. But those tools don't review the code and they don't validate that your comments are actually correct. So if your comment says that a variable name is XYZ, but it's actually ABC, you may be confusing your customers. So be watchful for that. Your best use case for document comments is using those tools to extract the comments from the code and make them available through those tools. A good example of that is API documentation. You can write code that represents an API that users can interact with. Then, in an API gateway, those users can explore your API, all of its operations, the various parameters associated with each operation, and even the status codes that can be expected. And that can all be extracted directly from your document comments. Now, in cases where you're writing comments in your code, there are a number of best practices that you should endeavor to follow. For example, above all, make sure your comment is readable. Developers that follow you will need to be able to quickly read your comment and understand it, so there's no need for crazy acronyms or jokes. It's also important to describe the intent. Don't tell me what it does, tell me what your intent for it is. That way, if there's a bug in the code, I know what you were trying to do and I can fix it. Comments should also be as brief as possible. Be descriptive, but be concise. I don't want to read a brief history of time to understand why you're setting a date to the beginning of the month. Another thing you need to do in writing comments is to avoid explaining functionality. Don't say things like use the JSON serializer class to deserialize a string to JSON. Instead, briefly describe the intent. Try something like deserialize the JSON string. If your company has policies and standards for creating and formatting comments, definitely adhere to those standards. That could be things like line lengths or spacing, or really anything that your company deems important. Now, also make sure that you don't include any unnecessary information, especially opinions or author details. Another thing to avoid is duplication. If you have code that does XYZ and then you have a comment above that says do XYZ, then you haven't gained anything at all. You've in fact duplicated the code essentially, and that's a waste. If your code is readable, then you don't need the comment at all. There are some other kinds of comments too. If you're using a code repository, and boy, I sure hope you are, you should also include a comment about the code that you've created or updated every time you commit that code. Don't commit without comments. In fact, if you can commit and reference a work item, that's even better. Every company I've worked for, I've implemented commenting policies for code commits. Not just documented policy, but enforced policy. In other words, our systems don't even allow you to commit your code unless you provide a comment and reference a work item. In today's world, it's hard to imagine software that doesn't include APIs. The most common kind of API today is the Representational State Transfer or REST API. REST APIs are really good for helping keep your code and projects nice and clean because they adhere to a common global standard. REST APIs are distributed web services, and that means that they're highly available and highly reliable. The vast majority of REST APIs include authorization through access codes or tokens. You don't pass in a username or password, you pass in an encrypted token to a standard header. All REST APIs accept standard HTTP requests as commands from consumers. Then, those consumers will receive responses back from the REST API with relevant information. So let's talk a bit more about REST APIs. First, what are the main benefits of REST APIs? Well, one of the greatest advantages is that it provides a layer of abstraction. And what that means is that there's isolation of storage from the UI. In other words, the UI is completely blind to the fact that the REST API stands in front of something like a SQL database, a cloud database, or even just a set of files. The UI doesn't even care where the data comes from, it just wants the data. One of the reasons this is such a huge advantage is that if the developers wanted to change the storage technology, they could do that without the user ever knowing. REST APIs also allow for caching of information automatically, and that means that users making requests for the same information over and over again can be greeted with a cached response, instead of the REST API making the same request to the database over and over again. REST APIs are also stateless, and what that means is that the API doesn't know who you are from the previous request you made. Each request has to be able to stand alone and not expect that the API knows anything other than what you're including in the command. Now, this is very useful because it means that APIs can be distributed all over the world. One request might be responded to by an instance in Canada and another in Zimbabwe. You wouldn't know, and you wouldn't care. Now, because of that, REST APIs can be very quick. It also means that consumers can have significantly improved performance too. They can hit close to home APIs and benefit from cached results. Of course, that doesn't mean that developing against an API isn't without risks. You need to always be cognizant of the body format for requests. For example, if you're trying to create an object or issue a complex command, you'll sometimes have to perform what's called a post. A post requires a formatted object to be included in the body of the request. If the body format is not correct, the request will fail. And the same is true the other way around too. When the REST API responds with information, it will include that information in the body of the response. So you have to be highly aware of what that format will be. Now, when you start getting into using APIs, it's exceedingly important that you read whatever documented guidelines are included, and this will help teach you which operations to use in which order to achieve your goal. Now, interacting with APIs means that you'll have to implement proper error handling. APIs will respond to you, but just because they respond, it doesn't mean that it worked. So you need to inspect the response for errors and behave accordingly. Now, interacting with APIs also comes with performance risk. While the APIs themselves are highly available and distributed, it doesn't mean that your code will be. So it's a good idea to set up your code to be able to handle API requests asynchronously as background activities. And of course, many APIs include security measures for both authentication and authorization. And that will be your responsibility to manage. If you don't have the right token, the API will reject you. And finally, when you start getting into using APIs, it's important that you read whatever documentation is included. And this will tell you what each operation is for, what each parameter is for, and what the request and responses should look like. Now, if you find yourself in a position where you're actually building REST APIs, then there are some best practices that you should definitely follow. For example, you should definitely craft meaningful documentation. You should have appropriate error status codes. It should definitely be secure. You should consider applying rate limits, and you should use JSON. So let's go over each of these in a little bit more detail. So one of the most important things you'll need to do in creating a REST API is to craft meaningful documentation. This documentation is often included in gateways that consumers can interact with. But what does it mean to be meaningful? Well, first it means that the documentation is clean, concise, readable, and understandable. Probably most importantly, the documentation needs to be informative. And you should strive for consistency. If your operations are all consistent and roughly the same, then you get an intuitive aspect to it that gets reflected in your documentation. And lastly, your documentation should be relevant. Don't include documentation about other technologies or methodologies. Keep it to your API and keep it to the facts. While you're building a REST API, it's also incredibly important to include appropriate error status codes. Sometimes a request will fail, and it can fail for any number of reasons. Using status codes can help the consumer immediately identify the cause of the problem. For example, a 404 means that the resource wasn't found, or a 401 means that you're not authenticated. With that information, the consumer can take appropriate action right away just from the code. But it's also a good idea to include any useful details that you can along with any error messages. For example, if you return a 400 code, it means that the user's request was invalid. By itself, that code doesn't really help. But if you include some detail about which parameter caused the issue, then the user can correct the problem and try again. Now, if it's relevant to you, and it almost certainly is, your REST API should be secure. Probably the most important and the easiest type of security step that you can take is to enable transport security. Most systems include that by default, but if yours doesn't, make sure that you enable SSL or TLS and deny straight HTTP. Also, if your API transmits headers with sensitive information, it's a good idea to scrub those before sending them to consumer. Hackers will take any piece of information they can get their hands on. And if it's possible, it's a really good idea to set up security-based unit tests or integration tests to make sure that your API remains secure. Now, one protective thing that you should look at doing when implementing a REST API is to apply rate limiting. Rate limiting prevents consumers from asking for lots of data or making too many requests. For example, lots of APIs will include a rate limit that prevents consumers from asking for more than something like 60 requests per minute. The good news is that there's already tons of tools out there that can do this for you. Generally, this is handled by a gateway tool. Now, because REST APIs are stateless, it means that rate limits are generally tied to authentication. That means that the gateway can understand who is making the request and limit that identity. You can also do this through subscription keys, IPs, and so on. But the advantage of doing it through authentication is that it provides a poor man's user control. For example, you can say that user A can access the system 100 times per hour, while user B is unlimited. Finally, REST APIs should use JSON for their requests and responses. JSON is the most common industry standard for APIs. If you want to reach the most consumers, JSON is your best bet. Other options include XML and YAML, and both are fine because there are converters to and from those languages. But they're not very common, and it adds more overhead to try to use them. The biggest advantage to JSON is that it's really easy to read. JSON is almost like a condensed JavaScript-based version of XML. And YAML is actually almost a condensed version of JSON. But most people understand JSON very quickly and easily. Throughout this course, we've talked about working towards ensuring that your code is clean. We've talked about ways to achieve that and specific things to look out for. Yet the concept of clean code is a bit subjective. It's worth talking about the specific characteristics of clean code, and we can start by first understanding the characteristics of messy code. Messy code is easily identified by its three main characteristics. It's confusing, it's disorganized, and it's difficult to manipulate and maintain. Now let's contrast that with the characteristics of clean code. Clean code is identified by its three main characteristics. It's sensible, it's organized, and it's easy to work with, enhance, and maintain. Now there are four categories where you can easily distinguish clean code from messy code: formatting, naming, method implementation, and comments. In fact, let me explain each of these in greater detail. First, let's talk about the difference in formatting between clean and messy code. One of the principal aspects of formatting is indentation. Clean code has consistent, policy-based indentation throughout the code. Messy code isn't indented, uses a mix of spaces and tabs, or is completely inconsistent. I've seen so much code that tried to align things by the equal signs, it sends a chill down my spine. Now, clean code will group appropriate methods together. Messy code will have no strategy. Clean code will have a common strategy for the use of case in names, and messy code will be inconsistent. Clean code will have a predictable common strategy for spaces between operators, while messy code won't. Sometimes there'll be spaces, sometimes there won't. Clean code will have a strategy for where to put braces, like the end of the line or the next line altogether, and messy code will be completely unpredictable. Clean code always has a maximum of one line break between logical code blocks, and messy code will have none at all or way too many. Clean code has a maximum number of characters a line will be before it gets broken onto a new line. Messy code won't care and will have lines that require tons of horizontal scrolling. Now, clean code makes consistent, predictable use of line breaks. Messy code will be completely arbitrary. And clean code makes predictable and limited use of nesting. Messy code won't. I've seen code that had loops that contained more loops that contained conditions with still more loops, switch statements, and conditions. I'm having nightmares just thinking about it. Next, let's talk about the difference in naming between clean and messy code. Clean code will have a consistent strategy for naming variables, and messy code will have arbitrary, hard to understand, and certainly inconsistent strategies, and likewise for method naming. It also extends to class names too. Clean code will have relevant, descriptive names for classes, and messy code won't. I worked with a guy who thought that it was a good idea to code name classes, things like blue, white, and orange. He was an executive in the company, in fact, and we worked very hard to get him away from code. Another obvious contrast between clean and messy code is comment implementation. Clean code will only use comments for clarity. Messy code will have comments all over the place and add no real value. Clean code may use comments to organize code, but messy code will have no such strategy. Clean code also knows when to use comments and when not to use comments. Messy code will provide comments to tell you something that you can plainly see just by looking at the code. And clean code will limit comments to identifying areas of complex code, whereas messy code will include comments about anything. Next, let's talk about the difference in method implementation between clean and messy code. Clean code will feature small methods that do one thing and do that one thing well. And messy code will have large, monolithic functions. Clean code will be modularized with obvious grouping of methods. Messy code will have no consistent strategy in method implementation. Clean methods will have clear and obvious functionality. Messy code won't. In fact, often messy methods will perform actions by side effect. For example, you may request some information and then, by virtue of that request, database connections are established. So developers are forced to request data just to connect to the database. And finally, clean code includes methods with no unnecessary code. Messy code may include lots of additional cruft like timers, unwarranted logging, or even those side effects I just talked about. When it comes to writing clean code, you're not completely on your own. There are tools that can actually help you achieve your objective. For example, 4 clean coding tools on the market are Husky, ESLint, Prettier, and Standard.js. In fact, let's talk about each of these in a little bit more detail. First up is Husky. Now, Husky is an open source Git hook, and that means that it's implemented in your Git repository. Git hooks actually execute code. In this case, they'll execute the Husky code. And that code is executed every time a commit or a push is performed. In other words, every time you commit or push your code to Git, Husky is executed against your code. Effectively, Husky can be used to run tests or format your code. But be cautious. This can be a bit pesky though, because it means that you have code on your local system, you commit or push it, and then it's different in the repository. But that being said, when you pull it back down from the repository, it's all nice and formatted. Next up is ESLint. Now, ESLint is a code linter. Linting is a static analysis of code that validates it against certain patterns and guidelines. And ESLint is pluggable too, so you can add all kinds of different pattern checkers. Now, ESLint can be run at any time, so you don't need to implement it as a Git hook like you do with Husky. Then we have Prettier. Prettier is a straight-up code formatter, and it has a built-in set of rules that work while you type your code. Ultimately, that means that Prettier is very easy to use. It will highlight your code to tell you that it has formatting issues, and then you can request that it formats it according to those standards. And one of the interesting features that it has is that you can run a single command, and it won't just clean the file that you're working on, but the entire codebase. So imagine your job is to take some old code and bring it up to at least the current code formatting standards. Well, with Prettier, that can be a pretty quick thing to do. It's just one click. And lastly, we have Standard.js. Now, Standard.js is a code formatter and a linter, so it combines the capabilities of things like ESLint and Prettier. Now, Standard.js uses a style guide to run the lint job as well as to format the code. But it is worth noting that this is exclusive to JavaScript. Now, when it comes to writing clean web code, there are tools that can help you make sure that you're adhering to common community standards. For example, 4 web code cleaning tools on the market are Code Cleaner, Code Beautifier, HTML Hint, and CSS Comb. So let's dive into each of these in a little bit more detail. First up is Code Cleaner. Now, Code Cleaner can be used for formatting JavaScript, HTML, and CSS code through a single click of a button. Formatting includes indentation and line formatting. For your indents, you can even choose whether to use spaces or tabs, and I recommend spaces, as well as how many. Now, the cool thing about Code Cleaner is that it has full support for the latest HTML5 and CSS3. Next, we have HTML Hint. Now, HTML hint is a tool that helps you to detect if there's any issues with your actual HTML code. Now, this can include attribute usage, missing elements, and more. One of the big advantages to HTML hint is that it's configurable. And that means you can tune it to detect issues that you care about, or not detect issues that you don't care about. Now, one of the most popular tools out there is Code Beautifier. It's been around a long time, and I've used it myself. Code Beautifier can be used to clean up your CSS. Now, it's super easy to use and has no frills or unnecessary features. But one of the cool advantages is that you can copy CSS from somewhere, and let's be honest, that's usually the internet, and paste it into your CSS file. And Code Beautifier will automatically and immediately clean it up. And finally, we have CSS Comb. Now, just like Code Beautifier, CSS Comb is for formatting CSS. It's an interactive tool versus something that just runs in the background. Now, CSS Comb is also highly configurable, so you can set up the types of rules you want, or don't want for that matter. It can also be used to quickly and efficiently configure colors in your CSS, which is actually, surprisingly, a difficult thing to do. And if you're like me, you always forget those dang semicolons in your CSS. Well, CSS Comb has you covered there, and it will automatically add them for you. So in this course, we've examined the importance and benefits of writing clean code and methods and tools for commenting and writing clean code. We did this by exploring the importance and challenges of writing clean code qualities, best practices, and benefits, preventing code bad habits, the cost of messy code, differences between clean and dirty and how to fix it, best practices for commenting code, and code cleaning tools. In our next course, we'll move on to examine the features of object-oriented programming in Java.
In this video, I'll present some of the key components of Java object-oriented programming and how it relates to Java. So Java is built around object-oriented programming. As a programming paradigm, objects are entities that have both state and behaviors and represent physical or conceptual things such as a cat, a chair, or a container to hold other objects. Classes are the blueprints of the objects created in memory that are instantiated or inherited from. Inheritance refers to the ability of an object to obtain the properties and behaviors of a parent object. For example, a dog class inherits the characteristics of a mammal class. In Java, we define classes that inherit from other classes. This encourages code reuse, modularization, and logical abstractions. What are some of the components that make up Java object-oriented programming? The first is polymorphism. This occurs when objects inherit a method from a parent class and gets overridden or overloaded with its own specific behavior. An example of this is a cat class and a dog class. They both inherit a speak method from a parent class. This speak method for the cat can be overwritten to display meow, and the speak method for the dog class can be bark. The next is abstraction. This refers to hiding the implementation details from the user and only providing functionality, and it's achieved by using the abstract classes and interfaces. Encapsulation is also known as data hiding, and it refers to classes providing access controls to the data inside of them, so it can limit outside access from other classes. What are some of the behaviors and aspects of Java object-oriented programming that deal with how objects interact in ways other than direct inheritance or abstraction? The first is coupling, which refers to the number of dependencies associated between multiple classes. Interfaces can be used to establish weak coupling. Cohesion refers to how relevant the data and methods are within a class. For example, the Java.io classes only have methods for performing input and output, but is considered highly cohesive. Association describes the relation between objects and can be one of the following: a one-to-one relationship, a one-to-many, a many-to-one relationship, and a many-to-many. From that, we get aggregation, which is a type of association that refers to a has-a relationship, where a class has an instance of an object, i.e., a person has an address. If that person moves, someone else can take that address. They exist independently. This is an important distinction relating to aggregation. Composition refers to a relationship where the association is a part of relationship. It's a strong form of association where the child entity or component cannot exist independently of the parent entity. What are some characteristics of Java object-oriented programming? Well, Java is considered to be a secure programming language because it does not permit arbitrary memory pointers and runs inside of a virtual machine sandbox. Components such as the class loader, bytecode verifier, and the security manager provide further security features and mechanisms to ensure safe code. Java is considered a robust programming language since it provides strong memory management, the absence of memory pointers, automatic garbage collection, and exception handling and type checking mechanisms. Java is considered architecture neutral since there are no implementation-dependent features such as the size of primitive data types, like an int, which can be different on different architectures and operating systems. Some more Java object-oriented programming characteristics are: the Java programming language is simple, it's easy to learn, and it's easy to get started due to its consistent object-oriented style. Java is compiled into bytecode rather than machine code, which runs on a Java virtual machine in a Java runtime environment on whatever local machine it's run on for code portability. Java virtual machines can run on multiple operating systems and environments, which allows Java to be platform independent. A few more important features before we finish up this presentation. Java supports multi-threaded processes and uses a common memory area with support for synchronized updates to critical sections between threads. Java supports the creation of distributed applications and allows for the use of remote method invocation, RMI. Java is a dynamic programming language and supports loading classes on demand, dynamic compilation, and automatic garbage collection. And that concludes this presentation on Java object-oriented programming. In this video, I'll present some of the features of Java objects, classes, and interfaces. Java is based on objects which are defined by classes and interfaces, and objects are entities in memory that have both state and behavior. Classes are blueprints of objects that can be both regular classes or abstract classes, which cannot be instantiated directly as an object. Interfaces are similar to an abstract class and do not contain any code, just descriptions of methods and features that must be implemented by classes that implement the interface. Classes can inherit more than one interface. Objects are entities in memory that have both state and behavior. Objects use their member variables to maintain state. For example, a cat may have a color, a name, and an eye color, a height and weight, as variables that describe the state of a cat. Objects can perform behaviors on the data contained within it or perform actions. For example, a cat object may be able to have methods to walk and speak defined by the class blueprint. Internally, Java objects have a unique object identity, which is used to internally identify it by the Java Virtual Machine, or JVM. Java classes are defined by their attributes, which are variables belonging to the class. Attributes can be primitive types like int, long, and double, as well as other objects. And methods, which are the actions that can be performed by the class and can make changes to the class's attributes. Abstract classes are a particular class type that cannot be instantiated. Abstract classes are a type of restricted class, meaning they can only be inherited by other classes. They cannot be used to create objects, though they can be used to reference objects that are inherited by the same abstract class type. Abstract methods contain a signature of a method, such as the name of the method, the return type, and parameters being passed to the method, but do not contain a method body on their own. The code body of an abstract method must be written in the classes that inherit from it. Abstract classes can define regular methods that have a code body, and these methods can be overridden by the classes that inherit it. Interfaces are similar to abstract classes, but do not and cannot contain any code implementations. They also cannot be instantiated by themselves to create objects. Interfaces are the blueprint of a class and contain the signature of a method such as the return type, method name, and the name and data types of any parameters. Interfaces are completely abstract or purely abstract. Interfaces can be inherited by a class, and a class can inherit more than one interface. And in Java, when a class inherits from an interface, we say that it implements the interface. And that concludes this presentation on Java objects, classes, and interfaces. In this video, I'll demonstrate how to create and run objects in Java. Well, to create and run objects in Java, we need to have a class with which to create the objects from. So I have open in IntelliJ helloU.java, a file I've created with a class called helloU. It starts out with a typical package declaration with package com.example. And I like to call it com.example for the sake of these demonstrations, but we don't need to worry too much about it here because both classes we have, this helloU and greet, are both inside of com.example. The important part here is I have a public class helloU. And this class will consist of the usual attributes and methods that belong to a Java class. So I start by declaring the attributes inside of the class. And in this case, there's only one attribute, private string u. And then I have two methods, public helloU. So since this method matches the name of the class, it's the constructor. So when we create helloU, it will call this method with the parameter string recipient. And then inside of this function, this constructor, I set u, the member variable. So the attribute of this helloU class, I set it equal to recipient, the parameter. The other method on line 11 is public void print hello. And what this does is print using system.out.println of hello, comma, space. So we have a string plus u plus the string with an exclamation mark. So it's fairly straightforward. It has very basic behavior with a constructor and a single method. And since the member u is declared as private, nobody outside of this class can access it. So it can only be set inside of the class helloU. Now I'll switch over to my other file, greet.java, which has the entry point for my application. So it's also in package com.example. It's declared as public class greet, and it defines a single function, the main entry point, public static void main, string double brackets args. And then inside, I create a helloU object called hello there. So helloU is the class, and hello there is the object, which we're going to instantiate. And we instantiate it by setting it equal to new helloU, and then in parentheses, we pass the arguments that get passed the constructor. And in this case, I put in the string there. So the recipient is there. So the result will be hello there. And then on line 7, I take the hello there variable dot print hello. So I call its member method, which will print the result. I create a second object on line 9 using the helloU class, and the object's called hello Bob, and I instantiate it with equals new helloU and the argument Bob, so the string Bob. And then on line 10, I call hello Bob.println. Now I'll use Shift F10 to compile and run the program. And then in the result, we have printed hello, comma, space there, exclamation mark. And then on the next line, hello, comma, space Bob, exclamation mark. Both of these printed by the print hello function inside of the helloU class. And that concludes this demonstration of programming Java objects. In this video, I'll present some of the features and ideas of Java inheritance. Inheritance is the ability of an object to obtain the properties and behaviors of a parent object. In practical terms, a Java class contains attributes and methods. A class that inherits gets the attributes and methods, plus it adds its own and can modify the methods if need be. Thinking of a real-world object, we can think in terms of classifications, categories, and types of objects. An engine, for example, that drives locomotion is implemented in different types of objects. Examples are a steam engine, an internal combustion engine, and an induction motor, which can be seen as classes that inherit from an engine. However, Java doesn't support multiple inheritance from classes. so I can't create a hybrid engine. In Java, I can't inherit both from the internal combustion engine and the induction motor at the same time. Although I can have a car class that has multiple engines as attributes, but that's a separate discussion. Interfaces are a type of class that define how a class should behave. Methods are defined, but not implemented. Interfaces can be inherited from classes, and a class can inherit from more than one interface. We call interface inheritance implementation. The extends keyword is used in a class declaration to indicate the class inherits from it. For example, steam engine extends engine. There's common terminology for discussing Java inheritance. The class, or classes, are groups of objects with common properties and logical entities that describe a blueprint that objects can be instantiated from. The primary components of a class are attributes and methods. A superclass refers to the class that it's extended from, also called the base or parent class. A subclass is a class that inherits from other classes. It's also sometimes called a child, derived, or extended class. Reusability refers to a class being able to make use of the fields and methods they inherit from a superclass. Logical separation and layout of entities is one goal of object-oriented programming in Java, but reusability is a concrete benefit to class inheritance. There are 3 different inheritance types in Java. The first is single inheritance, is when a class extends another class. The base class or superclass can be an abstract class or a regular class. Multi-level inheritance is a chain of inheritance with each subclass gaining the methods and fields of its parent classes. Hierarchical inheritance refers to multiple classes inheriting from a superclass. For example, an engine class can be extended to an internal combustion engine class and an electrical motor class. The internal combustion engine class can in turn be extended to a spark ignition gas or petrol class or a diesel engine class. The electrical motor can be extended to an AC class or a DC class. We end up with a hierarchy of inheritance, not just with a parent class, but now we get grandparent classes. And the overall inheritance can be described as a hierarchical tree. Java has 2 types of inheritance that can only be implemented using interfaces. Multiple inheritance refers to subclasses inheriting from more than one superclass. Java only allows a class to extend a single class. However, a class can implement many interfaces at the same time. Extending from a class and inheriting interfaces together is called hybrid inheritance. What are some considerations for inheritance in Java? An object class is the superclass of all objects and does not have a superclass itself. The object, spelled with an uppercase O from the java.lang package, is the base class of all base classes. You don't have to extend from it explicitly, it's always there by default. A superclass can have multiple subclasses. However, a subclass can only inherit from a single superclass. This is a direct result of being able to only specify one class in the extends clause when declaring a class. Constructors are not inherited from a superclass, but they can be invoked from the subclass. You can call your parent's constructor, if you need to. We also have to consider access modifiers. Declaring class members as private, so they aren't accessed directly by subclasses, but can still be accessed using getters and setters from the superclass. We can also declare members final, which means they cannot be inherited and changed by the subclass. And that concludes this presentation on Java inheritance. In this video, I'll demonstrate how to create and run classes that use inheritance in Java. In this example, I'm simulating writing to a log file. So I've created the structure with a log file base class and an HTTP log file class that inherits from this log file class. And I also have a main class with the main function as the entry point into the application. So I'll start by explaining the code in log file, move on to the implementation in HTTP log file, and demonstrate how it comes together in the main function, where we create and run the classes. So in logfile.java, I have package com.example. So all of these classes I create are in this com.example package. And then on line 3, I declare my public class log file matching the name of the Java file, logfile.java. And then in the body of the log file class, I have the attributes declared as private. So private string file name equals, so I set a default log file name to logfile.log, and then private string file path equal /var/log/. So standard log file location on most Unix or Linux systems. Then on line 7, I declare my constructor for the class public log file, which takes no arguments, so there's no parameters declared. And then what this does is print using system.out.println and the string default constructor to show if this default constructor is called. And then on line 11, I declare a second constructor, but this one declares 2 parameters. So I have public log file with string file name and string file path as its parameters. Inside of this log file constructor, I call system.out.println of the string parameterized constructor to show that this particular constructor is being called. I set this.filename equal to filename and this.filepath equal to filepath. So I change the values of the local attributes. And then on line 17, I have a function called writeLog, and it's declared as public void writeLog, and it takes a string line to simulate a log line being written to a log file. Now, I'm not actually going to carry out this log writing for the sake of this example, so we're not really writing to a file, we're just printing to the standard output so we can follow what's happening in the code. So on line 20, I have system.out.println, I take the file path string, and then I concatenate, so I have plus, file name, plus a string with space, hyphen space, and then plus line, the actual line of the log file. So this is for demonstration only, so we can see the results or see some activity happening when we run the program. Now, the HTTP log file is where we see the inheritance happening. So this is also in the package com.example, and this is declared on line 3 as public class HTTP log file extends log file. So it's a particular implementation or a particular type of log file, and it's extending the log file it came from. And since it's an HTTP log file, it will have its own attributes, like I have on line 4, where I declare private string site name. So there's a website name, like example.com. And this is particular to HTTP log files that wouldn't necessarily appear in other log files. And because HTTP log file extends log file, it gets all of its public and protected members, if there were any. So it can call the log file's constructors, and it gets a writeLog function inherited from log file. But since file name and file path are private, it doesn't have direct access to them. So inside of HTTP log file, on line 6, I declare HTTP log file's own constructor. So public HTTP log file, and it declares a single parameter string site name. And then it calls super. So super is a way of calling the superclass, the super constructor. So the parent's constructor, so log file's constructor is called using super, and then in parentheses, I specify the parameters to the log file constructor. And in this case, the file name is going to be the site name plus .log. So it's adding the string .log to the site name, and that's going to be the log file name. And the file path is going to stay at /var/log, which I pass as the second argument. Now in the main function in main.java, I declare a public class main, and I have the usual main entry point into the application. And in it, on line 6, I have log file log equals new HTTP log file, and I specify the site name, the string example.com. And then on line 8, I try to do something that's not allowed. System.out.println of log.filename. But filename is a private member, so I cannot access it. So this action is actually not allowed, and IntelliJ already flags it as a problem. It shows the error has private access in com.example.log file on line 8, so we can't access the file name directly, so I'll comment that line out using an end-of-line comment. I'll save it. And then on line 9, I have log.writeLog with the string index.html space hyphen space 200 to simulate an OK message from the web server that it's logging from, and some IP address that it's communicating with, 192.168.2.1. Now this is all simulated for the sake of this example, just to show how these things get built up. So now I'll press Shift F10 to compile and run the code. And in the result window, I get parameterized constructor. This is the string printed by the parameterized constructor in the log file. So it's the second constructor being called. The default constructor doesn't get called at all. And that's okay, it doesn't need to get called. And then the log line gets printed, /var/log/example.com.log -index.html 200 OK 192.168.2.1. And that's the expected result. There's a small change I'd like to make. On line 6, I have log file log equals new HTTP log file. Now, the interesting thing is that a base class log file called log can reference an instance created by new HTTP log file. But the reverse is not true. So I could do HTTP log file log, and that'll work fine, but I can't do HTTP log file log equals new log file. So the HTTP log file is a particular type of log file, and it can't refer back to its parent, its superclass. But the reverse is true. I can have the superclass, the base class, refer to an HTTP log file. And I can also create a log file. Since log file is not abstract, I can have log file log equals new log file and carry out the same operations. And in this case, if I run it as is now, it'll work fine. But the file name will be the default file name. So if I compile and run, in this case, in the output, I get default constructor, and /var/log/logfile.log is the log file path and name in this case, and then the line itself is the same. And that concludes this demonstration of programming with Java inheritance. In this video, I'll present some of the important features of Java polymorphism. What are the general forms of Java polymorphism? Well, the first is method overloading, where the parameters are different compared to the classes or superclasses implementation, and then method overriding. This is the main approach to polymorphism, where the name and parameters of the inherited method are the same as its superclass, but the implementation, the method body, is different and particular to the subclass. Method overloading has three main considerations: the different number of parameters, removing parameters or adding them, having different data types specified in the parameters, and having a different data type sequence, so the order in which the type parameters appear changes. What does this method overloading look like in practice? Well, in this example, there's a math class that has two methods with the exact same name, the sum method, but the parameters are different. When the math class is instantiated, the sum method that is called is dependent on the type and number of parameters passed into the method. Now, in both cases, they accept integers, but one sum method accepts two integers, a and b, and the other one accepts three integers, a, b, and c. So in the main method, we create the math object, math obj equals new math, and then obj.sum is called with 1 and 2 as its arguments, which would produce 3. And the second example has 1, 2, and 3, so it calls the second variant of sum, which produces the answer 6. What I would call the main or general form of polymorphism is when a subclass overrides a method that's implemented in the superclass, called method overriding. In this case, the parameter list in the subclass's method matches the declaration of the superclass's method in number of parameters, types, and in type sequence. It overrides the method but does not overload it. The access modifier of the overriding method cannot be more restrictive than the method in the superclass. For example, if the method in the superclass is public, then the subclass method must also be public. If methods are declared as private, static, or final, they cannot be overridden. What are some of the other details we need to know about Java's method overriding? The super keyword can be used to call the method of a superclass. This can also be used to call the constructor method of a superclass. This helps greatly in code reuse. A subclass can add functionality to a method without having to copy and paste the superclass's implementation. Instead, you can just call the superclass's implementation and then continue on with code in the subclass to implement its own additional details. Dynamic binding means binding overridden methods at runtime. When a regular class inherits from an interface or extends an abstract class, then it must override all of the abstract methods. However, if an abstract class inherits from an abstract class, it's not necessary to implement everything. Let's look at an example of how this works. In this example, there's a superclass called bird that has a move method with a default behavior for a bird, which is to fly, so it prints bird is flying. However, there's a penguin class that extends bird and overrides the move method. Since the penguin moves differently than the typical bird, when the penguin class is instantiated and the move method is called, the sentence penguin is walking is displayed. The penguin class overrides the default move method in the superclass. This is also sometimes called upcasting, and the output here is penguin is walking. However, polymorphism doesn't work on attributes, only on member methods. In this example, an animal class is created with a data member called number of legs, which has a default value of 4. Then I declare an octopus class extends animal, and it also has a data member called number of legs that has a default value of 8. When the octopus class is instantiated and cast to type animal, the value for number of legs is 4. So the output in this case is 4 and not 8, because polymorphism only considers member methods. And that concludes this presentation on Java polymorphism. In this video, I'll demonstrate how to create and run classes that use polymorphism in Java. I'm going to demonstrate method overriding from an abstract class. When a method is declared as abstract, it must be implemented in the subclass, unless that subclass is also abstract. Now in this case, I have an abstract class and an abstract method in it, and I'm going to use two different classes that inherit and implement their own functions. Let's have a look at this path.java file. I start with package com.example, where all of the classes that belong to this example are in com.example. Then on line 3, I declare an abstract class as public abstract class path. And path is going to declare public abstract double distance. So there's a distance function that returns a double that must get implemented by the classes that extend path. The first one I'm going to look at is circle path. So circle path is declared on line 3 with public class circle path extends path. And it has a single attribute, private double radius, a constructor as public circle path that takes a radius as an argument and sets this.radius equal to the radius passed into the constructor. Then on line 10, I have an annotation. So annotations are for informing the compiler or other tools the intent of the function. In this case, at override says that this function is overriding. It's a method override from its superclass. So public double distance, and it doesn't declare any parameters, and it can't. So if I tried to put a parameter in, it's going to complain because I'm not overriding the method correctly. So I can't overload the method. I can only override it. And then this function returns the distance of the path around the circumference of the circle. So it returns 2 times radius times math.pi. My next implementation is in rectangle path. So it declares it as public class rectangle path extends path. So this is going to be the distance around the perimeter of a rectangle specified by a width and height. So I have private double width, comma height. The constructor is public rectangle path with double width and double height as its parameters, and that sets this.width equal width and this.height equal height in the constructor. Then on line 11, I have my at override annotation, and then public double distance, which returns 2 times width plus height, the formula for the perimeter. And I'll put in a trailing comment, perimeter, just to make it obvious what I'm calculating. Now I'll switch over to the main class. In the main function, On line 6, I have path rect path equals new rectangle path, and the width argument is 3.0, and the height is 4.0. And then I call system.out.println with the string rectangle path and in parentheses perimeter, and then I concatenate rectPath.distance. And in this case, rectPath is of type path, so I'm using the abstract base class to refer to an object created by the subclass rectangle path. And then on line 9, I do the same thing with circle path. I declare an object of type path called circPath equals new circle path, and the radius I specify is 5.0. And then on line 10, I call system.out.println with the string circular path and in parentheses circumference, and I concatenate the call to circpath.distance. And now I'll use Shift F10 to build and run the program. And in the result, I get a rectangular path. The perimeter is 14.0, and the circular path, the circumference is 31.4159, and it goes out to a number of decimal places. So the key takeaway here is that when you have an abstract method in an abstract class, and you extend that class, you must implement the method. And that concludes this demonstration of programming with Java polymorphism. In this video, I'll present the main features of Java abstract classes. In terms of syntax, abstract classes are similar to regular classes, but cannot be instantiated by themselves. Abstract classes are restricted and can only be inherited from by other classes. You can declare a class that extends an abstract class, but they cannot be used to create objects by themselves. Abstract methods contain a signature of a method, such as the name of the method, the return type, and its parameters. When the abstract class is extended, the method body must be implemented by the subclass. Abstract classes can have their own regular methods that have implementation code, and these methods can be overridden by the classes that extend it. Java abstract classes have some fundamental rules of operation. The abstract keyword must precede the class keyword to declare it as abstract. Methods in an abstract class can either be abstract or non-abstract. Methods are regular by default and need the abstract keyword to declare them as abstract. Abstract classes cannot be instantiated as objects on their own. The subclass that extends it can be instantiated as long as it's not abstract itself. Now, a few more rules of abstract classes are that abstract classes can contain constructors, which is automatically invoked when the subclass is instantiated. Abstract classes can contain static methods. However, a method cannot be marked as both abstract and static at the same time. And abstract methods can contain methods that have the final keyword. A method cannot be marked as both final and abstract at the same time, and the final method cannot be overridden in the subclass since it's marked as final. So let's have a look at a couple of examples. The first one we have is an abstract bird class with the move method both declared as abstract, so it cannot be instantiated into an object by itself. Then the penguin class, which extends bird, has a move method, and in this case, the move method is required to have an implementation. And here, this method calls system.out.println with the string penguin is walking. In the main method, a new penguin object is created. However, we could not do new bird in the same way. And if you tried, the compiler would complain with an error because bird is abstract. And then on line 12, when the move method is called, the output would be penguin is walking if we were to run this code. In this example, I have another bird class declared as abstract, but in this case, the move method is not abstract, and it has an implementation. This class duck extends bird and gets the move method as it's implemented in bird, and it does not need to be defined inside of duck. It can be redefined if need be, but it's not forced like in the abstract case. Then in the main method, a new duck object is created, and the move method is called, calling bird's move. In this case, the output would be bird is flying if this program were executed. And that concludes this presentation on Java abstract classes. In this video, I'll demonstrate how to create and run classes that use abstract classes in Java. For this example, I'm starting in an abstract class defined in this document.java. And all of these classes are part of the package com.example. And then on line 3 of this file, I declare public abstract class document. So this can't be instantiated on its own. Objects can only be created through the subclasses that inherit from document. Now, document contains two private members, private string contents and private string file name. Because they're private, the classes that will extend from document won't have direct access to contents and file name. So I've created getters and setters for these two variables. So I have get contents, which returns string, and it returns the contents variable, and then set contents, which takes a string as an argument and sets this.contents equal to contents. And I do the same with file name. I have a getter, public string get file name that returns file name, and public void set file name that takes the file name as an argument and sets this.file name equal to file name. And then I declare an abstract method. So on line 23, I have abstract, public, void, display contents. So the idea here is we have a document. It has a file name and some contents of the file that are particular to the file type, and a function to display the contents of the file. Now, this is somewhat of a manufactured example to demonstrate how we can extend from an abstract class and implement an abstract method and access attributes that are in the base class even though it's abstract. So the first implementation is textDocument.java. So this declares a public class text document which extends document. It has a constructor public text document with no arguments, and it calls this.setFilename with the string untitled.txt. Now, if I had tried to say this.filename directly and set that equal to untitled.txt to try and set the file name through the member variable directly, the member variable from document.java, it would give me an error because filename has private access in com.example.document. So we can't access it directly, we can only access it through the setter. And because document is abstract and it has an abstract method, display contents, we must implement it. If I comment out the display contents function, I'm going to get an error. So public class text document extends document is highlighted in red. And if I select the current file, the errors, text document must either be declared abstract or implement abstract method display contents. The only way to extend an abstract class with an abstract method is either by implementing it or declaring the current class to be abstract as well. But in this case, I do want to implement display contents. And once I uncomment that code and have my implementation of display contents, everything is fine again. And what this function does is call system.out.println of getContents. So it just outputs the contents of the string from the contents member variable from document.java. Now, HTML document has a little bit more going on. It's declared as public class HTML document extends document, and it declares its own member variable private string header, like the header of an HTML page, and public document, the constructor, declares no parameters, and it sets a default file name with this.setFilename to index.html. On line 10, I have the @override annotation, which is an optional requirement. So I can put the @override in, or like in text document, I can leave it out, and it works just fine. And then I have public void display contents, system.out.println with an HTML tag in string. The next line, it prints the head tag. Then there's a println of the header. So the header is a special section of an HTML document that contains information such as the title and other meta information for the page. Then I print the closing tag for the head, the opening tag for the body, and then inside the body, I print the call to get contents, which calls get contents from document and gets the contents variable. And then I print the closing tag for the body and the closing tag for the HTML. And there's a getter and setter in this case for the header. So I have public string get header to return header and public void set header that takes the string header as an argument and sets this.header equal to header. Now let's have a look inside the main class and inside the main function. So on line 6, I have document HTML_doc equals new HTML document. I call HTML_doc.setContents with the p tag with the string this is in the HTML document, and then I close the p tag. And I call HTML_doc.displayContents. And then I do the same thing with text document. On line 10, I have document txt_doc equals new text document. Then I call txt_doc.setContents with the string this is in the text document. And then I call textdoc.displayContents. Now with Shift F10, I can build and run the code, and we can see the results. So if I scroll up in the results, I get some HTML information, and when I get to the header, it shows null, because I didn't set anything. Now it might be okay to have this text here, but it's a good idea to set a default value for a member variable inside of a class. Then I close head, and then open body, and then the p tag inside the body is this is in the HTML document. And then I close the body tag and HTML tag, everything that appeared in the display contents of the HTML document. And then in the text document, all it displays is the text that was set in the contents. This is in the text document. And that concludes this demonstration of programming with Java Abstract classes. In this video, I'll describe the main features of Java Encapsulation. Encapsulation is also known as data hiding and refers to classes providing access to the data inside of them through methods. I remember this definition by thinking of the word capsule and encapsulate to mean hiding something in a capsule. So encapsulation in Java involves wrapping the data and code together in a single unit into a capsule. If all the data members, all of the member variables or attributes of a class are declared as private, and the only way to get access to or modify it is through class methods, such as getter and setter methods, we say that the class is fully encapsulated. What tools do we have in the Java language to control encapsulation? The keywords for encapsulation are called access modifiers. A private access modifier is the most restrictive type. When used with an attribute or method, then it can only be accessed by a member method within the same class. Subclasses do not have access. Protected access modifiers allow the class, attribute, or method to be accessed by all classes in the same package and by all subclasses that inherit from this class. A public access modifier is the least restrictive and means the class, attribute, or method is available by all other classes. These are optional keywords. Classes, attributes, and methods can have no modifiers specified. In this case, these members are private by default. It's important to remember that private is the default access modifier. One of the more common Java design patterns for encapsulation is called the getter and setter methods. An attribute is created with a private access modifier, which hides the attribute from other classes. Then a public setter method is created to be used to modify the attribute, and a public getter method is created to read the value of the attribute. When all attributes are encapsulated this way, it makes it fully encapsulated by design. Let's look at an example. So we have a class duck, and it has a private string name, so it's a hidden value. It has a public string getName, which returns a name, and a public void setName method that takes a new name and modifies or replaces name with the new one that's passed in as an argument. And then in the public method, here we have duck. On 14, we have the duck class with an instance called duck in lowercase equals new duck. We call duck.setName to Daffy, and then system.out.println has to use getName to get the property from duck to get its name. So in this case, duck is fully encapsulated. Using encapsulation in Java has several advantages. We get data hiding. Classes that access the hidden data do not need to worry about where or how the data is stored. They just need to use the getter and setter methods to retrieve the data that's hidden. Variables in a class can be set up to be read-only or write-only. If there's only a setter method, then the variable becomes write-only. If there's only a getter method, then the hidden variable becomes read-only. Encapsulation allows classes to be easily reused without having to worry about the code inside the class. Often the inner attributes of a class can change in name or type without having to change the public methods of the class. Encapsulation also makes it easy for unit testing. You don't have to worry about accessing every attribute, just the public methods to get full coverage. And that concludes this presentation on Java encapsulation. In this video, I'll demonstrate how to create and run classes that use encapsulation in Java. Another word for encapsulation is data hiding. It's a layer of separation between our attributes and the outside world. In this example, I've created a class called greet inside of greet.java, which starts with package com.example to put it in this package. And then on line 3, I have public class greet. And inside of this class, the first thing I do is create my data members, my attributes, private string greeting and private string recipient, which means nobody from the outside world has direct access to these private members and can only access it through the member methods. One way of accomplishing what we call full encapsulation, where all of our data members are declared private, like we have here, is by using getter and setter methods and other helper methods. Next, this greet class has a single constructor, public greet, that doesn't take any arguments. All it does is set our greeting and recipient member variables to their default values. On line 8, I have greeting equals hello and recipient equals world. Then I have a number of methods. The first is print greeting. So public void print greeting is how it's declared. And all it does is call system.out.println with greeting, followed by a comma and a space, followed by recipient, and then it concatenates the exclamation mark at the end. Then I have a number of setters and getters. I have a combined setter that sets both greeting and recipient, and it's declared as public void set greeting recipient, then takes two arguments, string greeting and string recipient. I set this.greeting equal to greeting and this.recipient equal to recipient inside the body of the function. And then we have a number of getters and setters. So get greeting returns greeting, then set greeting is public void set greeting string greeting, and it sets this.greeting equal to greeting. And then I have a getter for recipient declared public string get recipient and return recipient in its body. And then on line 33, public void set recipient takes a string recipient as an argument and sets this.recipient equal to recipient. Now that's a lot of typing if you were to type out all the getters and setters for a given class, especially if it has a lot of attributes. One thing that IDEs like IntelliJ do is that if you select one of the members, let's say greeting, where it's declared, right-click and say generate, it gives you options to create getter and setter methods. And that's what I've done here to generate the code below. So it's much easier, much quicker to auto-generate the code if you can, than to have to type out every getter and setter. Now I'll switch over to main.java, and inside of the main function in the entry point to the application, I start by creating an instance of greet with greet message equal new greet. And then I call message.printGreeting, which will print the default greeting. So the default values for greeting and recipient. Then on line 9, I test message.setGreeting and I change the greeting to hi. I call message.printGreeting again to see the change. On line 12, I change the recipient by calling the recipient setter message.setRecipient with string Steve, and then message.printGreeting to see the change. And then finally, I check the combined setter with message.setGreetingRecipient, and I pass in goodbye and recipient Mallory. And then on line 16, I call message.printGreeting. Now I'll use Shift F10 to build and run the code, and we'll examine the results. So the first print greeting is hello world. Then I set the greeting to hi and reprint it, which gives me hi world, then hi Steve, and finally goodbye Mallory as expected. And that concludes this demonstration of Java encapsulation programming. In this video, I'll demonstrate how to create and run classes that use inner classes in Java. So I have an example here called outer for the outer class. So in outer.java, I have a package com.example, and I define a class, public class outer. So this is obviously the outer class, and just inside of it, I have a class defined public class inner. So inside of the body of the outer class, we define a class, and that class belongs to and is defined within that outer class. And everything inside in the inner class looks like a regular class definition, but its access modifiers have an additional layer of control. So if the inner class is defined as private, it changes it dramatically. But if I want some access from the outside into the inner class, I need to declare it public. When defining an inner class, it usually means that the outer and inner classes are tightly coupled and their objects depend on one another. So here's how I define the inner class. So I have public class inner, and then it has an attribute private final string message. It has a constructor public inner, which takes a string message as a parameter, and then it sets this dot message equal to message. It also defines a toString method with public string toString and returns message from the inside plus message. So that defines the whole inner class. The outer class has a couple of helper functions to let us interact with the inner class. And these helper functions are essential if the inner class is private. So the only way to get access would be through public methods inside of the outer class. So on line 15, I have public string get inner message, and it takes a string message. So it creates an inner class object, inner in equals new inner, with message passed to the constructor, and then it returns in.toString. The next function is public inner, so it returns an object of inner type, get inner, and it takes string message because the inner class requires the string message to be passed to actually instantiate the object. And this returns an instance of new inner with the argument message. Now let's see how this gets invoked from the main method. So in the main function, in main.java, I have outer out equals new outer, so I create an instance of the outer class, and then I have system.out.println of out.getInnerMessage with the string passed hi Steve. On line 9, I access the inner class directly, and I get an instance of it by calling getInner. So I have outer.inner in, so this is an object of type inner equals out.getInner of hello world. And on line 10, I do system.out.println of in. And accessing in this way is fine because by default, passing it to the println statement will call in's toString method by default. And then on line 12, I have a comment. This can only be done if inner is static, because on line 13, I have outer.inner into equals new outer.inner with the string test. But because inner is defined within outer, it can only be accessed if there's an actual outer object. The only way we can create a new instance of inner, which goes through outer, is if we have inner defined as public static class inner. And if I save it and go back, now this line is fine. Static allows for the instantiating of the object from the inner class directly. However, if you need this behavior, then you should really look at whether the inner class needs to be an inner class, or whether it can exist separately on its own. So it's probably not a good practice to access inner classes this way. So I'm going to comment out line 13 and save it and go back to outer.java and remove the static modifier on our class inner. So it works as it did when I started the video. Now, if I go back to main, I'm going to type Shift F10 to run the program. And in the result, I get the first message from inside, hi Steve, and message from the inside, hello world. So it behaved as expected. And that concludes this demonstration of Java inner class programming. In this course, we've examined the features of object-oriented programming in Java. We did this by exploring features of Java objects, classes, and interfaces, creating and running objects in Java, features of Java inheritance and programming, features of Java polymorphism and programming, as well as Java abstract classes, features, and how to program, Java encapsulation features and how to program, creating and running inner classes in Java. In our next course, we'll move on to cover the importance of design patterns as well as types of patterns such as behavioral, creational, and structural design patterns.
In this video, we'll consider the importance of design patterns. Design patterns are essentially typical software solutions that we would normally apply to common problems related to object-oriented software design. Design patterns point to higher-level descriptions of solutions, not to be confused with algorithms. Both describe typical solutions to some type of known common problems, and while an algorithm sets out a clear group of actions to achieve some objective, they're not the same. Again, a pattern is typically a higher-level description of a solution. For example, you can apply the same pattern to different programs, and it's possible that the code for each one is quite different. The pattern does not represent a specific set of code. Rather, it's a broad concept geared towards solving a particular type of problem. Each design pattern is a blueprint that is fully customizable to solve a design problem specific to our program or in a different context. In fact, design patterns have been described very succinctly as a solution to a design problem in context. So solution, problem, context. Design patterns are very important, and because of that, you'll find that most patterns are described in a very formal way, opening the door to others to reproduce them in different contexts. Typical sections used to formalize a pattern description include the intent of the pattern. The intent provides a brief description of both problem and solution, and answers the question, what problem does the pattern address? For example, the Singleton design pattern solves problems like, how can we ensure that a class only has one instance? And how can the solitary instance of a class be accessed globally? The motivation section explains the problem and solution typically by using a scenario that illustrates the problem. It's the motivation behind the pattern. The next section, the structure of classes, displays each component of the pattern and how they are all related. In a formal description, this is typically a diagram using object modeling technique, or OMT. Then, of course, there is the code example, and you'll typically find these in one of the more common programming languages, including Java. The code examples are awesome for helping illuminate the concept behind the pattern. You may also find other helpful details in some pattern catalogs discussing implementation steps, the relationship amongst patterns, as well as other details. So, we've established that patterns are typical solutions to common problems in object-oriented software design. But where do they come from? Solutions usually get applied over and over in different projects and in different contexts. Eventually, someone decides to give it a name and describe the solution in detail. But the concept of pattern language was itself first described in a book about a language for designing the urban environment. That was the concept that inspired 4 authors known as the Gang of 4: Eric Gama, John Velicities, Ralph Johnson, and Richard Helm. In 1994, they published Design Patterns, Elements of Reusable Object-Oriented Software, and it was in this book that they applied the concept of design patterns to object-oriented design. The original book featured 23 patterns solving various problems related to object-oriented design. Other object-oriented patterns have been discovered since then. Now, why are patterns important? Even if you weren't aware of specific patterns, the fact is that you may already be applying one, because a design pattern is just that. It's a pattern. And even from personal experience, I've applied several specific patterns before knowing and acknowledging that they even existed, as it were. Why would patterns be considered important if, for example, you're already unwittingly applying them? The thing is, until formally recognized and documented, a design pattern isn't formally recognized and documented. The act of formally recognizing and documenting solutions lends credibility to the solution. In fact, design patterns can be seen as another tool in your developer's toolkit, a collection of tried, tested, and proven solutions to common problems in software design. And they just work. Even if you never encounter problems associated with some patterns, understanding patterns is still valuable since it teaches one how to solve many different types of problems using object-oriented design principles. Design patterns enhance communication amongst developers, as design patterns define a common language to describe solutions to problems within a specific context. Basically, patterns enable us to communicate more efficiently and effectively. For example, you could just say to a developer on your team, use an iterator for that. And you know that the concept behind the suggestion is understood. You needn't explain what the iterator is about if you both know the pattern and the name. All patterns can be grouped or categorized by their intent, their purpose. We have three main groups of patterns. We have creational patterns, which are concerned with object creation mechanisms that improve the flexibility and reuse of existing code. We have structural patterns, which explain how to assemble objects and classes to create larger structures, while at the same time ensuring that the structures are flexible and efficient. And finally, we have behavioral patterns, and these focus on the interaction between objects, promoting effective communication and assignment of responsibilities amongst objects. Those who choose not to use patterns, ironically, follow a specific pattern of beliefs. For example, some detractors of patterns say that patterns are just so much duct tape to fix up a weak programming language. This is not entirely untrue. The need for patterns typically surfaces when a programming language or technology does not supply the necessary level of abstraction. Some patterns are just overused when in fact simpler, more performant solutions are available. And since patterns essentially formalize approaches that are already widely used, patterns can be used incorrectly by developers when they steadfastly stick to a specific pattern blueprint without taking into account the fact that they should probably adapt it to their own specific context. And then there's just unwarranted use of some patterns. Many beginners and novices who've become acquainted with patterns may be tempted to apply them everywhere. This is not advisable because there are situations where simpler code is the optimum solution. In this video, we'll explore behavioral design patterns. Behavioral design patterns are concerned with the interactions between objects. Behavioral patterns promote effective communication and assignment of responsibilities amongst objects. With behavioral design patterns, the interaction between objects should be designed such that objects can easily talk to each other and still remain loosely coupled, which essentially means that the implementation and the client are loosely coupled. We must avoid hard coding and dependencies. The first behavioral design pattern we'll look at is chain of responsibility. This pattern allows us to pass requests to a chain of request handlers. When receiving a request, each respective handler chooses either to process the request or to pass it to the next handler in the chain of responsibility. Next is the command pattern. This pattern allows us to take a request and transform it into an object encapsulating all the information about that request. We can use this pattern to parameterize clients and perform some actions, for example, queuing or delaying the execution of a request. Next, the mediator pattern allows us to effectively diminish the chaotic dependencies that exist between objects. Basically, this pattern restricts direct interaction between objects and instead forces objects to collaborate via a mediator object only. And the iterator pattern sets up the traversal over the elements of an object, but without exposing its underlying representation or structure, be it list, stack, tree, or what have you. Next, the memento pattern. This allows us to save and restore the state of an object without exposing the details of the object's implementation. The observer pattern allows us to define a subscription-based process which allows an object to notify observers of any state changes that occur. And the interpreter pattern basically defines how to represent the grammar of a language and includes an interpreter that can use that representation to interpret sentences in that language. The template method is a behavioral design pattern used to define the skeleton of an algorithm in an operation, with some steps being deferred to subclasses. The template method allows subclasses to redefine some steps of an algorithm without altering the structure of the algorithm. The state pattern allows an object to change its behavior when the object's internal state changes. This gives the appearance that the object changed its class. Basically, the state pattern solves the problem: how can we make behavior dependent on state? And the strategy pattern. This allows us to define a set of algorithms that may be used interchangeably. The strategy pattern allows the algorithm to vary independently of clients using it. In essence, this pattern defers the decision about which algorithm to use until runtime. And this in turn means the calling code can be designed to be more flexible and reusable. The visitor pattern allows us to isolate algorithms from the objects that they operate on. As a result, new operations may be added to existing object structures without altering the structures themselves. And the null object pattern describes the uses and behaviors of null objects. Rather than using a null reference to signify the absence of an object, the null object pattern uses an object which implements the expected interface, but the method's body is empty. One of the main advantages of this type of approach is that a null object becomes predictable. It does nothing, and hence it can have no side effects. In summary then, behavioral design patterns are focused on the interactions between objects, and behavioral patterns promote effective communication as well as the assignment of responsibilities amongst objects. And with behavioral design patterns, the interaction between objects is designed so that it's loosely coupled. And that means that the implementation and the client should also be loosely coupled, avoiding hard coding and dependencies. In this demo, we'll implement an iterator design pattern. To start my demo, I've opened IntelliJ and I have a project named Behavioral Patterns open. The base package here is com.local.iterator. So that's where I'm developing this iterator implementation. Okay, so first, iterator demo. On line 3, I import Iterator from java.util. And then on line 9, this is where I'm getting an instance of a class called course repository. and that instance is called repository. So that's on line 9. Now on line 11, I'm just printing out a message saying, let's add some courses. Then lines 12 through 15, I'm calling the add course method to add courses to the repository. Now on line 17, this is where I'm getting an instance of the iterator. Then line 19, I'm printing out a message indicating let's iterate over the courses. So I have two messages here that I want to use to separate out what I'm doing. So first, I'm adding courses. Before I add the courses, again on line 11, I'm printing out a message. But then again, when I iterate over the courses after adding them all and using the iterator, I want to print out a message indicating that we're going to iterate over the courses. So on line 20, the conditional statement is calling the hasNext method on the course iterator. This is testing the condition that we're at the end of the collection. Further on down in the code, from lines 24 through 26, I'm using a for each loop to demonstrate how convenient it is to be able to iterate over a collection with the for each loop. Now, over in course repository, again, importing java.util.iterator. But then on line 5, we're implementing the iterable interface. Upon implementation of an interface, we override all of its methods. I do that later on down in the code, so we'll have a look shortly. Lines 7 and 8, I set up variables to work with. Then on line 10, I'm initializing the course repository with a default size and index. Then from lines 15 down through 25, this is the add course method. It's passed in a course. Then a conditional statement on line 16 looks to see if we're at the end of the courses array. And if we are, then we'll add a new item by defining a new array. And I do that on line 18. The new array is named more courses, and it's an array of string values, and its length is the length of the original courses array plus 1 for the course we're going to add. It has a length of 0. We're going to add 1 to it, so it's going to have a length of 1, and that 1 will be the course that's passed in to the add course method here. Now we can conveniently use array copy. We're doing that on line 19 to copy the arrays. So basically, it's a way to recreate the old courses array with the new course that is temporarily stored in more courses. So that's why in line 20, I set courses back to the larger more courses. Then I set what was the temporary more courses array to null. Then on line 23, I set the element in the courses array at the index value to the value of course that was passed in to the add course method. Then on line 24, I increment the index after the operation. Line 27 starts the overrides. So we override the iterator method, the hasNext method, and the next method. On line 29, I'm creating an instance of an iterator. And this iterator will be passed back to the calling program to allow it to iterate over this collection. The hasNext method on line 34 returns a true or false based on the current index. So if the current index is less than the length of the current courses array, that means that it does have a next element. Then, on line 39, the definition of the next method, which just returns the element at courses at the current index, and then after that operation, increments current index. So that's why the double plus is after the current index. And then on line 43, returning the iterator. All right, so let's go ahead and try this out. I'll select Run in the toolbar. Now I'll resize the console area so that we can access the full output. The message appears. First, let's add some courses. Then 4 courses are added. Then another message, now let's iterate over the courses. So at this point, the collection has values in it. So it should output the exact same courses that it output while it was adding them. And it does. So now let's go back to the Iterator demo and take a look at lines 19 through 22. So in lines 19 through 22, we have the now let's iterate over the courses message. And then the iterator iterated over the collection using hasNext to determine if it's at the end of the collection. And then with each iteration on line 21, prints the value of the collection item that is represented by course iterator.next. Now we can do the same thing with the for each loop. However, I won't get the second message indicating now let's iterate over the courses. So that's a good test. We should see if it's different. So I'll highlight lines 19 through 22, Control / to comment them out. Now I'll highlight lines 24 through 26, Control / to uncomment them. Now I'll select Run from the toolbar again. Now I'll resize the console again so we can access the full output. And sure enough, there's the first message. Then the 4 items being added. And then this time we don't have the header indicating that now let's iterate over the collection. But it did output the elements in the collection. And so with that, we've successfully implemented an iterator pattern. In this video, we'll explore creational design patterns. Creational patterns provide various mechanisms concerning the creation of objects. One benefit is increased flexibility as well as code reuse. So these patterns then are focused on how objects are created. Creational patterns are used when a decision must be made during the process of instantiating a class or during the creation of an object of a specific class. In Java, an object is typically created using the new keyword. With creational patterns, rather than instantiating objects directly using the new keyword, we can create objects in a more flexible way, deciding which objects are required for a particular use case, while at the same time hiding their creation logic. The first pattern that we'll discuss is the Singleton pattern. The Singleton pattern is one of the simplest design patterns in Java. This pattern involves using a single class whose responsibility is to create a sole instance, that's one single instance of an object. With this pattern, a class must ensure that only a single instance is created, and further, that it can be used by all other classes. In other words, that it's globally accessible. There are 2 forms of Singleton design pattern. First, lazy loading or lazy instantiation, which defers creation of an instance until such time that it's required. And then there is early instantiation or eager loading, which involves the creation of an instance at load time. This carries with it a performance hit, particularly on larger systems where you could have as many as thousands of instantiations at load time. Next, the prototype creational design pattern provides a way for us to copy existing objects without making our code dependent on their classes. The prototype pattern effectively delegates the process of cloning to the objects that are being cloned themselves. The pattern declares a common interface for all objects that support cloning. The common interface allows us to clone an object while managing to keep our code decoupled from the class of that object. Typically, an interface like this contains a sole cloning method. In all classes, the implementation of the clone method goes something like this. The method creates an object of the current class and then brings all the old object's field values over to the new one. An object supporting the cloning process is known as a prototype. When objects have several fields and large numbers of possible configurations, cloning them may in fact be the most effective and efficient approach to creation rather than subclassing. The factory design pattern provides an interface for creating objects in a superclass, but it allows subclasses to alter the type of objects to be created. In the factory pattern, we can create an object without exposing its creation logic. The new object can be accessed using a common interface. The factory method provides an approach for replacing direct calls to constructors using the new operator with calls to a special factory method. Under the hood, the objects are still created via the new operator, but the new operator is called from within the factory method itself. Objects returned by a factory method are typically called products. The abstract factory is a pattern that allows us to create families of related objects, but without the need to specify their respective concrete classes. Abstract factory patterns represent a type of superfactory which effectively creates other factories. This is why it's also known as a factory of factories. An interface is responsible for creating a factory of related objects, deferring the instantiation to subclasses. The abstract factory pattern is typically used when you want to group a collection of factories together. The builder pattern lets us construct complex objects in a step-by-step fashion. This pattern allows us to create different types and representations of objects using the same constructor. The builder pattern proposes that the object construction code be extracted out of its own class and moved to separate objects known as builders. The pattern organizes the construction of an object into a set of steps. To create an object, you simply execute a series of steps on a builder object. One important thing to note about builder design pattern is that you needn't call all of the creation steps. Instead, you can call only those steps that are required to produce a specific configuration that you're looking for. It is possible that some of the construction steps may require different implementations to build various representations of a product. In this scenario, we can create several different builder classes that use the same set of building steps, but in a different manner. We can then use these different builder classes to produce different types of objects. In software design, performance is typically one of, if not the key issue, and object creation can be a costly step. The intent of the object pool pattern is to reuse objects that are typically expensive to create. An object pool is essentially a container holding a specified number of objects. When an object is borrowed from the pool, it won't be available in the pool again until it's put back. Thus, objects in the pool have a specific life cycle: creation, validation, and destruction. A pool can help manage available resources in a more efficient way. But the main advantage of the object pool design pattern is that it boosts application performance considerably. And it's most effective in scenarios with a high rate of initialization. In this demo, I'll implement the Singleton design pattern. Okay, to get started, I've opened IntelliJ. Now on the Welcome to IntelliJ screen, I'll select New Project. I'll select Next. Now I'll check the Create Project from Template checkbox. Select Next. Now I'll specify the project name. I'll call this project Creational Patterns. And note that base package is already filled in for me. Now this is filled in only because I've already created a singleton and I had it in this base package. So IntelliJ remembered that and filled the base package for me. So I'm just going to leave it and select Finish. And now IntelliJ prepares my workspace and loads the project. And the main.java file is opened in the editor. Okay, so over in the project tree, I'll expand the project, then Source, then I'll right-click the base package, point to New, and select Java class. In the New Java class dialog, for the name, I'll specify my singleton, press Enter, and now I have the shell of my singleton class. Okay, so let's press Enter a couple of times to create some space in my singleton class. Okay, and on line 5, I'll enter a comment about early loading an instance. Then on line 6, I'll use private static my singleton instance equals new my singleton. So this will instantiate a new instance for me. Now I'll press Enter a couple more times. And now on line 8, I'll specify a private constructor. So that's private my singleton. Okay, and now I'm creating this private constructor here so that no one will be able to create new instances of this class. Now essentially, because we define this private constructor like this, the new keyword won't be available to create another instance. We can, later on, return the instance to the calling class when the getInstance method is invoked. Now I'll press Enter a couple more times, and now I'll specify a public getInstance method. And this is going to allow me to maintain control over how I want to return the singleton. Now we're going to use the conventional getInstance method, which is standard when implementing a singleton. This just returns the instance created earlier on line 6. Okay, now let's select the main.java tab. Now, over in the project tree, I'll right-click main, my main class. I'll point to refactor, select rename, and I'll specify my singleton demo to rename this class. And I'll select refactor and done. Okay, so now I have my singleton demo class. So I'll highlight the comment, write your code here on line 6. Now I'll start writing my code. So first, let's just see if I can use the new keyword to create a new instance of the my singleton class. And notice that my singleton is underlined in red. If I hover over my singleton, the information pop-up tells me that my singleton has private access in com.local.singleton.mysingleton. Okay, so now let's backspace over that And now I'll just specify my singleton dot get instance. So I'm going to call the get instance method from here. Now I'm going to output that. So I'll type system.out.println instance on line 7. Press enter a couple more times, and on line 9, I'll specify a comment about grabbing another instance. So I want to grab another instance to see if we get the same instance of the singleton back. So I'll type my singleton new instance equals my singleton dot get instance. Right, so new instance. And now I'll print that out. System.out.println new instance. Now I'll right-click main, select run, and now in the console, the system.out.println printed the object to the console for both instance and new instance. And note that they're identical. Now, we've been successful to this point creating the singleton pattern, but it's early loaded, and I want it to be lazily loaded. So let's go back into my singleton. And now on line 6, basically, I want to lazy load the new instance. So I'll change my comment on line 5. And then on line 6, I'll backspace over new my singleton and specify. And now down in the getInstance method, I need to handle the fact that this is now a lazily loaded instance. So I'll type if instance equals null. Then I'll specify instance equals new my singleton, right? We'll create a new singleton. If it's null, obviously one doesn't exist. If it does exist, then it's not null, so I'll just return that instance. Okay, so now I'll right-click main again. Over in my singleton demo, I'll select run main from the context menu, and the output to the console again confirms the fact that we have one instance. All right, so we've successfully implemented a singleton design pattern. In this video, we'll explore structural design patterns. Structural design patterns describe how to assemble objects and classes into larger structures while at the same time managing to keep these structures flexible and efficient. In other words, structural design patterns are focused on how classes and objects can be composed to form larger structures. The structural design patterns can simplify structures by identifying relationships, and the patterns themselves are concerned with the way that classes inherit from each other and how they are composed using other classes. First, let's consider the adapter pattern. This pattern provides a way for objects with incompatible interfaces to collaborate. You can create an adapter, which is a special object that converts the interface of one object so that another object can talk to it. An adapter wraps one of the objects in order to hide the complexity of conversion, and the wrapped object doesn't even necessarily have to be aware of the adapter. For example, we could wrap an object that works with imperial measurements like cups, quarts, ounces, and so on with an adapter that converts all of the data to metric like milliliters, liters, grams, and kilograms. Sometimes, as in the example I just cited, it's possible to create a two-way adapter that can convert the calls in both directions. A bridge is a structural design pattern that can be used to split a large class or a group of closely related classes into two separate hierarchies, abstraction and implementation. And these can be developed independently of each other. A bridge pattern can be used to decouple functional abstraction from implementation such that these two separate hierarchies can vary independently. The bridge pattern therefore enables the separation of implementation from the interface, which improves extensibility and can hide implementation details from the client. Next is the composite design pattern, and this pattern allows us to compose objects into tree structures and then allows us to work with these structures as if they were individual objects. A composite pattern defines class hierarchies that contain primitive and complex objects, and they make it easier to add new kinds of components and provide structural flexibility with a manageable class or interface. The decorator structural design pattern lets us attach new behaviors to objects by placing them inside special wrapper objects that themselves contain the desired behaviors. Extending a class is typically the most common approach to altering an object's behavior, but inheritance is not perfect. Inheritance is static. That is, you cannot change the behavior of an existing object at runtime. One can only replace the object itself with another one created from a different subclass altogether. Subclasses may also only have a single parent class. In most languages, inheritance won't allow classes to inherit behaviors from multiple other classes at the same time. One way to overcome these limitations is by using aggregation or composition rather than inheritance. Aggregation and composition work almost identically. One object has a reference to another and delegates some work to it. To summarize, with this pattern, an object can use the behavior of various classes, has references to multiple objects, and can delegate various kinds of work to them. And the facade pattern. This structural design pattern provides a simplified interface to a library, a framework, or any other complex group of classes. Basically, a facade is a class that offers a simple interface to a complex subsystem, typically containing a lot of moving parts. Although a facade may actually provide limited functionality when compared to working with the subsystem directly, it only includes those features that clients actually care about. A facade is particularly helpful in situations where you need to integrate an app with a complex, sophisticated library having a large number of features, but you only need a handful of those features. The flyweight pattern allows one to fit more objects into available RAM, and this is accomplished by sharing common components of state between multiple objects rather than storing all the data in each object. The flyweight pattern proposes to stop storing extrinsic state inside the object. Instead, this state is better passed to specific methods that rely on it. Only the intrinsic state should reside within the object, allowing us to reuse it in different contexts. Consequently, we'd require fewer of these objects because they differ only in their intrinsic state, which has far fewer variations than extrinsic state. Proxy. Proxy is a design pattern whose intent is to provide a substitute or placeholder for another object. A proxy has control over access to the original object, allowing one to perform some action either before or after the request is made against the original object. The proxy pattern proposes that a new proxy class be created with an identical interface to the original service object. Then the app is updated so that it passes the proxy object to each one of the original object's clients. When a request from a client is received, the proxy creates a real service object and subsequently delegates all the work to the service object. The benefit here is that if you need to execute something either before or after the primary logic of the class is encountered, the proxy can accomplish this without changing that class. Because the proxy implements the identical interface as the original class, it can be passed to any client expecting a real service object. In this demo, we'll implement the adapter design pattern. Recall that the adapter pattern works as a bridge between two incompatible interfaces. In this scenario, we have a client that works in imperial measurements, but we work in metric. We want to be able to interface with the client so that they can purchase wine in bulk from our store. Now, we could change the app, but the point of the demo is to show how we can work with incompatible interfaces. So we'll assume, for the sake of this demo, that we cannot alter the client system, and we want to maintain our own system as it is because it's integrated into several other client systems, and we don't want to risk breaking something when a quick and easy adapter pattern will do the job. Here in IntelliJ, I've got my project open. Now, the first file to look at is the client class. Now, this class simply is going to act as a client to complete the demo. All the work here takes place on lines 6 and 7, where we're grabbing an instance of the wine in gallons imperial class, and then we're calling the purchase wine in gallons method. Okay, so now the wine class is a functional class that calculates the price of the wine. Now, it calculates this price based on liters. So that's why we're going to implement the adapter design pattern. Okay, carrying on, the wine in liters interface is an adaptee interface. The adapter class converts the incompatible interface of the class, the adaptee, into another interface that the target client requires. Now, the wine in liters class is an implementation of the adaptee interface. On line 3, this class implements the wine in liters interface. Now, in the wine in gallons interface, this is the target interface. This is the interface that the client wants to target. And then we have wine in gallons imperial class. This class extends the wine in liters class, and it implements the wine in gallons interface. So it's here that we actually do the conversion. So yes, this is a very simple example, but it does the job, because what we'll see is that we'll be able to specify gallons. So over in my client class on line 7, we're setting up to purchase 10 gallons of wine. Okay, so let's run this and see what happens. So I'll click the run icon on the toolbar. All right, so the application told us that we're purchasing around 38 liters of wine, that the order today is $757.62 roughly. I didn't bother to round off this dollar figure. And then we thank the customer for their order. Okay, so we've successfully implemented the adapter design pattern. In this video, we'll explore design anti-patterns. Anti-patterns, similar to their corresponding design patterns, define an industry-wide vocabulary that describes the common defective processes and implementations of organizations, a higher-level vocabulary, as it were. When implemented effectively, a higher-level vocabulary tends to simplify the communication amongst people in the software industry which facilitates concise and articulate description of higher level concepts. In other words, people in the software industry can understand each other better with a common higher level vocabulary. An anti-pattern simply describes a common solution to a problem, but that solution generates negative consequences, so it's not really a good solution. Anti-patterns can sometimes be the result of managers or developers just not knowing any better, or it could result from them lacking sufficient knowledge or experience in solving a specific type of problem. Or anti-patterns can also result from managers or developers applying an excellent design pattern in the wrong context. Anti-patterns themselves offer real-world experience in the recognition of recurring problems in the software industry, and they also provide a detailed solution for the most common difficulties. Anti-patterns focus on the most common problems in the software industry and offer the tools to enable one to recognize these problems and, further, to uncover the underlying causes to begin with. One of the key objectives of anti-patterns is to describe useful approaches to software refactoring. Software refactoring itself is a way to modify code in order to improve the software's structure and long-term maintenance. The first design anti-pattern that we'll consider is the poltergeist anti-pattern. Poltergeists are classes with very limited roles and similarly limited effective life cycles. They usually start processes on behalf of other objects. The refactored solution includes reallocating responsibilities to longer-lived objects, thereby eliminating the poltergeists. You've got to love some of these names. And the next one is a boat anchor. And this is a unit of software or hardware serving literally no useful purpose on the current project. It's very ironic, but it's also very common to learn that what is considered a boat anchor in an organization turns out to have been a very expensive acquisition, probably the reason why the organizations tend to hold on to it. A golden hammer is a familiar technology or concept that seems to be enthusiastically overapplied to several software problems. The solution with this anti-pattern involves expanding developer knowledge via multifaceted education and training to help developers understand alternative technologies and approaches. A dead-end anti-pattern describes a situation where a dead end is reached if, through the modification of a reusable component, it will no longer be maintained and supported by the supplier. At this point, the support burden rests on the application system developers and maintainers. Typically, improvements in the reusable component are not simple to integrate, and support problems can then be blamed on the modification. Next, spaghetti code. Spaghetti code is one of the most recognizable anti-patterns. Spaghetti code occurs in programs or systems lacking software structure. Continued coding and extensions typically serve to compromise the structure of the software, where even the original developer may lack clarity about the software. Common causes include developers inexperienced with object-oriented design technologies, lack of mentoring, developers working in isolation, ineffective or non-existent code reviews, and no design work done prior to implementation. Now, the minefield. Sometimes, using current software technology is like walking through a high-tech minefield. Several bugs are found in released software products. In fact, some estimate that original source code may contain, on average, multiple bugs per line of code. To address this anti-pattern, proper investment in software testing is an absolute necessity in order to ensure that systems are reasonably bug-free. In some organizations, the number of testing staff actually exceeds programming staff. That's how important testing is. Next is cut and paste programming. Code can be reused by copying source statements, but this can also lead to significant maintenance issues. Instead, consider alternative forms of reuse that can reduce maintenance issues by using common source code that has been tested and is typically well documented. The next design anti-pattern is continuous obsolescence. This anti-pattern is related to the rate of technological change. We all know that technology changes so quickly, without pause. And this makes it so that developers frequently experience trouble keeping up with current versions of software, and this can result in difficulties integrating combinations of product releases. Java should be recognized as an example technology of this phenomenon. New versions are released every few months, and with the advent of DevOps and CI/CD, the release cycle has only accelerated. To counter this, open system standards have emerged as an important stabilizing influence because consortium standards are typically the result of well-thought-out industry consensus. The lava flow anti-pattern is concerned with dead code and neglected or forgotten design information that tends to get frozen in an ever-changing design. The name comes from the fact that dead code and neglected or forgotten design information are analogous to a lava flow with hardening edges and globules. The refactored solution to this anti-pattern includes a commitment to a configuration management process which eliminates dead code and continually evolves or refactors design focused on improving quality. Our next anti-pattern is the ambiguous viewpoint. Object-oriented analysis and design models are usually presented without a clear explanation of the viewpoint represented by that model. By default, object-oriented analysis and design models represent an implementation viewpoint that may actually be the least useful. Further, mixed viewpoints don't permit the fundamental separation of interfaces from implementation details, effectively nullifying one of the primary benefits of object-oriented design. Next, the functional decomposition anti-pattern is the output of experienced, non-object-oriented developers creating applications using an object-oriented language. The resulting code may resemble a structural language in class structure, and this can be deceivingly complex because resourceful, experienced, and intelligent procedural developers are very adept at devising very clever ways to apply their tried and true, time-tested methods to an object-oriented architecture. Next, input sludge. Software that fails basic behavioral tests may be victim to input sludge, which typically occurs when ad hoc algorithms are used for handling program input. The next anti-pattern is mushroom management. Within some architecture and management groups, there is this explicit policy that's designed to keep system developers isolated from the system's end users. Requirements are therefore passed second-hand through intermediaries, including architects, managers, or requirements analysts, and this can lead to confusion. And finally, the blob. This procedural style design can lead to one object with a large majority of responsibilities, while most other objects execute the simplest processes or perhaps only hold data. The solution here involves refactoring the design to more equitably distribute responsibilities and also includes isolating the effects of changes. In this video, We'll explore the process of refactoring. First, let's define refactoring. Refactoring is a systematic process that involves improving code without creating new functionality. It can transform what is a veritable mess into clean code and simple design. Refactoring improves the internal structure of source code while preserving its external behavior. Typical risks and pitfalls include the fact that refactoring does not mean rewriting code. Refactoring is also not about fixing bugs. That's a totally different process altogether. Refactoring is not about improving visual aspects of software, such as its user interface. Refactoring must not be performed where there's an absence of safeguards against introducing defects. That is just too risky. Rather, safeguards should include regression testing, automated unit or automated acceptance tests, and support for formal reasoning like type systems. When undertaking a refactoring initiative, we expect that the refactoring exercise will improve the code base. One benefit from refactoring is that with reasonable effort, it does invariably help understand the code base. Refactoring also typically improves the objective attributes of code, for example, length, duplication, coupling and cohesion, cyclomatic complexity, and so on. And these are attributes that generally are consistent with improved maintenance. Refactoring facilitates reusable design elements such as design patterns and code modules, and refactoring encourages developers to carefully consider design decisions that were made and understand why they were made. Now, we'll talk about one of the main objectives of refactoring, and that is to combat technical debt. Refactoring can transform a code mess into clean code and simple design. So it avoids dreaded sloppy code like inconsistent and poorly conceived variable and object naming, bloated classes, and bloated methods. Clean code adheres to the don't repeat yourself or dry principles, which means, for one, that it doesn't contain duplication. This can be a real problem because each time a change is made in a piece of code that is duplicated somewhere in the code base, you must make an identical modification to every duplicated instance. Clean code uses a minimalist approach with respect to the number of classes and other moving parts. Less code is less subject matter that needs to be kept in your head. Less code means easier maintenance and results in fewer bugs. Also, keep in mind that code is liability, so it should be kept short and simple and as concise as possible. One other thing about clean code is that clean code passes every test. When only 95% of your tests have passed, you know that your code is dirty. Overall, clean code is far easier and much cheaper to maintain. What exactly do we mean by technical debt? Well, technical debt is simply a metaphor for sloppy or unclean code. Let's consider a bank loan. You get a loan from the bank, which allows you to make purchases faster, as in now. You pay interest on the principal, which is the amount borrowed, in order to speed up your purchasing process. You eventually have to pay off the principal, again, the amount you borrowed, but you also have to pay the interest on the loan. It's compound interest too. So the longer you go without paying and continue to borrow, the more debt you accumulate in an accelerated fashion. The interest could potentially exceed your total income, which renders repayment difficult, if not impossible. And a similar thing can happen with technical debt. A developer can temporarily speed things up by avoiding tests for new features. However, slowly but surely, this gradually slows progress every day until the developer is compelled, one way or another, to pay off the technical debt by writing and running tests. So what causes technical debt? When there is a lack of tests and testing, there is a lack of immediate feedback. It may be quicker to go this way, but it just invites risk. In a worst-case scenario, changes may be implemented and deployed right through to production without any prior testing, and we know that this can lead to some pretty catastrophic consequences. There's also the lack of documentation. This not only slows down current developers, it introduces myriads of other risks, and it also slows down the onboarding process, delaying the possibility of getting new people to contribute in a meaningful way. Worse, if key people leave the project, that lack of documentation can put a full stop to development. Lack of team interaction and communication is another cause of technical debt. For example, if an up-to-date project knowledge base isn't distributed properly, some people will wind up with outdated material and consequently outdated understanding about the project. There's also the lack of compliance monitoring, and this can occur when everyone working on the project writes code with no oversight or monitoring for standards and compliance. And the sheer lack of understanding related to the consequences of technical debt can cause technical debt, typically because there is no commitment to provide sufficient time for refactoring if its impact, as negative as it is not understood. Now, let's consider some other factors. The project's requirements are constantly changing, and the project's programmers are writing new code every day that works with potentially obsolete components. Therefore, the longer that refactoring is deferred or delayed, the higher the volume of dependent code that will have to be reworked and addressed at some point in the future. Long-term simultaneous development in several branches can also lead to simultaneous accumulation of technical debt, which increases when changes are merged. The more changes made in isolation, the greater the total technical debt. In some scenarios, business pressures can create circumstances that may press the rollout of features before they're actually really finished. This is very risky. Also, when a project seems like a monolith rather than the sum of individual modules, any changes to one part of the project will affect others. In addition, team development is more challenging due to the fact that it's difficult to isolate the work of individual developers. And incompetence. This is when the developer just doesn't understand how to write clean code. When should refactoring occur? Well, there's this rule of 3 or limit of 3, which goes like this. When you're doing something for the first time, just do it and get it done. When you're doing something similar for the second time, blush at the fact that you have to repeat it, but just get it done anyway. But when you find yourself doing something for the third time, it's time to start refactoring. Also, when you're addressing bugs in code, that's a good time to consider refactoring. It doesn't mean that you refactor while you're addressing bugs, but it's a good time to consider refactoring. Clean code is much easier to troubleshoot and to locate root causes of errors. The code review could potentially be the last chance to clean up the code before being pushed to production. Pairwise reviews are excellent for identifying and fixing simple problems quickly and for assessing the time required to fix more difficult problems. And finally, when adding a feature, refactoring can help bring out the understanding of other developers' code. But if you must deal with other people's dirty code, try to refactor it first, because clean code is so much easier to grasp and comprehend, and it's so much easier to make changes within clean code. In this video, we'll consider software refactoring techniques. Before you can effectively refactor your code, it's important to understand what the main culprits are, the typical problems, and further, how to locate them. This is where code smells make their presence known. Code smells are simply aspects of code that are typically indicative of problems. Okay, so now let's look at some typical refactoring targets. First, code bloaters. These are code, classes, and methods that have grown to such huge proportions that they're genuinely difficult to work with. These smells don't typically manifest right away either. Rather, they accumulate over time and as the program evolves. For example, the long method is a situation that occurs when a method contains too many lines of code. Of course, this is subjective. For example, what is too long? What is too many lines of code? Generally speaking, though, most methods needn't be longer than 10 to 20 lines. Usually, long methods contain code snippets that can be grouped together. So you may want to consider moving this code to a separate new method or function and replace the old code with a simple call to the new method. Change blockers or change preventers are smells that can indicate when you need to change something in one place in your code, but you'll also have to make similar changes in other places too. As a result, development becomes much more complicated, risky, and expensive. This is similar to shotgun surgery, where making any modifications requires that you make several small changes to many different classes. In the refactoring exercise, this may mean moving classes around. Next are smells related to incomplete or incorrect application of object-oriented programming principles. This can happen, for example, when using alternative classes with different interfaces, which essentially means having two classes that perform identical functions, but they have different method names. Another target exists in the form of dispensable elements. These are elements in code that are not necessary, and in fact, without them, the code would be easier to read, more efficient, and simply cleaner. Examples include unnecessary comments, duplicate code, that's a real bad one, and dead code, which may be a variable, a field, parameter, method, or class no longer used, and this frequently happens because it's obsolete. Then we have couplers. Couplers are interesting targets. Couplers are code elements that participate in the excessive coupling between classes. You'll often hear of symptoms like feature envy in relation to couplers. This is a situation where a method accesses the data from some other object more than its own data. For example, this can occur when fields are moved to a data class. In this type of situation, it may be best to move the operations on data to the class as well. Refactoring methods. These methods can be conveniently grouped by their function. So first, let's consider moving features. Moving features is concerned with moving features between objects. Let's assume, for example, that functionality has been distributed amongst various different classes in a confusing and difficult way. The moving features refactoring techniques, which includes moving methods, fields, extracting classes, as well as others, can be used to safely create new classes, move functionality between classes, and hide implementation details. Next, simplifying conditionals. This is an excellent refactoring technique because the logic in conditionals tends to become more complicated over time. Decomposing conditionals, which is one of the refactoring techniques in this category, decomposes complicated logic into separate methods: the condition, the then, and the else. Next are the organizing data refactoring techniques. These are focused on data handling and replacing primitives with rich class functionality. For example, one problem that is common is when you have an array that contains various types of data. In this case, it may be wise to replace that array with an object that has separate fields for each element. Now, composing methods. A significant component of refactoring involves correctly composing methods. In most situations, excessively long methods are the culprit. The sheer volume of code inside long methods can disguise the execution logic and make the method very difficult to understand, which means that changing it is even more of a challenge. The refactoring techniques in the composing methods category can help reorganize and simplify methods and address code duplication. And of course, with clean code, we know that it makes it much easier to understand code and to work with code. The next category is handling generalization. The techniques in this category are concerned primarily with creating new classes and interfaces and moving functionality within the class inheritance hierarchy. Now, the techniques involved in the simplifying method calls category simplifies method calls, making them easier to understand. This also serves to simplify interfaces associated with interaction between classes. In this video, we'll explore the guiding principles behind typical API patterns. Most modern web applications expose APIs that clients can use to interact with the application. A well-designed web API should aim to support platform neutrality or platform independence. Any client should be able to call the API regardless of how the API is implemented internally. This requires using standard protocols and having a mechanism whereby the client and the web service can agree on the format of the data to be exchanged. The web API should also be able to evolve and add functionality independently of client applications. As the API evolves, existing client applications should continue to function without modification, and all functionality must be easily discoverable. When designing APIs, it's important to organize the API around the resources. We need to focus on the business entities that the web API exposes. For example, in an online video service, the primary entities might be users and videos. Keep in mind that a resource doesn't necessarily have to be based on a single physical data item. For example, a video resource, which could include movies, TV series, and documentaries, might be represented internally across multiple tables in a relational database, then presented to the user as a single entity. And this leads nicely into the next point, and that is to avoid creating APIs that simply reflect the internal structure of a database. A typical client should never be exposed to the underlying structure or implementation. Entities are often conveniently grouped together into collections. For example, users and videos. A collection is a separate resource from the individual item within the collection, and it should have its own URI. You should adopt a consistent naming convention in URIs. Another consideration is how you may be able to expose relationships and associations between different types of resources. So the focus is on serving resources, and we should always try to keep URIs relatively simple. We must not forget that all web requests impose some load on the web server. More requests mean larger load, so we should recognize and acknowledge that. To help in this regard, we should avoid deploying chatty APIs, that is, exposing huge volumes of small or tiny resources. An API configured that way may require that a client send several requests to find even modest amounts of data. When designing an API, we must avoid introducing dependencies between the web API and the underlying data sources. The web API should be an abstraction of the database. In scenarios where it's not possible to map an operation implemented by an API, we can use HTTP methods to accommodate such requests. For example, the API could provide an option to invoke a function and return the results as an HTTP response. An API should define operations in terms of HTTP methods. The HTTP protocol defines some well-known methods, and the most common HTTP methods used by RESTful web APIs are the GET request, which is used to retrieve information about the resource at the specified URI, and the response body contains the information requested. The POST request creates a new resource at the specified URI. The request body contains specifics about the new resource. A PUT request can create or replace the resource at the specified URI. The request body specifies the resource to be created or updated. Patch requests perform a partial update of a resource. The request body specifies the changes that are to be applied to the resource. And delete. The delete method removes the resource at the specified URI. When a GET request is made, the response body contains a representation of the requested resource. The HTTP protocol uses media types, also known as MIME types, to specify formats. Most web APIs support JSON and XML, and the content type header is where that format is specified. Post, put, patch, or delete operations require processing and/or network traffic time to complete and return a response. Such operations are treated as asynchronous. You could return an HTTP status code 202 accepted that tells the client that the request was accepted but isn't completed. Now, let's take a quick look at some status codes. A successful GET usually returns a 200 OK status code, while if the resource is not found, the method should return a 404 not found code. For POST methods, if a POST is accepted but doesn't create a new resource, the method can return HTTP status code 200. If the method creates a new resource, it returns a 201 created code. If there's no content to return, the method can return 204 no content status code. And invalid requests should return a 400 bad request code. For PUT methods, if a PUT method updates an existing resource, it can return a 200 OK. If the method creates a new resource, similar to the POST method, it returns a status code 201, created. If the method updates an existing resource, it can sometimes return 204, no content. And where it's not possible to update an existing resource, a 409 conflict code is returned. Now, the specification for the patch method, which is RFC 5789, does not define a particular format for patch documents. The format is typically inferred from the media type specified in the request, and the most common supported patch formats are variations of JSON. Now, the delete method, if successful, typically returns 204 no content status, or if the resource was not found, a 404 not found code. An API should support navigation allowing clients to access resources in an efficient manner. Clients, for example, could be provided with the ability to request a sort order. An API should provide a convenient way for clients to request information, but in a way that is network friendly. We do not, for example, want a client application to have to return all orders and then filter them client-side. That's too inefficient. Instead, the API could support passing a filter in the query string of a URI. For example, year equals 22. The Web API is also responsible for parsing and handling the cust ID parameter in the query string and returning the filtered results from the server side. Now, this is a typical REST API design. So from the left-hand side, we've got the data model, which is provided by the application. Then we have the resource model, which is the API. So for example, we have a resource model that exposes a logical hierarchy over the customer's resources. And then we have on the client side, a client app, a REST library, or an HTTP library that makes the client requests. Now, an API can support partial responses for large binary resources. For convenience and reliability, we can enable resources to be retrieved in chunks by supporting the accept ranges header for GET requests for large resources. APIs can use HTTP head requests for these resources. A head request is similar to a normal GET request, but a head request only returns the HTTP headers that describe the resource. The content length header gives the total size of the resource. Now, hypermedia as the engine of application state is a design feature of RESTful architecture. Under this principle, a client communicates with the network through hypermedia, which supports various delivery formats. Each GET request should return the information necessary to locate resources related directly to the requested resource through hyperlinks included in the response. Now, APIs may change. For example, when business requirements change. Perhaps there are new or different data sources or collections. For that, we can employ some versioning scheme. When considering making changes to an API, though, it's imperative that one consider how client applications will be affected. Backward compatibility is imperative in order to continue to handle existing client application requests unchanged while allowing new client applications to take advantage of new features and resources. Versioning enables an API to indicate the features and resources it exposes. Likewise, client applications should be able to submit requests that are directed to specific versions of a feature or resource. Versioning approaches include no versioning, which is the simplest approach. URI versioning means that each time you modify the Web API or change the schema of resources, you add a version number to the URI for each resource. Then we have query string versioning. Here, rather than providing multiple URIs, you can specify the version of the resource by using a parameter within the query string appended to the HTTP request. With header versioning, rather than appending the version number as a query string parameter, a custom header could be implemented indicating the version of the resource. The client application adds the appropriate header to any requests. And media type versioning. When a client application sends a GET request, it should specify the format of the content that it can handle by using an accept header. The accept header can be used to allow the client application to specify the format of response body, typically XML, JSON, or any other common format that the client is capable of parsing. When designing an API, the Open API initiative is one consideration. It was created by an industry consortium to standardize the REST API. The Open API specification includes a set of opinionated guidelines on how a REST API should be designed. And Open API promotes a contract-first approach which means that the API contract, the interface, is designed first, and then code is written to implement the contract. In this video, we'll explore fundamental design patterns for implementing API resource layout and naming. REST is an architectural design pattern and is not a communication protocol. HTTP is considered a RESTful protocol as it is one implementation of the REST architecture. Due to the fact that it is not a formally defined protocol, there are all sorts of opinions about implementing REST APIs. But here are 5 constraints that most experts will agree must be present for an application to be considered RESTful. First, it must be client-server. A client-server architecture allows a clear separation of concerns. The client is responsible for requesting and displaying data. The server is responsible for data storage and application logic. It should employ a uniform interface. Caching. Stateless client-server communication can see server load increase because some information may require multiple requests. So only retrieved data should be cacheable. Then there's statelessness. Communication between client and server must be stateless. Each client request must contain all the information necessary for the server to process the request. And it must be a layered system, a key feature of most network systems. Where REST is concerned, this means that a client won't necessarily be able to tell if it is directly communicating with the server or an intermediate like a proxy. APIs should be organized around serving resources. Focus on the business entities that the Web API exposes. Entities are often conveniently grouped together into collections. A collection is a separate resource from the item within the collection, and it should have its own URI. A consistent naming convention for URIs is crucial, and APIs should expose relationships and associations between different types of resources. We also want to keep URIs relatively simple. APIs must also avoid introducing dependencies between the API and the underlying data sources. The API should be an abstraction of the database. And to avoid excessive traffic, Web API should be careful not to expose huge numbers of small resources that require several requests. Now, looking at a typical REST API design, on the application, we have a data model. Now, that data model is served through the application interface, and the API represents a logical hierarchy over the resources it serves, in this case, customers. So, for example, customers returns all customers. Customers/1 returns the customer with an ID of 1. And customers1 orders would return all the orders for a customer with a customer ID of 1. On the rightmost side, we have the client. And the client could be a client app, a REST library, or an HTTP library. And these client requests are sent to the server, and the server responds accordingly. Now, when creating resources, we need to use simple API endpoints. The example I use here is customers, and customers/1, which is an individual customer, and customers, which is a collection. We also want to be careful to use nouns, and that's what I'm doing here, customers, 1, and orders, right? Customers is a noun. Orders is a noun. We want to be careful not to use verbs. So, for example, a GET request with our URI ending with GET all customers is something to avoid. We want to avoid verbs. We want to avoid mixing verbs and nouns, which are operational URIs. So when creating resources, we want to use parameterized URIs. Likewise, we can have multiple parameters in a URI. We should use sub-resources to expose data relationships. For example, the department/IT/employees URI returns all employees that belong to the IT department. So there's that relationship. We do not want to use, as mentioned, operational URIs. For example, get all employees in IT department, or list employee in IT department/NY. And there's a debate about single versus plural nouns, and there is no hard rule. However, when there's one resource returned, it's a good idea to return singular, and when multiple resources, use plural. So again, when creating resources, we can use parameters, and I'm referring to parameterized URIs. And we want to avoid operational URIs, which mix nouns and verbs. Now, another consideration is the return type. The most common return type is JSON format. So that's likely the best option. XML is another choice if you want to offer both. However, JSON is the fundamental API return type among web developers, and it also works nicely with document databases. Now, what are the specific HTTP methods used for? Well, GET is used for fetching resources or collections. POST is used for creating resources or collections. PUT and PATCH are used for updating resources or collections. And DELETE is used for deleting resources or collections. So in this course, we've examined the importance of design patterns as well as types of patterns. We did this by exploring behavioral, structural, and creational design patterns and their implementations. We explored different types of design anti-patterns. We explored using code refactoring techniques. We considered API pattern principles, as well as API design patterns for resource layout and naming. In our next course, we'll move on to describe Java classes, attributes, methods, constructors, access modifiers, and how to compile and run a Java application.
A Java class is a logical entity that we can use to create objects out of. You can think of the class like a blueprint or a set of instructions that tells an object what it should contain when it's being created. So to that end, within a Java class, we have various components that make up what that blueprint is. The first component of a Java class is its attributes. You can think of attributes like variables. Basically, an attribute of a Java class is a defined instance variable that exists within the class. So this could be an example, int a equals 1, as we see on the screen in the graphic bubble. Basically, it's defining this class will always have this variable as part of it. This is an attribute of the class. And then we can manipulate those attributes or those variables in various different ways depending on how they're defined. We can either manipulate them directly or indirectly through the use of something like a class method. A class method is a logical function block that has a set of code that we can run repeatedly. Every time we call a class method on an object created out of that class, we can run the code contained within that method. So a good example of a common class method is called a getter. And a getter would be used to retrieve the value of an attribute and return that value to us somewhere else in the program. Similarly, we also have setters. And setters are a class method that we can call on an object to set the value of an attribute. So oftentimes these attributes and methods go hand in hand. The attributes provide constant values or dynamic values that we can feed into these class methods in order to do whatever the class needs to do. And then on those attributes and class methods, we can apply Java modifiers. We have two types of modifiers. The first are access modifiers. And these are modifiers that control who and what can access certain attributes or certain class methods and how they can access those methods. Examples of access modifiers are public, private, and protected. And each one means a different thing. So if we're looking at a Java attribute, a public attribute means if we have an object created out of a class, then we can access that public attribute directly. We can just call on that object and modify that attribute to our heart's content. A private attribute means that we can't do that necessarily in the same way. We can't just access the attribute directly on an object. Instead, we need to have some sort of method that allows us to access that attribute, because a private attribute is only accessible within the class that it exists inside of. So if you create an object out of a class, only methods or other attributes inside that class have access to a private attribute. Protected is a different kind of access modifier. It's not nearly as often used as public or private, but it defines things as being visible within a Java package as a whole, but not outside of the Java package. But most often you're either using public or private as your access modifier. The public or private works the same on class methods. A public class method can be accessed by anybody within the Java program, whereas a private class method can only be accessed by other methods or attributes within the class that it's defined in. Then we have other types like non-access modifiers. Non-access modifiers are more about defining the behavior of an attribute or a class. So for example, a non-access modifier is final. We use final on an attribute if we don't want the value of it to be changed after it's defined. So if I were to, say, have the constant of gravity within my program, 9.8 meters per second squared, then there's a good chance that's not going to change. So I would define it as final, and then no matter what, if somebody tries to overwrite my gravity value or tries to change it in some way, it won't work because I've defined it as final, so you can't change that value. We also have other non-access modifiers like the keyword abstract, which we can use to create abstract classes. Abstract classes are classes that can't be used to directly create an object out of, but instead define subclasses that would implement the abstract class, and then they're making a promise to implement whatever is defined within that abstract class. We can also apply the keyword abstract to attributes, and we would do that within an abstract class. So abstract classes would have abstract attributes. We could also use a non-access modifier like static. If we apply the keyword static to, say, a class method, what that means is that we can call that method directly on a class. We don't necessarily need to have an object created out of that class in order to call that method. So if I have a static method inside of a test class, I could just call test dot whatever the name of the static method is. I don't need to first create an object and call that method. These are the two different modifier types in Java and what they're used for. Let's take a closer look at Java class attributes. This can be confusing sometimes because attributes are called by many different names. They can be called attributes or instance variables or fields. And in essence, they all mean the same thing. Sometimes they have slightly different connotations behind them, but they're all referring to these Java class attributes. So let's look at the different names that you might see and what they might mean. I mentioned earlier that you could think of them like variables because they are variables. A variable is just a piece of data that houses a dynamic value of some sort. The value can change, it can be modified, it can be typecast into a different type of variable. You might also hear the word fields used, and really the only difference between a variable and a field is semantic. A variable becomes a field once it's assigned an access modifier like public or private. And then we have what we've been talking about all along, which are attributes. Strictly speaking, attributes are publicly access modified, and we have properties which are privately modified. These are all the different semantics associated with Java class attributes. Taking a similar look at Java class methods, we can see all the different things that can be applied to them. So we talked about access modifiers earlier. Java class methods can be public or private or protected. They can be static or non-static. Once again, that means that static, you can call the method directly on a class, whereas non-static methods, you first need to have an object created out of the class and then call the method on the object. And you can have them abstract versus concrete. If you define a class as abstract, you can't create an object out of it. If you define it not being abstract, therefore by default it's concrete, then you can create an object out of it. And these class methods are used to execute repeated pieces of code. Taking a similar look at Java class methods, we can see all the different things that can be applied to them. So we talked about access modifiers earlier. Java class methods can be public or private or protected. They can be static or non-static. Once again, that means that static, you can call the method directly on a class, whereas non-static methods, you first need to have an object created out of the class and then call the method on the object. And you can have them abstract versus concrete. If you define a class as abstract, you can't create an object out of it. If you define it not being abstract, therefore by default it's concrete, then you can create an object out of it. And these class methods are used to execute repeated pieces of code. And the final component of a Java class that I'm going to talk about are Java constructors. Java constructors are a very special type of class method. And they're special because this class method is called automatically whenever an object of a class is created. So if you were to create a new object with the new keyword, then this constructor is run automatically. You don't need to call the method explicitly. It's just going to run. So it's a good way to set up default values in a class or within an object once it's created out of a class. And you can have a constructor within any Java class. Actually, all Java classes have a constructor by default, even if you don't explicitly define one. Now, the default constructor doesn't really do anything, but it's still there. But you define a Java constructor by creating a method within a class that is the exact same name as the Java class, and it has no return type. You can also have constructors within abstract classes, but you cannot have constructors in interfaces. Interfaces are another extension or another type of abstract class, but they're defined in such a way that you can't put a constructor within the interface. Rather, anything that implements the interface will have to build its own constructor. Let's take a deeper dive into Java classes. The majority of Java classes consist of two things. The attributes, which are variables in the class, are instance variables. These can be integers, floats, strings, doubles, all kinds of different types. And they also have methods, which are the actions that these classes can take to modify and return these attributes to other parts of the program. The primary use case for classes is to create objects out of them. So our objects are created using the template defined within the class. When we create an object out of a class, there are certain components that go along with the object. The first one is the state. So this relates to the attributes of the class. When we have an attribute defined in a class, say an integer, it's just there, but it's not necessarily being used. We could have int I equals 1. Now, when we have an object, that integer suddenly represents the state of the object. If that integer I is still equal to 1 in the object, then that's representing a state. So for example, we see on the page that there is a cat symbol within our bubble. Some things that might become states with a cat object are things like fur color, eye color, age, height, all these different things that would describe what the cat object looks like would become state elements of our object. Objects also have a certain behavior. So this is describing what the object does. And this relates to the class methods that are defined within the class. So if you have a method within a cat class called walk, and then you create an object out of the cat class, you could then describe that walk method as being a behavior of the object that you've instantiated. Because you could call that walk method on the object, and then the walk method would do whatever it is that it's supposed to do. Most likely it would tell the cat to move forward or backward or side to side. And finally, objects have an identity. So when you create an object out of a class, the internals of the Java virtual machine assign it a unique identifier so that Java will know this object is always taking up this part of our memory. This memory is allocated for the object, so whenever we need to access it, we go here to do that. And that's because you can create any number of objects out of the same class. So if we created two cat objects, one with a cat fur color of brown and one with a cat fur color of black, we don't want Java to think that they're the same object because they have two distinctly different fur colors. So we would actually have two different distinct objects that were both created out of the cat class, and Java knows that they're different because they have different identities. In Java, we have special types of classes. One type is an abstract class. And an abstract class is special because it's a restricted class. And what that means is you can't use this class to directly instantiate an object. We can't use the keyword new to create an object out of this class. First, another class has to inherit the abstract class before we can actually use it to create an object. And then we create an object out of the class that has inherited the abstract class. And any class that inherits an abstract class has to implement whatever abstract methods are defined within the abstract class. So an abstract class will have these abstract methods, and these abstract methods define the skeleton structure of the method. It would have the method name, the return type, any arguments that go passed to the method, but it doesn't actually have the body of the code. It doesn't specify what the method does, but it does tell any class that inherits an abstract class with an abstract method that it needs to implement this specific method with this specific return type and these specific arguments, but how you do it is up to you. Abstract classes can also have regular methods. They're not restricted to only having abstract methods. And basically what these abstract classes are doing is they're making a promise. If you inherit from an abstract class, you're promising to adhere to the structure laid out in the abstract class. And it's a way of creating more formal, defined program structures within your code. Some of the things to keep in mind when we're dealing with abstract classes: they can have constructors, and the constructor gets called whenever a class that has inherited an abstract class is used to instantiate an object, and then the constructor defined in the abstract class will be called. You can have static methods within an abstract class, but you can't have methods that are both static and abstract at the same time. So you need to have one or the other. You can't have a static abstract method. Similarly with final keyword, you could have final methods and you can have abstract methods, but you can't have a final abstract method. To make a class abstract, the abstract keyword has to be placed in front of the class keyword. So if you had a paper class, your declaration would be public abstract class paper. If you wanted to make a method abstract, it goes in front of the return type. So you would have public abstract int, for example, as the return type. And it's important to get the order correct. Otherwise, Java won't recognize that you are trying to make an abstract class and you'll get an error. Methods within an abstract class, as we mentioned, can be either abstract or non-abstract. You have the choice. And object instantiation has to be done from a class that's inherited from the abstract class, not the abstract class itself. In this video, we're going to demonstrate the features and components of Java classes. I'll be working within an IDE, which is a development environment. The one that I'm using is IntelliJ, but there are many different options available on the market, so take a look around and see what one you like the best before deciding on which one you want to go with. You don't need to use an IDE. You could also do your development in a plain text editor like Notepad, but you'll find an IDE makes your life a lot easier. So the first thing we're going to do is create a Java class to look at what kind of features it has. So I have a project started, and we can see the project tree on the left-hand side of my screen. And within the source folder, I'm going to create a new Java class. And we'll call this employee.java. And I'm giving my file name a capital E for the first word. And that's convention with classes, is to capitalize every word in the name. So now I have an employee class created. Now I created a Java class using the IDE, but there's nothing special going on yet right now. This is the same as if you created a normal text file, saved it as employee.java, and typed in the text that you see on the screen. So here we see some of our first features of a class. When we're defining a class, there are certain keywords we need to put in. The first one defines the visibility of the class to our overall Java project or package. In this case, it's public. Classes will almost always be public. You may run into some niche scenarios that require you to use a different visibility, but in general, public will be suitable for almost all of your purposes. Once we define the visibility as public, that means that other classes within our Java package can utilize this class and make objects from this class, which we'll talk about a little bit more later on. The next keyword is class, and this is what tells Java that we are defining a Java class. So we put in public class and then the name of our class, which we have defined as employee. Once again, following the naming convention, which is capitalized for every word in a class name. An important feature of a class name, it can be anything that you want it to be, but it must match the name of your file. So because I've called my file employee.java, my class name has to be employee. If I were to add employee test, now we can see that there's a red line underneath my class name because Java has detected that there's a mismatch between the class name and the file name. And then we have the curly braces, an open curly brace and a closed curly brace, which defines the boundaries within where I can define features of the class. So everything that I put into the class will be between these curly braces. Now let's go over some of the things that we can put into a class. And don't worry too much if some of them seem a little unfamiliar. We'll go over in more detail in future videos everything that I'm talking about here now. The first thing that we can put in is called an instance variable or a field. And this is simply a variable that we define within the class. So for example, if I wanted to have an employee number, I could define a private int employee num equals 5. And now I've defined an instance variable within my class. Instance variables don't necessarily have to have a value. We could have a private string representing the employee's name, and we could just leave it as null, which is the default assignment if I don't give it a specific value. The next feature that a class can have is a class method, and class methods are used to manipulate or return the values associated with our class fields, among other different operations that you might want to carry out. So for example, we might have a class method called setEmployeeNum. And within that method, we would manipulate the class field or instance variable by setting our instance variable to the argument that we pass into this set class method. So that's another feature that we can have in a class is a class method. Class methods don't have to necessarily interact with instance variables. They can be completely standalone, operate on the argument passed to them, and return a different value. It all depends on the functionality you want, but that's what we use class methods for. Another feature of a class is its constructor. A constructor is a special class method that runs when an object is created out of that class, and this method just runs automatically on creation. The key to a class method that is a constructor is that our constructor doesn't have a return type. So we can see our class method setEmployeeNum has a return type of void. when we make a constructor, we won't have any return type. We'll still have the public visibility, but all we'll have is the name of the method. And the other special part about a constructor in a class is that the constructor name is going to be the same as the class. It must be the same as the class. So we will say public employee. Now we've defined a constructor. And we've defined the constructor because there is no return type and the name of the method is the same as the name of the class. So when an object is created, this will run automatically by default. So let's say we wanted our employee class to have a default name, and we didn't define it in an instance variable. We could manipulate it here by saying this.employee name equals default. And now when an object is created out of this class, this constructor will run automatically and our employee name instance variable will have the value of default. The next feature that I want to talk about of Java classes is how we use them. So let's keep that public class employee here, and now we'll create a new Java class. And we're going to call this one employer.java. Now we have a new class, which is called employer. And we want to, within our employer class, make use of that set employee number class method that we defined in our employee class. So in order to do that, we need to create an object out of the employee class. And that's the feature that I want to talk about now is classes are used to create objects out of them. So we are going to create an object of type employee called object1, and we're going to set it equal to a new instance of employee. So this is telling Java, I want to create an object out of the employee class. And the key items to look at here are the type, which is type employee, which matches the class name, and the keyword new, which tells Java that I want to create a new object out of the class. There's no limit to how many objects can be created out of the same class. So if I wanted a second employee object, I could define object2 equals new employee once again. And these will be two distinct objects even though they're created out of the same class. And now object1 and object2 will have access to all of the various class methods that I've defined within the employee class. So they'll have the ability to set employee number, they'll have the ability to run this constructor, which will be run by default on creation. And the advantage to this is that classes allow us to save a lot of code reuse. We want to have many different employees, and now I can create many different employees, and I never have to touch or modify the employee.java class. And the final class feature that I want to talk about is abstract classes. So let's create a new class called color.java. And we're going to make this an abstract class. And we do that by adding the keyword abstract between the visibility identifier and the class keyword. So we come up with public abstract class. And abstract classes are special because you can't create an object directly out of them. Other classes need to inherit these abstract classes in order to create objects using those classes. So you can think of an abstract class like a promise. We're going to define certain class methods within this abstract class, and any other class that makes use of it is promising to implement these specific methods that we define here. So let's make an abstract method that we want every class that uses this color abstract class to have. So now we have an abstract method within our abstract class. And what this is saying is when we create another class that inherits this abstract class, we are promising that class will have this void method. So let's see that in action. Let's create one more class. We'll call it blue.java. Now we want blue.java, our class blue, to inherit the abstract color class. We do that with the keyword extends. And we provide it the name of the abstract class. And we can see that there is a red line underneath my first line here because I have not fulfilled my promise yet. I haven't implemented the abstract method temperature in my color class. So before Java will let me continue, I need to fulfill that promise. And I do that by implementing the class method that I had defined in the abstract color class. And within this class, I can do whatever I want to do, but the important thing is that I have implemented this method and that this method does something. Color.java doesn't force me to do anything particular within this method, but it does force me to have this method. So I could do something as simple as system.out.println to print to the terminal warm. Or in this case, since we're blue, it would be cold. And now everything is okay. So this is how abstract classes work. They force a certain structure to your classes that inherit from them. And we use inheritance with this extends keyword. And in Java, you can only inherit from one class. So it's single inheritance. We can't extend from multiple different classes. Now that we've extended from color, that's it. That's all we can inherit from. And that covers the main features and components of Java classes. So the important points are that we use classes to prevent code reuse, and the primary use of a class is to create an object out of that class. And that gives us a lot of power in terms of object-oriented programming. Now we're going to take a deep dive into Java class attributes. Java class attributes are known by a few different names, and the differences between them are largely semantic, and we use the different names to refer to how the attributes are actually being used at that given time. So names that you might see for attributes within a class are variables or instance variables, fields, attributes, and properties. They're all referring to the same type of data. It's just differences in how they're being used at the given time. So let's take a look at each one of these in turn and see what they're referring to in terms of class attributes. The first term that we have when talking about Java class attributes is Java variables. Java variables are the basic storage unit in Java. They contain a value of some sort, and that value can be modified or overwritten or reassigned in some way. The most common type of variable, and what often comes to mind first when we talk about Java variables, are the primitive data types. So these are things like your integers, your booleans, your string values, doubles, longs, anything that represents a basic number or string or a true-false value. We aren't limited to only these when we're talking about variables though. Our variables can also refer to objects, so we could assign a variable to contain a certain object and all of the different states that that object contains. But at the end of the day, it's still a value stored in memory, and it's a value that we can change and overwrite. The next term we have is Java fields. Now, fields is still referring to a type of variable or a class attribute, but the difference between a field and a variable is that a field is a variable specifically defined within a class. So once a variable or an instance variable is defined inside of a class, it becomes a field. Oftentimes fields are obtained using data access objects, which is a framework that allows you to access underlying persistent storage, which is what these fields are. They're persistent states or storage of some sort of value in a class. And these fields will have access modifiers. And these access modifiers are telling Java who can modify these fields and how can they modify them. So these are where we get into things like public, private, and protected. Public means that a field can be accessed by anybody. I can freely modify or update the field to my heart's content if it's public. Private means that the field can only be accessed by the class in which it's defined. So outside of that class, I don't have any access to that field if it's private. And protected is somewhere between the two. It's available to any piece of code within the Java package, but anything outside of the Java package won't be able to access that field. And we can also apply the static and non-static modifier to fields. Now this behaves a little bit differently than if we have static and non-static methods. The static modifier doesn't behave the same between the two. When we're talking about a static field, we're talking about how many versions of that field get created. So in a non-static field, the field is created new every time the class is instantiated. So if you have an integer I and it's equal to 2 by default in the class, then whenever that class is instantiated, a new version of that I field will be instantiated along as a state within that object, and it will always be equal to 2. But if you were to make that field static, then only one instance of that field will ever be created. So if you wanted to have, say, a counter to count how many times an object is created using a class, then you could have a static field within that class, and it could be a count field, and you could have it set so that in the constructor, every time an object is created, you add 1 to that field. And then in every object, you will have the most recent version of that field because there's only one instance of it. Our third term is Java attributes. And a Java attribute is a field that has a public access modifier on it. So once we define something as, say, public int I, now that field is an attribute because it's public. And to access Java attributes, we use the dot syntax. So let's say that we have an object called phone, and phone has a attribute or public field called screen. If we wanted to change the value from flat to curved, we could do that by saying phone.screen equals curved. And that's how we access a Java attribute. So Java attributes are readable and writable. We could also assign a variable to the current value of that phone screen by saying public string screen equals phone.screen. And then it would return us the current value of that phone's screen. If you don't want an attribute to be writable, you only want it to be readable, you can use the final modifier. So maybe we're making phones that are only ever flat. So we would put our string with the final modifier, public final string screen equals flat. And now we can't change the value of the screen. We can still read it with the dot syntax, but we can't change it with the dot syntax. And finally, we have Java properties. A Java property is a field with a private access modifier. So once we have something with the private access modifier on it, it becomes a property. Let's take, for example, our phone example again. In this case, for whatever reason, we don't want our screen field to be accessible outside of our class. In that case, we would have a private string screen equals flat, for example. Now, what do we do with these properties or private fields? We can't access them outside of the class, so how do we get them? Well, that's where we implement something like a getter method. A getter method is a method that returns the private field or the property to us outside of the class. So what we would do is we would have a get method, something like public get screen. But we have to make sure that the return type of that method matches the type of the property that it's returning. So in this case, we need to return a string, so it would become public string get screen. It doesn't need to take any arguments because we know it's just going to return the screen property. So it would just, in the body of the method, have return screen or return this.screen. Similarly, we have setter methods, and these do the opposite of the getter method. These allow us to manipulate Java properties or private fields. In this case, this would be a void method because it doesn't return anything. So we would have something like public void set screen, and it would take an argument of a string, and then it would assign whatever string is passed to it as the variable to the screen. So if we wanted to change the screen from flat to curved, we would pass curved as a string to the setter method, and then the setter method would set this.screen equal to the argument, in this case curved. Let's take a look at a concrete example of these attributes in use. On the screen, we have a class called account. So we can see on line 2 the class declaration public class account telling us what our class is. And then on line 4, we have a field. And this field has a couple different modifiers on it. First, we have the final modifier. So that means whatever value is assigned to the field, which in this case is called account type, that's the value it's always going to have. We can't overwrite it or change it. So the value that's assigned to account type is a string called USD checking, and that's the way it's going to stay. The next modifier is static. So that means that no matter how many times this class is instantiated or an object is created out of it, there will only ever be one instance of this account type. And then we have the type of account type, which is string. The next field, which is on line 7, is defined as private, which makes this a property. So we have private big decimal balance. We know that it's type big decimal, and the name of it is balance. And since it's private, it's only accessible within the class that it's defined in, the account class. So below the property, on line 9 to 11, we have the getter, and on line 13 to 15, we have the setter. So looking at the getter first, it's public, then it returns type big decimal, and it's called getBalance. It doesn't take any arguments, but it returns this.balance. If we wanted to set the value of balance, we would look at our setter, and it's also public. It doesn't have a return type, it's void, and it's called setBalance, and as an argument, it takes big decimal num, and it will set this.balance equal to num. And then finally, from line 17 to 19, we have our main method, and it prints out whatever the value of account type is. So in this case, it will print out USD checking. In this video, we're going to show the features and components of Java attributes. To get started, we'll create a Java class and start to create our attributes within that class. So we'll go to our IDE or text editor and create a new Java class. And I'm going to call my Java class @.java. So here we have the skeleton of a Java class. Now we want to add some attributes to it, and then we'll talk about what we can do with those attributes. So when we refer to attributes or class attributes, what we're really talking about is variables or fields that are defined within that class. So let's make our first attribute within our @class. And we're going to define it as an integer, and we'll call it public int first attribute. And now we have our first attribute. Now there's no limit to how many attributes we can define within a class. So let's go ahead and define a few more before we start to talk more about these. We'll define a second integer, and we'll say this one equals 5. Now let's define a string. And we'll define another string. And we'll give that one a value of default. So at this point, we have 4 attributes within our class. Now let's take a look at the various features of each declaration line for the attribute. So the first thing that we'll notice is in each attribute, we've defined the word public. This defines the visibility of our attribute to the rest of our Java package. There are 3 different declarations that we can make in terms of visibility. Public is one of them. We could also have a private attribute, and we could have a protected attribute. What do these visibility modifiers mean? Well, a public visibility modifier means that attribute is visible to anybody. Anybody that wants to access it and modify that variable or that attribute can do so from anywhere within the code base. A private visibility modifier means that attribute is only accessible within the class that it's defined in. So I could make a class method within this at class, and it would be able to access a private attribute, but a object created out of the at class would not be able to directly access a private attribute. Protected is kind of a hybrid between public and private. It refers to an attribute that can be used by the package as a whole and any subclasses within the package as well. But generally, you don't use protected that often, so we're going to ignore it for now. The important ones are public and private. Those are the main ones that you'll be using. More often than not, attributes for best coding practices are defined as private. It's generally better to have your attributes defined as private and then provide what we call getters and setters, which are class methods that will allow other parts of the program to set your attribute values and retrieve your attribute values, rather than allow other objects or other classes to access these attributes directly. But if you have a need to, you can set the attributes as public, and then other classes will be able to access these attributes directly. The next thing that I want to point out is certain attributes, such as second attribute here, I've defined with a default value of 5, but other attributes, like first attribute, I haven't given a value. And that's because you don't necessarily need to assign a value to an attribute. You can leave it like my first attribute or my third attribute, which will just have null values. Or you can have them like my second attribute and my fourth attribute, which have default defined values. And either is suitable. It just depends on whether you want to have your attribute start with a value of null, or if you'd rather have it start with a certain value. Now let's take a look at how we can access these attributes from other classes. So we'll create a second Java class, and let's call this one access.java. And within access.java, our goal is going to be to access and make use of those attributes in at.java. The first thing that we'll need is a class method from which we will create an object and access these attributes. In this case, we're going to use the main method, which is public static void main string args. And it's within this method that we will be creating an object and accessing the attributes. So our first step is to create an object of the at class. So we will say at myObj equals new at. And this creates us an object of the at class. And now let's access our first attribute. We're going to access second attribute, and what we're going to do is simply print it to the command line. And we do that by calling system.out.println and then we'll say my obj to tell it we're accessing it out of this object. And then we use dot, which will tell it that I'm going to access an attribute. And I say dot second attribute. And what this will do is print 5. This is the value of second attribute. Similarly, I could do the same thing with the string. By calling print myObj.fourth attribute, which will be default. So that's how I can access public attributes. If I were to try and do the same thing for a private attribute, such as fifth attribute, we can see that my IDE is not happy with me. And that's because fifth attribute has private visibility, which is going to prevent me from directly accessing the attribute like this. So in this case, I would need a class method to access the attribute, which I don't have. So that makes this attribute inaccessible to me. We could also change the value of the attribute by calling myObj.secondAttribute equals 6. And then if I used the same print line once again, now this would print 6. The attributes that have no values, I could assign a value to them. I could call myObj.firstAttribute, which currently has no value. I could make that equal to 10. And then I could once again print out that attribute. And that would print the value of 10. I could create a second object of the same class. And all of the modifications that I've made to my first object won't be made to my second object. So if we remember, I've overwritten in my first object the value of second attribute to 6. But if I were to now print out the second attribute of my second object, this value is unaffected by my previous change to my first object. So this value is still 5. So we can have any number of objects and they will all have their own attributes, and these attributes are unaffected by changes made in other objects. So that's how we can access objects and manipulate them and overwrite them. If I wanted to access this private fifth attribute, I would have to define within my @, class a public class method, a getter, which won't take any arguments, but will just return fifth attribute. Similarly, I could define a setter that takes in an integer and assigns fifth attribute to that value. And with these setters and getters, I can now access and manipulate the value of that private attribute. So I could come back to my access class and define an integer called set2, and I will say the value of 5. And then I could call that class method on my obj.setFifthAttribute set2. And then if I were to do another print line, I could use the getFifthAttribute getter, and this will print 5. So that's how we can access and work with private attributes. The final point that I want to make about attributes is the keyword final. So I've defined a sixth attribute, and I've defined it as an integer equal to 10. and I've used the keyword final. Now, what final does is it means that this integer cannot be overwritten. So if I were to try to modify the attribute like I did in access.java to say myobj.6 attribute equals 8, that won't work because this is a final attribute. It is defined as 10 and it will stay as 10. With final variables or final attributes, there are generally naming conventions. One naming convention is to give it an all uppercase name to indicate that it is a final attribute. So that's how we can define and use attributes in Java. Let's take a closer look at Java class methods. Java class methods are methods that are defined within the body of a class. And you can think of them as blocks of code that perform some sort of functionality, and they can perform them over and over again. It's a routine that the class can continually call to perform repeatedly. So an example of a class method could be something like print blank spaces, and you would call this class method when you wanted to print out a bunch of blank lines to the console in order to format your output to look a certain way. Just like fields or class attributes, class methods also have access modifiers. So we can have a public class method, which means it's accessible to anybody who wants to call that method. We could have a private class method, which means it's only accessible within the class that it's defined. And we can have a protected class method, which means that it's accessible within the Java package, but not outside of your Java package. Methods can be static or non-static, and this is not the same as when we define a field as static or non-static. The behavior here is different. A static class method means that we can call that method without actually instantiating an object. We don't need to create an instance of the class with an object to call that method. Instead, what we could do is if we had a class called pencil and we had a static method within the pencil class called write, we could just use the dot syntax and say pencil.write. We don't need to first create an object, say yellow equals an instance of that class pencil. We can just call the method directly. A non-static method means that an object has to be instantiated before we can call it. So if we had a non-static method called erase, we could not just say pencil.erase. We would have to instantiate an instance of that pencil class. So we could have brown equals a new instance of the pencil class, and then we could have brown.erase. So that's the difference between static and non-static methods. And our class methods can be either abstract or concrete. An abstract method is a method that's defined within an abstract class with the abstract modifier. And it defines the name of the method, the return type, any arguments it might take, but it doesn't define the body of the code. But it does require that any class inheriting or implementing that abstract class with that abstract method implement that method with some sort of body of code doing something. Whereas a concrete method is the standard declaration of a class method, and in that case you have all the same things as the abstract method plus the body of the code defining what the method does without the abstract modifier. In Java we have what we call polymorphism, and there are two types of polymorphism in Java. We have method overriding and method overloading. So let's take a closer look at both of these to see what they are and what they do. We'll look at method overriding first. Method overriding is where we have an implementation of a method, and then down the line, we redefine that method and change what it does, thereby overriding its functionality. This happens when we use inheritance. So if we have one class that's inheriting from another, we call that class the subclass. And a subclass can use the super keyword. And what this will do is it will call the constructor of the class that it's inheriting from. And that allows us to set up a subclass with its superclass. And once we have a subclass, we can re-implement any method that's implemented in our superclass in our subclass. And this happens at runtime. It's called dynamic binding. And it means that anytime we compile and run our program, it's in the running stage where the program will decide which method to use. And if we've overridden a method, that was present in our superclass, then it will use our subclass's implementation of that method. The nice thing with this is that we can have a method in our superclass, and it does one thing, and then in one subclass we want it to do a different thing, so we override it there. But let's say in another subclass, we don't want it to do something different, so we can just leave it as it is. And we haven't had to touch the original method at all in the superclass to have these two different implementations. If you remember, we talked about abstract classes and interfaces and how we have abstract methods. So whenever we implement an abstract class by extending it or inheritance, then we also have to implement all of the abstract methods that are within that abstract class. And that's a form of overriding. We're overriding the abstract methods with our concrete methods using the definition provided to us. There are some rules we have to follow though when we do method overriding. The first rule is that the parameter list has to match. So if the first implementation of the method in the superclass has two parameters as arguments to its method, and both parameters are strings, then in our overriding implementation in our subclass, we still have to have two strings as our parameter list. The access modifier that we apply to our method in the subclass that's overriding the superclass's method cannot be more restrictive than the access modifier in the superclass. So if we have the superclass method defined as public, we can't define the subclass implementation as private. It has to be public as well. And finally, there are a select few methods that we can't override. Private methods, static methods, and final methods cannot be overridden. Method overloading is where we have two methods with the same name, but they perform a different function. So for example, we might have two methods that have different numbers of parameters. So let's have our method be called stand. And in one definition of stand, we take in an integer. But we also want to have a behavior where we take in two integers. So we could have the method defined twice, both times with the name of stand. And in the first parameter list, we'll have one integer. And in the second parameter list, we'll have two integers. And Java will polymorphically at runtime figure out any time this function is called, is it being called with one integer or two? If it's being called with one integer, it will take the method definition that only has one integer as a parameter. And if it's being called two, it will take the method signature that has two parameters. We could also have different parameter data types. So let's use our stand method again. And this time, we'll have one method signature that takes an integer as a parameter. And then we'll have a second implementation of stand, which takes a string as a parameter. And once again, Java will polymorphically at runtime decide when this method is called. Is it being called with a string as a parameter, in which case it will use the method signature that has a string, or is it being called with an integer or an int, and in which case it will use the method implementation of int. So method overloading is where we have the same name for a method, but different parameters in terms of number or type. In this video, we're going to demonstrate the features and components of Java methods. So to get started, let's create a class in which we can define some methods. So I'm going to create a new Java class called a.java. And within this class, we're going to define some methods that we can talk about. So first, we'll define a method called public void print this. And it will take in a string called toPrint, and all it will do is print out the string that it's passed. Now we have a method that we can talk about. So here I've created a method. Now let's go over the individual parts of what I've stated. The first part is this keyword public. Now you might be familiar with the visibility of public and private when we're talking about fields or instance variables. When we're talking about methods, this public is a little bit different. There are two different visibility modifiers that you can have on a method. There is public and static. We'll talk about static a little bit more later on, but for now, let's stick with public. Public means that in order to use this method, I'll need to create an object out of class A and then call this method on that object. So that's what we do when we're setting the visibility modifier to public. The next keyword is void, and this is the return type of the method. Now, since my method isn't returning anything, it's only printing something to the command line, we use the keyword void, and that tells Java this method doesn't return anything. We'll show a few other methods that actually have return types, and you'll see the difference between void and something like int or string. The next keyword is just the name of the method. I've called it print this. It can be anything you want. Method convention is that the start of the first word is lowercase, and then every subsequent word is capitalized to start with, and that's called camel case. Generally, you want to try and make the name somewhat descriptive of what the method is doing. And then we have what we call the method parameters. Method parameters are pieces of data that are passed along to the method in order for that method to work with those pieces of data. In this case, I am passing a string called toPrint as my parameter, and then I am printing that string to the command line. We could have any number of parameters. There's no limit. So I could have another string called toPrint2, and we could use that parameter and print it out as well. So we have multiple parameters separated by commas. And then we have the open braces and the closed braces, which tell the method its starting and ending point. So anything in between those braces is the contents of the method. And then within the method is the code that we want to execute. So if we wanted to do a method that had a return type of, say, integer instead of void, we could have public int add 2. And it takes a parameter of n, which will be of type integer. And what this does is it will take n, which is an integer, and add 2 to it, and just return the value with 2 added to it. And now we have a method that has a return type of int because it's returning an integer, which will be n plus 2. So the advantage of methods in Java is that it allows us to reuse the same code many times on different parameters. So if I wanted to, say, add 2 to many different numbers, I could in my code add 2 to each number individually, or I could call this method and have the method take care of it for me any number of times by simply passing in a different parameter to the method each time. In order to call these methods, since these are public methods, I'll need an object created out of the class. So in order to do that, I'm going to create a new Java class called b.java. And in b.java, we're going to make use of these methods. So in order to make use of these methods, I'm going to create a method within b, public void use case. And this is where I'm going to make use of the methods that I've defined within a.java. So because my methods in a.java are public, I need an object to work off of, and that object needs to be created using the a class. So I'll create an object of type a called obj1, and that's going to be equal to a new instance of the a class. And now I have an object that I can call these public methods on. So if I wanted to call the print this method, I would say obj1.print this, and it takes 2 strings as arguments. Now, I called them parameters earlier. They're called parameters when they're defined in the method. When I actually send concrete pieces of data to the method, we call them arguments. So if I pass it default and default2. Now, these are the arguments that I'm passing to the method. And so what will happen is obj1 will use that print this method to print out the words default and default2 to the command line, because that's what print this does. Now, what about static methods? I talked about them earlier. So let's talk about those by creating a new static method. Here we have a static method. Once again, the static method is void because we're not returning anything. We're just doing a print statement to the command line. And I've called the method static print. It takes one parameter, which is a string called print1, and it prints that to the command line. Now, because my method is static, I don't need an object instance to call this method. What I can instead do is I can call it directly off the class. So I could say a.staticPrint static. And that's how I can call a static method. So we can see the difference here is that to call print this, which is a public method, I've had to create this object, obj1, and then call the method. Whereas to use a static method, I've simply called the class .staticPrint. So that's the difference in how you use public and static methods. We can also do what we call overloading methods. And this is where we define two methods with the same name, but they take different parameters. And that allows us to handle multiple different cases where we have different types of data with the same method call. So for example, let's create two methods which are overloaded, which simply just return the data that they're passed. So our first one will be public int return value, and it takes a parameter of int called p, and it simply returns that value. We could also have public float return value, and it takes a float f and returns f. Now we have an overloaded method. We can see they both have the same name of return value, but they have different parameters. One takes in an int and one takes in a float, and they have different return types as well. One returns an int and one returns a float. I could return to my object where I'm calling methods, and I could define two new variables. Let's call the first one int an int, and we'll say it equals 5. And then we'll have a second one, float a float equals 6.7 f to define that it's a float. Now we could call that method to get ourselves a return type. So if I wanted to print these variables, I could do it in a roundabout way by using these return methods. I could say system.out.println, and then I could use my object.return value, and I could pass it an int. I could use the exact same method call, but I could now pass it a float. So in this case, I haven't changed the method call, but I've passed it two different types of data. One is an integer, and one is a float. And Java will decide polymorphically which method it's going to use based on the type that it's given. So this overloading of methods can be very useful when developing. So those are the features and components of Java methods and how we can make use of them. Java constructors are a special type of method in Java that are called automatically when an object is instantiated out of a class. So a class will have a constructor defined, and then when you create an object using that class, this code, whatever is defined in the constructor, is run automatically behind the scenes for you. In terms of naming, the name of the constructor has to match the name of the class. It has to have a public access modifier, it cannot be private, and it can't have a return type. So if you have a class called pencil, then your constructor is also going to be pencil. It would be public pencil, and then you can take any number of arguments. It doesn't have to take arguments, but it can if you want it to, and then you have the code to run whatever you want it to run after that. So that's how we run Java constructors in our concrete classes. Our abstract classes are exactly the same. We can define a constructor in an abstract class if we want to, and then any class that makes use of our abstract class through inheritance will automatically call the abstract constructor when an object is instantiated out of it. Interfaces, on the other hand, cannot have constructors. And that's because interfaces are another special form of abstraction that define just a skeleton of the code, but don't contain any code itself. So if there's no code there, there's nothing for the constructor to do, so we can't put a constructor into it. And just like any other method, we can overload constructors by having multiple different constructors. And there's always a default constructor in any Java class. Even if you don't define a constructor specifically, there is going to be one that Java will create for you behind the scenes. There are some considerations to keep in mind when we're dealing with Java constructors. The first is the super keyword. Oftentimes in Java, we're dealing with inheritance, where we have a superclass and a subclass. The subclass inherits from the superclass. And when we want to call the constructor of the superclass, we use the super keyword. So the super keyword allows us to invoke the constructor from the subclass. And this is because constructors aren't inherited from the superclass. The subclass doesn't necessarily inherit that constructor, but it does have access to the constructor. So if we want to call it, we use the super keyword. A slight deviation to that rule is with abstract class constructors, because abstract class constructors are invoked automatically as soon as any class that inherits from that abstract class is instantiated into an object. I mentioned at the beginning of the video that we can have multiple constructors and that they can be overloaded just like any other method. And we do that because constructors can take parameters or arguments. They can take any number of them, including taking no arguments or no parameters. And so we could overload a method by using the same techniques that we overload other methods. We give it the same name, but we give it either a different number of parameters or different types of parameters. So defining one parameter as an int in one instance of the constructor and defining it as a string in another, or having one parameter in one instance of the constructor or having more than one in another instance. This is how we can overload constructors. And let's examine what a constructor actually looks like by looking at a code snippet here. We have a class called student, which is declared on line 1, and this class has two properties defined on lines 3 and 4. The first is private string first name, and the second is private string last name, and both are initialized to null. So we're going to want to use a constructor somehow to give these actual concrete values. And our constructor we can see defined on lines 6 to 9. It's defined as public student, and that's our constructor declaration because it is public, and the name of the method or constructor matches the name of the class, telling Java this is a constructor. In this case, our student constructor takes two parameters, string first and string last, and it sets first name equal to first, and it sets last name equal to last. So when you create an object using class student, you would pass it two arguments, and then the constructor would be invoked to initialize using the parameters to define first name and last name. And let's look at another Java constructor example, in this case showing how we can overload Java constructors. So once again, we have our student class, and we've defined three different properties in our class. We have a private string first name, a private string last name, and a private int that represents the year of graduation called graduation year. Both strings are initialized to null, so we're going to want to use our constructor to assign them a value. And the graduation year is set to 0. And then we have our first constructor, which is from lines 7 to 11, which reads public student. So there's our definition telling it to be a constructor because it's public and it matches the name of our class. And it takes three parameters, string first, string last, and int graduation. And in this constructor, we use those parameters first initializes the string first name, last initializes the string last name, and graduation sets the graduation year. But we also have a second constructor, as seen on line 13 to 15. So once again, we have the declaration public student, matching the name of the class and matching the name of the first constructor. But in this case, we only take two parameters, string first and string last. We don't take a graduation year. And what it does is it calls its own constructor, but using a default graduation year of -1 and using the first and last name that's passed to the student. So the way this works is when you initialize an object, you can either initialize the object with 3 different arguments, and it would use the first constructor, or you could initialize it with 2 arguments, and then the second constructor would be invoked, which actually in itself invokes the first constructor by providing a default graduation year value. In this video, we're going to demonstrate the features and components of constructors. Constructors are a special type of method that are automatically executed when an object is created out of a class. So in order to take a look at constructors, let's first create a Java class. So I'm going to create a new Java class called a.java. Now, constructors have to be named in a very specific way. The first rule of a constructor is that it must match the class name, and it has to have no return type. So let's look at what a constructor for the A class would look like. We would assign it a visibility modifier like any other method. So we'll assign it a visibility modifier of public. The name of our constructor has to match the name of our class. So this will be public A. And then we will have our open and closed parentheses followed by our open and closed curly braces. So we can see here that we've created a constructor with a name that matches the class name. The return type is absent. Normally with methods, you might be used to seeing something like public void or public int to define what the method is going to return. With a constructor, we don't have that. So that defines the skeleton of a constructor. Now, what do we do with those constructors? Well, in order to demonstrate what the constructor will do, let's add a few instance variables to our class. We'll add int var1 equals 1. And we'll say int var2, but we'll leave it undefined. Now, we mentioned earlier that constructors are automatically called or executed when an instance of the class is used to create an object. So we might want to have certain variables set by default. So let's say that we want var2 to be equal to 5. We can do it the way that I did at first with var1, where I defined it to be 1, or we can set it up in the constructor to be automatically defined when an object is created. So now when an object of type A is created, the constructor will set the value of var2 to be 5. For simplicity, let's make these instance variables public so that we can access them directly. And let's show how you could use this with another class. So I'm going to create a second Java class called b.java. And we'll define a normal method, public void display within B. And what we'll do is create an object out of the A class of type A. So we'll say A test obj equals new A. So now I will have created an object of class A, and the constructor will have automatically run and assigned the value of 5 to var2. So now I could do system.out.println test obj.var2. And this would print the value 5 to the command line because it's been set. Even though it hasn't been explicitly set here on line 4, the constructor has been run and set it here on line 7. If we go back to class B, it might not look like it, but this class actually also has a constructor. Even if you don't explicitly define a constructor, Java will automatically create a constructor for you. Now, it doesn't really do much. You could think of it as just an empty method being there, but the fact remains that class B does by default have a constructor. Constructors can also take parameters. So I could say in public A, I could give it a parameter int n. And instead of assigning var2 to be equal to 5, I could assign it to be equal to n. And then when I go back to creating my test object, I could pass it a value of 5. And now, when it's created, the constructor is taking 5 as my argument to its parameters, and instead setting var2 to be equal to that value. And now we'll have the same result, print the value 5, because var2 is still being set to 5, but I'm setting it by passing an argument. And in this way, I could create more objects with different values for var2. So if I were to create a test object 2, now I could call the print line again on test object 2, but this would print the value of 6. There's no limit to the number of parameters that we can pass to a constructor. So I could have a second integer, which sets this .var1 equal to I. And then I could pass more values into the constructor. And what that's going to do is set var2 to be 5 when I create this first test object, and it will set var1 to be 10. Similarly, when I create the second test object, it will set var2 to be 6 and set var1 to be 7. We can see that even though I've defined in my A class var1 equals to be 1, because I have this call in my constructor, this.var1 equals I, whatever value I've set up here on line 3 will be overwritten by the constructor value of whatever argument is passed for this parameter. And constructors can also be overloaded just like any other method. So I can define a second constructor, and let's make this constructor deal with floats. So I give it one float as a parameter, and up on line 5 I've defined a float var3. So with this constructor, it will set var3 equal to f. Now I have an overloaded constructor. To use that, I can go back to my B class and define a new object. We'll call it testObj3. And I will pass it 8.7f. Now, because I've passed only a single float, Java will use this constructor, the second constructor from line 12 to 14, instead of my first constructor from line 7 to 10. And if I were to do a third print statement on testObj3 with var3, it would print the value 8.7. And in this case, var1 would actually still be equal to 1 because it hasn't been overwritten by this constructor. So that's how we can use constructors and the features and components of constructors in Java. We use Java modifiers to control the behavior of our data in the code. So for example, this might restrict certain things like who has access to our data or our variables, and how can they use that data. So the first type of modifier is an access modifier. And these are the ones that are defining who can access our data. So these are things like public, private, and protected. We also have non-access modifiers. And these aren't concerned with how the data is accessed, but rather how the data behaves. So these are modifiers like final and static. And we'll take a deeper look at what these modifiers mean later on in this video. Our access modifiers are private, protected, and public. The private modifier is the most restrictive, so anything defined with a private modifier, like a private method or a private variable, is going to be accessible only to the class in which it's defined. Other classes won't have access to whatever is defined as private, and any subclasses that inherit from that class will not have access to anything defined as private. Protected means that the method or variable defined as protected is accessible to anything within the same Java package, as well as any subclass. So if a class inherits from a class with a protected modifier, then anything that is protected will be also available to the subclass. And finally, we have the public modifier, which is the least restrictive modifier. Anything defined as public will be available to any other Java class. And we have one other access modifier that's not in this list called package private. And this is the default modifier that's given to anything that doesn't have a modifier explicitly defined. So if you define a method as neither private, protected, nor public, then it will by default be given the package private modifier. And what this means is that method or variable is accessible to anything within the same Java package. Let's examine a very typical Java code framework using Java data encapsulation. It's generally good practice to define your variables within a class as private. You don't necessarily want other classes to be able to directly modify your variables. Instead, you want to be able to control how those variables are modified. So just because we have a private variable doesn't mean it can't be modified in any way. It just means it can't be modified directly. And what we use are public defined methods. And in this case, we'd use something like a public setter and a public getter method. And what these do is they allow other classes to set your variable's value and retrieve your variable's value. And the advantage to this is you can control within those methods how they're set. So within your public setter method, you could add checks first to make sure that the variable is as you expect it to be. So let's say you have a private variable that is of type integer. Well, you might want to check in your setter method before you assign the value to that variable, am I dealing with the correct type? Is this an integer? And maybe you also only want to allow a range of integers from, say, 10 to 20. So you could also add a check, is this value that you're trying to set my variable to within the acceptable range? And if it is, then I'll allow it. If not, then I'm going to throw back an error and say you can't set this variable to that value. So it adds this layer of protection by setting up a private variable with these public methods. We also have a list of some of the non-access modifiers that are present in Java. So some of the more common ones that you'll see are abstract, which indicates that there is no body contained within a method or a class. It's just a skeleton that you're going to have to implement yourself once you inherit from this class. Final, which in the case of a variable means that the value contained by that variable cannot be overridden or modified. Static, which means that the attribute is part of the class itself. So for a method, it means that you can call that method without having to instantiate an instance of that class as an object. These are three of the very common non-access modifiers that you'll see. We also have a few less common non-access modifiers, things like strict FP, which we use to restrict the rounding and precision of floating point calculations. Synchronized, which we use when we're dealing with multi-threading operations, so that we can make thread-safe operations in terms of telling Java how many threads can access a certain method or a certain class at a given time. And transient, which restricts data serialization on a class. Here's a code snippet showing the use of a non-access modifier in Java. So we have our public class hello world defined on line 1. And within that, we have two fields. We have a final int r equals 10 and a final double pi equals 3.14159. And since they're both defined as final, that means that those values can't be modified or overwritten or changed in any way. Below that, on line 5, we have our main method declaration, which the body runs from line 6 to 9. And what it does is it first instantiates an object out of the hello world class called myObj. And then it tries to directly manipulate our two final fields, myobj.r equals 50 on line 7 and myobj.py equals 25 on line 8. And we can see in the comments, both of these will generate an error. And then finally it tries to do a print statement, system.out.println myobj.r. But we can see down at the bottom of the screen where it says Java C hello world.java, this program doesn't compile. And that's because it's throwing us this error, cannot assign a value to final variable r at myobj.r equals 50. And the same error, cannot assign a value to final variable pi. So we can see in action the use of the final modifier preventing our fields from being modified. In this video, we're going to demonstrate the features and components of Java modifiers. Java modifiers are keywords that we can place before classes, fields, methods, in order to apply certain effects to them. So in order to take a look at what these modifiers are and what they do, let's create a couple classes. I'm going to create one Java class called a.java, and I'm going to create a second Java class called b.java. There are two basic types of modifiers. We have modifiers that are responsible for controlling who can access a certain class or attribute and how they can access that. And we call those access modifiers. And we have a second type of modifier that are responsible for defining the functionality of the data. So what is the actual class doing, or what is the actual instance variable doing, and how is it doing that? We're going to start by looking at access modifiers, and we actually have an access modifier present already in the skeleton of our a.java class on line 1. That access modifier is public. So let's start by talking about access modifiers on classes. For classes, we only have two options. We have the default option, which is where no modifier is explicitly defined. And by default, if you don't explicitly define an access modifier, then a class will only be able to be accessed by other classes in the same Java package. Alternatively, if you define a class as public, then that means that the class can be accessed by any class. No restrictions there. Almost always, your classes are going to be public. Very rarely will you be not explicitly defining them as public, but there might be some niche cases where you don't want your class to be public. Now, when it comes to things like instance variables or methods, we have a few more options. So let's define a public int mod equals 5. The name and the value aren't necessarily important for this demonstration. What's important is, again, this keyword public. But I mentioned that we have a few more options when it comes to things like methods and instance variables. So let me make a few more instance variables using the different options, and then we'll look at what each of them does in turn. My second option will be private int mod2. And then I will just define a variable or an instance variable without any modifier at all. Mod3 will be equal to 7. And it will be type int. And then finally, we'll have a protected int mod4 equal to 8. So these are the different options that we have when we're looking at instance variables or methods. A public modifier means that this variable is accessible to all classes directly. A private modifier means that this variable is only accessible within the class in which it's defined. When I don't define a modifier, that means that Java will use the default behavior, which will make this variable only accessible in the same package in which it's defined. Protected is the same as without declaring a visibility modifier, in that it's only accessible in the same Java package, but it's also accessible to any subclasses. So any class that inherits class A will also be able to access this protected variable. So to see how we would use each variable differently, I will create an object of type A in class B. And now I have an object that I can access the variables in different ways. So to access mod, because it's public, I could do system.out.println obj.mod. And then we'll encapsulate this within a method to make it functional. So this will print out the value of mod. Now, if I were to try to do the same thing for a private variable, this will give me an error because I can't access mod2 directly. I'm no longer inside of the class in which mod2 is defined, and mod2 is private. So in order to access mod2, I would have to have some sort of getter and setter available to me, which would be a method inside of class A that would allow me to access mod2. But as it stands, I have no way of accessing mod2 outside of the A class. For mod3, will still work. I can print out the value of mod3 by accessing it directly because I am working in the same Java package that mod3 was defined in. And similarly, I can print out the value of mod4 because once again, I'm working in the same package as the mod4 was defined in. Access modifiers on methods work exactly the same as they do on fields or instance variables. So if I wanted to provide a method that would allow me to get the value of that private variable that we have, I could do that by defining a public int get mod2 that would return mod2. And now because this method is public, I can use it to get access to this private instance. And I could do that by going back to my B class and calling system.out.println obj.getMod2. And this will print the value of mod2. So that's how we can use these modifiers in tandem. We can use these public modifiers on methods in tandem with private modifiers on variables to work together. If I have a method that I don't want to be able to access outside of class A, I can define it as private. So for example, private int getMod could return mod. And in this case, I can only use this method within class A. If I tried to go to class B and call system.out.println obj.getMod, this will give me an error because that method is private and not public. I mentioned at the start of this video that there are two types of modifiers. Up till now, we've been talking about access modifiers. The second type of modifiers were the modifiers that control more of how the data is handled rather than how it can be accessed. And these are called non-access modifiers. Non-access modifiers can actually be used in tandem with access modifiers. So I'll be adding our non-access modifiers onto our existing variables that already have access modifiers applied to them. The first non-access modifier that I want to talk about is final. So I can add to my instance variable mod the keyword final to make it public final int mod equals 5. And what this will do is set mod in such a way that it cannot be overwritten or changed or modified in any way. The value that it is assigned right now of 5 is the value that it will stay. So in my B class, if I were to say obj.mod equals 6, that will give me an error because I'm trying to modify a final variable, and I'm not allowed to do that. And we can see my IDE is telling me there's a related problem because I'm trying to modify a final variable. The next non-access modifier that I want to talk about is static. So we'll use static in a method by defining public static int return an int. And this will just return the value 7. So we have defined here by using this non-access modifier static that this method is a static method. And what that does is tell Java, I can access this method on an instance of a class directly. I don't need to create an object first to access that method. To see that in action, over here in the B class, up till now I've been accessing all of my methods on an object. But now that A has a static method, I can print out a.return an int directly, and this will print the value 7. And I didn't need to create an object first. I can do it directly on the class. Going back up to our class A, there are non-access modifiers we can use on classes as well. One of those is final. Now this behaves a little bit differently than when we define final on an instance variable. Final on a class means that this class cannot be inherited. So if I was to try and inherit A on class B, it will give me an error because A is a final class and I'm not allowed to inherit from it. The final modifier that we're going to talk about is abstract. In order to talk about that, we'll create a third class, c.java, and this will be an abstract class. And we define it as an abstract class using the non-access modifier abstract. So we have public abstract class. And what this means is that C as a class cannot be used to create objects out of it directly. So if I were to go back to b.java and try to create an object of type C, it will give me an error because C is abstract and cannot be instantiated. So I can't use it directly like that. Instead, abstract classes are inherited. And when we inherit an abstract class, we have to implement all of the things defined within the abstract class. What gets defined within an abstract class? Well, usually we define an abstract method. So I might have public abstract int abs method. And this uses a non-access modifier abstract on a method to create a framework within this abstract class saying, if you inherit this abstract class, you have to implement this method. Now you'll see an abstract method doesn't have a body of code after it. It's just a framework defining the name of the method and saying that it's abstract. When we implement the abstract class C through inheritance, we would have to define our own code within the abs method. What we define abs method as doing is up to us, but it has to be there. And that covers the features and components of Java modifiers. In this video, we're going to put together everything that you've learned so far in order to create a basic Java program and show how we can go from code to compiled code with a Java program that we can run. The first thing that we need is code that we can run. So let's create a few Java classes in order to create our code package. We're going to create a simple Java program that will ask for user input to give us a sentence or a word or a string of any sort, and then our Java program will read that word in, reverse it, and print out the reversed word or string back to the command line. So our first class will be a class designed to get user input. So we'll create user input.java. And in this class, we're going to import the scanner package from Java in order to use it to get user input. So at the top, we'll do import java.util.scanner. Now we can utilize that scanner class to get user input. So within our user input class, we'll define an instance variable to store the user input. So we'll define a private string and leave it as null. And now we'll create a method that will ask the user to input a string, and then we'll assign that inputted value to imp. Now we're going to create a class method that will read in the user input and assign the user input into our string value imp. So the method will be public, void, because we're not going to return anything, get user input. And it takes no parameters because it does not need to take any parameters. And now within our method, we're going to create a new scanner object. We'll call it sc equals new scanner. And as a parameter or an argument, we'll pass it system.in. Next, we'll print out a line to the console to let a user know what they're supposed to do. And then we will read the next line that the user types in and assign that value to imp. So now we have a class that will get user input and assign it to a value. We also want to have a way to retrieve this value from our main class. So we'll have a public string get imp, and this will return the value of imp. Now our second class will be a string reverser class. So let's create a new class called string reverser.java. And we're going to use a static method within the string reverser class, which will return a string called reverser. And it takes as a parameter a string s. To reverse a string, we're going to use the string builder class. So we'll create a new string builder called sb. And then we will append our parameter to our string builder class, and we will return the reversed string. And that's all we need there. So finally, we'll create a third class, and this will be our main class. This will be our driver. So this will be called main.java. And within our main class, we'll define our main method. And this is where our Java program will start its execution. So the first thing that we want is an instance of the user input class. And then we'll set the imp value by calling ui.getUserInput. And then we'll define a new string to get the value that the user has input. Now, our instance variable input contains the value from our user. So we will create the reverse string by using our static method. And we're passing as a value to that static method the forward input from the user. And then we're storing the output into a new string called reverse string, which houses the reversed string from our method. And finally, we'll print that to the command line. Now we have our code. We're ready to compile and run our Java program. To do this, I'm going to open up a terminal in the directory with our Java code, specifically our main class. So we can see I'm not in the directory that I want to be in right now. So I'm going to change directory into source. And now we have the files that I want. You can compile each file individually, or if you compile your main class with the main method, it will compile every other class that it uses and needs along with it. To compile, I'm going to use the command javac, And I'm doing this in a terminal. You could do it in PowerShell or any other terminal emulator, whatever you prefer. If you're on Linux or Mac, odds are you'll use terminal. If you're on Windows, you could use command prompt or PowerShell. The command is going to be the same either way. It's going to be javac, and then I pass it my main.java. And now the command is completed. And if I do another directory, we can see some new classes have been created. Previously, all I had was main.java, string-reverser.java, user-input.java. Now I have main.class, string-reverser.class, and user-input.class. So Java has compiled all my code into Java-compiled bytecode. And now I'm ready to run my program by calling Java main. And it's asked me to please type a string. This is a string. And we can see the next line right below this is a string has printed out a reversed value of my string. So those are the basics of how we create a Java program, compile a Java program, and run a Java program. So in this course, we've examined the components of a basic Java program. We did this by exploring basic Java programming features, Java classes, attributes, and methods, features, and programming, Java constructor and modifiers, features, and programming, compiling and running a basic Java program from the command line. In our next course, we'll move on to explore the Java programming basics and the Java programming style guide.